All right, welcome back. And so now what we're going to do is build these circuits. So we're going to build the inverter, we're going to build the NAND gate, and we're going to build the NOR gate. So again, inside of the document here, the book, you can take a look at these and just kind of review them. But we'll start off with the inverter because that's kind of the basis of everything. So once we have this inverter circuit, where did it go? Once we have this, we can just put two of those in parallel and we can do the NOR gate, and then we can put two of those in series and we can do the NAND gate. All right, and then again, we can take a look here at our document we've been kind of marking up here on the blackboard. So we're going to change what's in the book a little bit, and we're going to use a 2.2K in the base resistor here to drive it, and then we're going to use a 100K pull down to just make sure there's some signal, and then 100 ohms up in the collector. All right, so that's kind of our basis. So this is our little building block, all right, and we're just going to use PN2222 transistors, all right. So let's go to the bench and let's build these things. Okay, so I am pretty excited. You know I like building stuff, so let's get right to it. So first we're going to build the inverter. So hopefully you have that up on your screen so you can kind of figure out what we're going to do, but we're just going to start off here with a 2222 transistor, which is NPN. And why don't we, as a matter of fact, what we'll do is we'll put the inverter over here, and that way we'll create either a NOR or a NAND gate here, and then we'll use this inverter to invert the signal at the end. So we'll put one inverter here, which we'll leave, and then we're going to add two more inverters to make a NOR and a NAND gate. All right, so we start off, and remember it's emitter, base, collector. All right, so we're going to take the emitter and we're going to put that right to ground. And we're going to do this with a 5-volt system. So we're going to put our power supply at 5 volts and run that in those rails there. All right, and now we need the collector is going to go up to the power rail through a 100 ohm. So we're going to find that. I've got all my resistors here. And I'm going to try and make these fairly small. As a matter of fact, let me zoom in just a little bit for you. I'm going to try and make these fairly small so that these little blocks, we can replicate them and they're not going to use up too much space. All right, now what else do we need? We need the base. We need the base, and that's going to be fed through a 2.2 K resistor, and that's going to be the signal, either high or low logic. So let's get a 2.2, which is a red, 2.2K. And we'll go ahead and put that right there. And then also, off the base, we're going to take that base and we're going to put it to ground through a 100K resistor, and that's just going to keep it with a stable signal, so it's not floating. All right, you'd be surprised. These circuits can kind of float, and you can touch them, and you can get them to a changed state. So we're going to put a resistor there, 100K, and that's going to give us a steady signal. Okay, so now we've got our inverter. That's it. I mean, that's pretty cool. So that's all there is to it. So now let's get something to put a signal in here. So what I'll do is I'll just take this wire, just this wire, and then what we'll do is we'll connect the wire to either ground or +5, and then that will be the signal in, and then the signal out is going to come out here. So let's get that for now, and then we may change this a little bit. So here's the output. So here's the logic output right here. All right. And then what I want to do is I want to put that through an LED so we can see it. So let's just get a green LED here. And then let's use about a 220. Here's a 330. I'm just looking for what I kind of like. Let's use a 330 ohm resistor here. I don't want to pull too much current, so that's a orange, brown. And then we're going to go to ground. And remember on these LEDs, the flat spot is ground. Oops. The flat spot is ground. Let's go on the zoomed in camera again. So if you look at this, you can see there's that flat spot. Let me get it so you can see it. Green's not the best color. The flat spot is there, all right? And then it happens to be, you can see that big post there, the big flat post. That's ground, all right? Okay, so that's going to go to ground. All right, so there's our circuit. All right, so when there's a high we're going to get the LED is going to be on, and when there's a low, the LED will be off. All right, now remember, this is an inverter. All right, so let's go ahead and let's power this thing up. Let's see what happens. So I've got 5 volts going in. Now, right now, we've got this weak low on here, right? So that's why we're getting a high out. All right, so now let's actually put a low. So now we've got a low and we got a high out. That's good. All right, and then we'll put a high and we get a low. All right, so when we put a 1, we get a 0, 0, we get a 1. Perfect. All right, now let's go and measure, and there's our little red LED to let us know that our power is on. Now let's measure the voltage here. So let's measure the voltage because we want to see what's going on with that. So what I'm going to do is I'm going to get one of our handy meters here, and a bunch of stuff is going to drop off the table. All right, so I've got a meter, and I'm going to get one of our little probe connectors here. And what I'm going to do is I'm going to connect it right here before the resistor because I just want the voltage at that node. All right, so that red lead is going to the output, and then I'm going to take this yellow lead to ground. All right, so we need a ground reference. Let's do that. And the power is still on, but I'm not going to short anything, so I think we'll be okay. All right. So now I'm going to connect up the meter. All right, so the meter's connected. You can see it there. And let's get it a little bit out of our way there. Okay, and now let's get the actual meter in the picture. Zoom out. Alrighty. And there we go. Okay, let's turn our voltmeter on. Okay, so right now we've got a 0 for our output, and we're showing 106 millivolts or 0.1 volts. All right, so that's good. So that's almost at ground. Now let's put a 0 in, which will get us a 1 out, and then notice we're at 4.33 volts. 4.33. Let's get rid of this LED. When we get rid of the LED, now notice now what happens because we're dropping no current, or we're pulling no current through the LED to ground, we get the entire 5 volts out of the system. All right. So, but remember, the moment we put this LED, now we've got a load, and this LED is about 10, 15 milliamps. So that current then drops over our collector resistor, which is at 100 ohm there. All right. So that's why you got to be careful. You want a really small collector resistor, so as you pull a lot of current, not a lot of voltage drops there, and you still get your full voltage out. But the point is that even with our LED in the circuit there, we're still getting 4.33, and that's well over the minimum for a 1, which is 2 volts, right, in the TTL system. All right, so that's an inverter, so that works. All right, so we're done. All right, now what we're going to do is we're going to copy this circuit, and we're going to copy it 2 times. We're going to put it here, and we're going to put it here, and then we're going to make a NOR gate, and then we're going to make a NAND gate, or a NAND gate and a NOR gate, whichever one. And then we'll take the output of that through this inverter here, so we get a proper OR gate, or an AND gate. And I know it's hard every time I say a NAND gate or a AND gate, right? You gotta be careful. So anyway, let's do that. All right, so let's turn the power off. Let's zoom back in. All right, let's go ahead and build this. I'm going to move this meter here, and I'm going to get rid of this line right here. All right, so let's copy this circuit right now 2 times here and give ourselves some room. All right, so I've got these 2 other transistors, 2 other 222s, and they're all of the same manufacturer because I want them to, I want them to be semi-matched. So that's important. If you're going to do things, you might as well use the same manufacturer. All right, so let's put the ground leads from each of our emitters. Let's get that in. So all our emitters go to ground. So we've got 2 of them here. So there's one. And then here's the other one. Okay, looking good. All right, then what else do we need? We need our, let's work with the base right now. So at the base, we need a 100K to ground in both of these. So let's do our 100K to ground. There we go. And 100K is brown, black, yellow. Brown, black, yellow. All right, brown, black, yellow. So there we go, good. All right, and then before we go put the collector resistor, we're going to, let's continue finishing the base circuit. So we need 2.2 Ks coming out of the base. That's what's going to feed each one of the bases. That's where our inputs are going to go. So there's one of them, that's red, 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 right? Red, red, red. And another red, red, red. All right, so there's our circuit there. Okay, so and then we'll just use wires to connect both of these. Okay, so now let's go back to the blackboard on the computer there, right? Okay, so here on the screen, this configuration right here, when we have the two transistors in parallel like this, and we have just one collector resistor, this is going to be the NOR gate. So when they're in parallel, it's going to be the NOR gate, all right? So let's do that first. So we're just going to use one collector resistor, and we're going to tie both of the collectors together, and that'll be a NOR gate, all right? All right, so we just need one collector resistor. So we're going to take it, and we're going to put it right here. That'll be our final output. All right, and then we're going to tie both of the collectors together. All right, that's going to take both of our gates and just tie them together. All right, so there they are. You know what, let's use a little bit shorter wire there. So that ties both the collectors together. All right, and then now we need our output, which is also at that collector point. And so that's going to go to the input of this other inverter, because this is going to end up being a NOR gate. All right, and then we're going to take that output to here. But first, let's just confirm that this is a NOR gate. All right, so let's take the output here. So we're going to take the output, and again, we'll put it through, take it through a wire here, and we want to conserve space. As a matter of fact, let's do this. Take the wire, we'll put it like that, and then we're going to take a resistor. Let's take another 330 ohm, and then we'll put the resistor right here. So this is a little bit tricky, so I'm going backwards. So there's the output, and then I'm putting the resistor here, and I'm going to then go to ground. All right, so I'll use a red LED here to differentiate it. So here's a red LED, same thing, flat side is a ground. All right, so we're going to hook the output there to ground. All right, so now forget this inverter over here, just ignore this. We're not using this. So now this is going to be a NOR gate. So basically we're going to put an input here and an input here, and then we're going to see what this LED does. All right, so if you get I want you to have your truth table for the NOR gate, get your truth table for the NOR gate in front of you, and I'm going to get it myself also. All right, so all right, so the only time we should get a 1 out is if we put 2 zeros in. Everything else should be 0. So the only time we'll get a 1 out is if we put 2 zeros, all right, 2 logic zeros or 0 volts, all right? So the system is off. All right, let's get it right there, and let's go ahead and let's turn it on. Powering it up. We've got our LED there. Just forget this one right here, this green one. All right, so right now we've got a 0 and there's always zeros in here, right? So there's always zeros in here. And let's see, are we doing something wrong here? Do we put this, yep, we put this LED in wrong. All right, there we go. So 0 and 0, there's always a 0 in there, we get our 1 out. So now let's just emphasize that by putting these to 0. All right, there we go. So we got a 0, 0, and we get a 1 out. Now every other combination, we should get zeros out, which means the LED will be off. All right, so let's make this one high. That one's high now, and now it's off. Let's put that one back low, and we'll put the other one high. And sure enough, and now we'll put them both high. All right, so that is a NOR gate. All right, so that's a NOR gate with a positive logic output. So it's when it's on, it's a 1. When it's off, it's a 0. All right, now let's take this output, and that output should be about 4.3 volts or whatever, because some current is getting drawn through this LED here, right? It's getting pushed through the LED to turn on the LED, so we're dropping a little bit of voltage over the collector resistor. But we've still got 4 volts. That'll be more than enough to work this inverter. So now let's get another wire. Why don't we use a purple wire so we can see the connection here? And let me come in just a little bit here. All right. Now let's connect the output of our NOR gate to the input of our last inverter. So now we've got an inverter here. All right, And this inverter is inverting this signal here. So if this is 0, this will be 1. So now you can just forget this output right here. This is now going to be like an OR gate, right? So we've inverted the NOR, so that gets us back to an OR. So this is the OR. So just forget this red LED here, and let's see what happens, all right? So we put 1 and 1. See, we got the 2 wires going in the red. That's 1 and 1, 5 volt, 5 volt. We get a 1 out, all right? So now let's try 0, 1. 0, 1, we get a 1 out, and we should, right? Anytime there's a 1 or both are 1. All right, let's try 1, 0. We get a 1 out. Looks good. Now let's do 0, 0. 0, 0, we get a 0 out, right? That's the only time the OR gate is 0. Anytime there's any 1s or both 1s, we're going to get a 1 out, right? So let's go back and put a 1 there. Look at that. It works exactly as we would expect. There we go. Perfect. All right. And if we wanted to have a little fun, we know that we've got zeros, these weak zeros, these pull down 100K. So what we could do is we could put switches on these inputs. Why don't we put some momentary switches on there for fun? All right, so let's just put some momentary switches. So we'll put these momentary switches, and then both of these are going to go high. So I'm going to connect those to the +5 rail so we can switch in +5 at will. All right, or 1, right? All right, so right now there's 0, 0 on here. Now there's 1, 0. Now there's 0, 0 again. Now there's 0, 1. And now if I push them both, there's 1, 1, and we get the 1 out. So isn't that cool? So we have just implemented TTL logic, basically. Very simple TTL logic. All right, and that is the NOR gate, and then we invert it again, and that gets us back an OR gate, or creates an OR gate. Now let's turn this into a NAND gate, all right? So let's turn the power off. So the NAND gate, let's take a look at the back at the computer real quick. So the NAND gate, what does that look like? We just need to put them, the 2 transistors in series. So see this? We still have the single 100 ohm, right? But now we take emitter to collector, and then the other emitter goes back down to ground. So we're just going to connect one emitter to one collector, and then put them in series, and that's going to give us our NAND gate. All right, let's go do that. Okay, so we've got this, and let's see here. Since this transistor's already got the collector resistor here pulling up to the top rail, let's use this one as the top one, and then here's our emitter going to ground. So now what's going to happen is that emitter is not going to go to ground. We're going to undo that. It's going to go over here to this collector. And now we're putting both of these transistors in series. So only when both of these transistors are on or off are we going to get the action that we're looking for, all right? So hopefully I did that right and I didn't make any mistakes. But you see, I only just moved a couple wires. Very, very simple. All right, so that's that. So now we'll have a NAND gate. So right here, this will be a NAND output, and then this will be an AND output because we've inverted it here. So for now, let's just pay attention here. Let's go look at the truth table on the screen for the NAND gate. All right. So let's give this a try. So for a NAND gate, right, think of it as, the opposite of an AND. So an AND, the only time you get a 1 out is if both inputs are 1. So if both inputs are 1, you get a 1 out. Otherwise, you get 0 out. So the NAND will be the opposite of that, all right? So the AND will be the opposite of that. The NAND will be the opposite of that. I know it's confusing. All right, so let's power it up. All right, so right now we've got, and there's always these zeros on here, these weak zeros. So we've got 0 and 0. Now normally that would give us a 0 in an AND gate, right? But in an AND gate, that's going to give us a 1. And over here is the AND gate, right? Because we invert it, so we've still got 0. Now let's do 1, 0. So if I press this, I'm going to get a 1. This is already giving us a 0. So 1, 0, right? With an AND gate will still give us 0, but with a NAND gate we'll get 1. And sure enough, as I press it, all right, and same thing if I press this one, this will give me 0, 1, all right? So you see the AND gate, still nothing, but I'm still getting the 1 here. Now, only when I press both of these will an AND gate give me a high output, right? But then the NAND gate will invert and go to 0. And there we go, all right? So the first one's a NAND, and the second one is an AND, all right? So how cool is that? So we've just implemented an inverter. We've implemented inverter, NAND, NOR, uh, and OR. All right, that's a big tongue twister. So we basically just created all the gates, the basic gates. Now there's another gate, XOR, and I'll show you that on the screen. So back at the computer. But so let's see. Is there anything else we want to take a look at here? Not really. So we could keep taking these blocks, and if you really wanted to do something crazy, we could make little ICs out of these. We could make little print circuit boards, and we could make a little 2-input AND or NAND, an inverter, and so forth. And then we could tie these together, these little blocks, and plug them in here. If you really wanted to, that might be fun to do. Actually, is just make simple transistor-based logic. All right, so let's go to the computer, and I want to show you one more gate real quick. All right, so we're back here on the computer, and let's just go ahead and why don't we erase some of this, because we don't need this anymore. So let's just erase this NOR here. And what I want to show you is a gate called an XOR. All right, let's get the color we want here. All right, XOR. And this stands for exclusive OR. Exclusive OR. And the logic for this is, let's start with the truth table. Let's do a truth table here. So we're going to do XOR. All right, and let's have X, we'll have Y, and we'll have Z. And an XOR is an interesting thing. So we've got 0, 0, 0, 1, 1, 0, and 1, 1. Only when the inputs are opposite will you get a 1 out. So that's called an exclusive OR. So only when the inputs are opposite do you get a 1 out. All right, and the symbol. So now let's take a look at the symbol. Let me show you this. So we'll go XOR. Go to images. So the symbol, this is a poor one, but this is a good version of it. So it's just an OR gate, right, with this line here like that. That's it. That's all an XOR is. And then the symbol is like the OR, except with a circle around it. That's it. So that's all it is, all right? So if we go here, and we can draw our OR gate again. So there's our OR. And I'm not doing it good either. Sometimes it's really hard to draw straight lines on this, I'll tell you that. Wow. There we go. There we go. Not too happy with that. All right. So then here's one input, here's the other input, and then let's put this in green. So then you just you do another one like that. All right, and that's the XOR. And then here's your X and here's your Y. And then the output here is Z. All right, and there's no inversion on this. This is just XOR. All right, there's also an XNOR. So if you did want the opposite of that, that's the XNOR. And this would be Z bar here. And that would be 1, 0, 0, 1. So this would be the XNOR. But an XOR is when they're opposites, you get a 1. And the XNOR is just the logical opposite of the XOR, which is you get 1s when they're the same, and when they're opposites, then you get 0s. All right. So, but we're interested in the XOR. So let's erase this little dot here, and let's put that back to how we had it. Let's do it in the right color. Okay, and we'll just put that output right there. All right, so that's the XOR. Now, so this is really, really useful if you want to determine if two signals are opposites, right? Then you'll get a high signal out, right? So that's useful, all right? Like if they're opposites, in this case right here, then you would get a high out, right? And if they're the same, you get 0 out. So that's very useful. Now, we're going to do a lot more digital logic and Boolean algebra and all that in the next chapter that we get into. But before we go into the next topic, which we're going to talk about clocks and timer chips, there's let's do one other little experiment here. We'll just do it here in the Blackboard. So, and we're going to talk about this more. We're going to talk about what's called combinatorial logic. But we know enough now, and you're programmers, right? You're a programmer, so you should be able to do this. So if we want to do an exclusive OR, right? We want to do an exclusive OR. So what do we want? We want to basically say if x equals 0, right? So let's just write some code here, all right? So I think everybody would be comfortable if I write a little bit of C code, right? So if I say, which is like JavaScript or Java or any C-based language, PHP, Python, you name it. So let's code out what an XOR is. So this is what we want. So if x equals 0, right? And then I'm just going to write and because I'm not even going to try to draw the symbol, and y equals 1, right? So if this is one case. So if x equals 0 equals 0 and y equals 1, all right? Or what's the other case? If x equals 1 and y equals 0, right? Then we're gonna return a 1 here, and then else we would return a 0 here, right? So this is kind of the implementation of the XOR. So we could write it out. So logically, we have to test these two conditions. So we have to say if x equals 0 and y equals 1, or x equals 1 and y equals 0, then output a 1, else return a 0. So that's in code. Can we do that with digital electronics? And that's the beauty of digital electronics. It's just literally like the code. It's very, very simple. All right, so first we need to get two AND gates. So let's get some gates up here. We'll use this color. All right, so we need an AND gate to ask the question if x equals 0, and so we need x equals 0, y equals 1. So here we go. So here's one AND gate. All right. And we're going to ask the question, and we'll put in x right here, and we'll put y in right here. All right. And let's run the wires out a little bit longer here. So here's x and here's y. All right, we want to ask the question when x equals 0 and y equals 1. When x equals 0 and y equals 1. All right, so now watch this. So if x equals 0, let me invert that. So let's put an inverter right here. But I'm going to represent an inverter just with a dot, right? Really, it's this thing right here, right? But I can just represent it as a dot. See, these dots mean inversion. So there's like an extra inverter right there. We just don't like drawing the whole inverter, right? That would be a pain. So here's x, and then here's a dot. So right after this is not x, right? So this is saying if not x and y, and it's going through an AND gate here, then it's going to give me an output. So when x equals 0 and y equals 1, this will equal 1. So that is one case of the XOR, right? So that's what we want. Now what's the other case of the XOR? So let's draw another AND gate. And this is why digital electronics is fun. I mean, it is literally like the code. Now, again, we need this x and we need this y, right? So we'll just take the wires right here. And as a matter of fact, let's draw them with a slightly different color here. Why don't we draw them with red? As a matter of fact, let's just keep it simple. Let's just put x here and let's put y again. All right, and we're going to put those right into that AND gate. All right, and then what I was just trying to do was, you could, if you wanted to, just draw wires here. We could have just, drawn a wire here and connected it like that, and then draw a wire here, and then, jump over this and connect it right here, right? It's just a little bit harder to see. So we'll just put these x and y's again here. All right. Now, the second case is when x is 1 and y is 0. All right, well, when x is 1, that's when x is 1. We don't do anything to it. But when y is 0, we'll have to invert it if we want this AND gate to output high. So now this piece right here tells us what? It tells us this. It says when x not and y, right? Isn't that cool? And then this one tells us x and y not. All right, that's what each one of these gates literally says. So that is each one of those logic pieces of that if statement. Now, we need to OR this together. So if either of these cases happen, now I want a 1. All right, cool, no problem. Go like that. And this is kind of how you draw this stuff too. So we go like that. And then here, let's go, what's our OR look like? It looks like one of these guys. So we go like this, go like this, bring it down, bring it up. There we go. And so now this term right here and then this term right here are going to get OR'd here. So this is an OR, right? And these are ANDs, right? These are both ANDs, and there's an OR. So this final term right here, Z, so here's Z. So what does Z equal? So Z equals what? All right, let's break it down. It equals X and Y, but it's X bar or X naught. That's that term right there. All right, then OR, and we could put parentheses around this too, no harm in that, or X and Y naught. X and Y naught. That's it. And then if you want to put some parentheses around the whole thing, you could do that. This right here, this is XOR of X and Y. It is equivalent to this, equivalent to that. All right, so inside, if you look at the circuitry inside of an XOR, it's going to literally look like the circuit that we've just made right there, right? And if you couldn't get an XOR gate, right, you didn't have the chip or whatever, you could do it with ANDs and or you could do it with NANDs and NORs, right? You can always do it with those. So so let's take a quick look. You know, I like to show everything. I like to be thorough. So let's look for XOR. And I used to have this memorized, what an XOR was, but I actually have forgotten. And let's see here. Let's see. If we just, let's try this. If we type in TTL XOR gate, TTL XOR gate, and we'll get a number off here. Yeah, 74LS86. I should have known that. 74LS86. Yep, go. 74LS86 is a quad 2-input XOR gate, and we just look at the PDIP package right here. Here's one here from Texas Instruments. I've got a bunch of these right over here to my left. All right, and let's go and look at this. So this is XOR. It's a number of circuits is 4, number of inputs is 2. Yep, it's TTL, looks good. Let's go here to the data sheet. Let's pop this open. All right, let's zoom into this. All right, and obsolete. This particular one is obsolete. Look at that, 1972 is when it first came out. Wow. All right, and then the latest one is probably, well, they've obviously got this in other logic families, but I'm sure you can still find this. All right, so there's that symbol again, right? And then let's see if they have. I'm trying to find if they have an equivalent circuit here. Let's see here. So these are just showing the of each input right here, but it's not showing the entire circuit. Let's see if we can find that inside this data sheet. Probably not. Looks like it's going to end right here. Yeah. So we could type in 74LS86 internal circuit and see if we can find this from a different vendor. Let's see, op amp operational. Huh. And that's still that same Texas Instruments one. Anyway, the point is I wanted to show you what was in here, but so that's that. And then you can see right here there's that logic again. So there's exactly what we said. The output is the input exclusive ORed with B, which is equivalent to A naught and B, or A and B naught. And notice that multiplication, in this case, they just put them adjacent, they don't put the dot, whereas we formally are putting the dots. And you don't need to do that. You can just put the variables right next to each other. And we're going to learn more about this when we talk about Boolean algebra in the next chapter. All right, so let's wrap this up right here. So this is a good little demo lecture. And we're going to come back and do clocking circuits. We're going to learn about crystals a little bit, oscillators a little bit. We're going to run them over there on the oscilloscope so you can see these things. And we're going to talk about the famous 555 timer, which is the basis of like a gazillion circuits that you can build and so forth, and kind of came out in the 70s as well as like a simple timer chip. All right, so I'll see you in the next lecture. Bye. All right, welcome back, and we are on the next lecture, and so this one's going to be a big show. Uh, they're all big shows. Everything takes a long time to explain in these lectures, but so now we're moving into the digital material, and one of the first things that we need to talk about, or kind of one of the last things that we're going to talk about in this series of lectures before we go completely into digital, is we're going to talk about clock generators, and then the next chapter we're going to go into digital logic primarily and work on that. But before we do that, since clock generators are still a little bit analog, we're going to talk about them right now. So a clock generator is a device, a piece of electronics that generates a clock for your digital system. So just like your computer has a clock speed, whether it was megahertz or kilohertz back in the 70s, right? Then it was megahertz in the 80s, and now they're up to terahertz, right? On graphics processors, and your PC's running gigahertz range, right? So so we need something to generate these clock signals, and there are a number of ways to do this. So if you're looking here at the screen, so this little figure right here is basically showing kind of what a clock looks like. So it's just a square wave, right? We've seen these before, square wave. And whatever your digital system is, typically the square wave is going to go from 0 volts up to the voltage of the digital system. So if it's a 5 volt system, or a 3.3 volt, or a 1.8 volt, or 1.2 volt. So in this case, it's a 5 volt system we're showing here. And time is here on the horizontal axis. And this is just showing a clock, and this has got a 50% duty cycle, meaning it's high 50% of the time. And then, of course, one cycle is high, and then low. That makes one cycle, and then it repeats. All right, and that's about it. Now, there's not really a symbol for for clocks, but if you wanted to make one, a lot of people will just use something like a rectangle or a square, and it'll have a ground, it'll have power, it'll have output, and then it'll show a little clock signal on there, and it might have an enable pin to show that it's enabled either high or low to turn the clock on. All right, so that's great. So now the question is, how do we generate these clock signals? All right, so we're going to have to use oscillators, and we haven't really talked about oscillators. Oscillators is like filters. It's a field all in itself, and it's actually pretty complicated if you want to understand the exact detailed math of what's going on with an oscillator. But and we're going to get to it in a minute. But an oscillator, how it works is you have some kind of amplification unit, and then you take the output, and then you feed it back to the input back in phase. So 360 degrees back in phase. So basically the output is feeding back in a positive way. So it's you're getting positive feedback into the system. It'll cause it to oscillate. So now typically with electronics, we don't want them to oscillate, right? But with an oscillator, we do want it to oscillate. So the irony is, a lot of times when you build an analog system, you'll get oscillations if you have high amplification gain stages, right? If you have filters and gain, you'll actually get oscillation. And so then what you want to do is you want to, remove these oscillations by understanding what's causing the oscillation. And what causes this oscillation is you're getting positive feedback. All right. So the amplifier just basically, keeps getting a larger and larger output. That larger output feeds back to the input, and so on and so forth. And then it oscillates. We'll get to it. First, we're just going to kind of run through some of this stuff, and then we'll focus more. All right, so I want you to read this. So this is section 3.11, so clock generators. And there's three main classes of things that you would use here. So you can use a crystal, and with additional caps and inverter to build a clock circuit. So you can build a real simple clock yourself just with a crystal. And everyone has heard of a quartz crystal or clock crystals, and we're going to talk about that in a little bit of detail so you can understand what these things are, why they do what they do. Then there's oscillator ICs, and these oscillator ICs, basically they have a crystal, inverter, capacitors, resistors. So it's basically a packaged version of the crystal oscillator number one here. All right. So this figure right here, this is just a crystal. So inside of here is just a crystal, and it's suspended inside of this package, and then it's wired up to these two leads. The oscillator basically has that crystal inside of it plus the electronics. And then the last way that you might make a a clock is using a timer integrated circuit, a circuit that's specifically designed to create clocks. And one of the most famous ones is the 555 timer, which is probably invented in the 70s, I would think. I'd have to look that up. But anyone that knows anything about electronics has heard of a 555 timer, and that's a real basic clock IC to create time delays and do different things, monostable and astable oscillations. But there are very, very complex clock generator ICs that can generate multiple clock domains for, modern digital systems. We're not going to really look at that. We don't really need it. But they exist. So we're going to look at these three different things: a crystal oscillator, just a basic crystal oscillator. How would you make one of those? An oscillator IC. So these basically, you give them power and they put out a clock. And then let's play with a timer IC, and we'll play with a 555, all right, since it's a very useful and fairly simple IC. So again, let's just kind of go through here and look at some pictures. So here's, this is showing using an oscillator. So this is the oscillator symbol. And you can see they're in these little metal cans like this. And there's two sizes of them. One is it kind of looks like what an 8-pin dip dual inline package would look like. And the other one is like a 16-pin dip. They have the same footprint, but they only have 4 pins, all right? So this one is a 4-pin, but it uses the same footprint as an 8-pin dip would, but it only has 4 pins. One there, one there, one there, one there. And you can see it up here symbolically with the circuit. So we've got our bypass capacitor here, just like we normally do. We've got our V sub CC, and then we got our ground, and then the output just comes from the top here, right there, pin 5, and you just get a clock signal out of it. That is all there is to it. And this typically has amplification or buffering in it, so it can drive a lot of devices. Because remember, the clock is going to drive the clock of the entire system synchronously. So when you build a digital system, I want every single gate, subsystem, you name it, to run off that clock, or a multiple of the clock, or a division of the clock. So they're all based on a clock. So that clock's gonna have a lot of load on it, and that means that it has to have a lot of drive, which means it has to have a lot of current, right? Current drive, right? So anyway, so that's how you would set up one of those. Little circuit right there, a picture of it. And then that's kind of what you get out on the oscilloscope there. Now, this one in particular is showing 3.579445 megahertz. This is color burst. And this is from NTSC television sets, right? The old analog TVs, which some of you are probably too young. You never even had an NTSC TV. You probably only had a modern television, a flat screen TV that has a digital input. And doesn't use NTSC signals. But anyway, if you're a gamer or something, you've got a Nintendo or something like that, or old Atari or whatever, then you're used to NTSC signals and you know what those are. And anyway, this is a color burst, and I'm not going to go into video, but this is the color burst frequency is the frequency that the color is encoded on in TVs. So it's just a very common crystal and a very common oscillator frequency that you'll find, and it's just showing it right here. But now, one thing that we notice is it's not square, right? So why isn't it square? Well, the reason it's not square is, remember, nothing is ideal, right? So ideally it would be a perfect square wave, right? But what are we seeing here? We're seeing capacitive charging and we're seeing capacitive discharging. So that means that the circuit had some capacitance in it, and that capacitance, as it was driving it, was causing charging and discharging. The oscilloscope cables themselves, the probes, can cause this also. So just by looking at the signal, you can cause loading on it, and that's why you have to understand what you're doing with your probes, and also have very high quality probes. All right, so we're going to get into more of this, and we're going to see how bad these signals will look until we fix them up a little bit and clean them up. All right, let's see what else here we have. And yeah, okay, so then here is the 555 timer. And so there are different versions of the 555. It's a very, very famous little IC. It's a little 8-pin IC. And this is just one page from the data sheet. I believe this is probably a Texas Instruments data sheet. And so it's got some different modes of operation. So monostable means when you hit it with a pulse, it puts out another pulse, but no matter the size of the input pulse, the output pulse is always fixed. So basically, if you have a little short pulse or a little long pulse, no matter what, the output pulse is exactly what you want. So say like something's going to make a change and you want a 1-second pulse, you'd use the monostable operation mode. And and then there's the astable, and this is like an oscillator. So this will oscillate and create a square wave of a specific duty cycle. And then there's equations that describe this. All right, and we're going to go into that. We're going to go into all this in detail. And then there's some equations here that describe for the 555. It's basically an RC timing circuit with some comparators, and we're going to look at it. And these equations right here describe the period and the frequency for resistors RA, RB, and capacitor C, and that's right up here, RA, RB, and capacitor C. So you put in those values, you plug in those numbers, and here's what you're going to get, and then here's the duty cycle, okay? All right, and then here's just an example. So that's it. So very short. I want you to read all this. And we are now we're going to go into this in some good detail. All right, so let's scroll back up here kind of to the crystal oscillator and crystal section. All right, so let's start off, and what I want to do is I want to show you some crystal stuff here. So just to give you a feel for this. So, all right, so crystal oscillator, and then this is on Wikipedia under crystal oscillator. So if you just Wikipedia for crystal oscillator, and of course I'll have this exact link inside of the materials for the lectures. But I want you to just kind of scroll through this. This is very, very advanced. It has a lot of material in here. All right, but I just want to bring your attention to a few little things. So first, here's what a crystal oscillator looks like, and this is a bad caption. It's not a crystal oscillator. It's simply a crystal. It's not an oscillator. This is just a crystal. All right. And here's the electronic symbol of it. So it's just a crystal. You could use it in a filter circuit, an amplifier circuit, an oscillator circuit, whatever you want. But it's definitely, this picture is not a crystal oscillator. It's just a crystal. It's a quartz crystal. All right. Now, they have different kinds of packages. This hermetically sealed HC49S, which is a small little package here. All right. And you know, there's the electronic symbol of it. Now, and these will go from, you know, hertz to megahertz and very, very high. And they're all based on the piezoelectric effect, right, which you can read about, the piezoelectric effect. And what the whole idea of the piezoelectric effect, let me kind of go here, is when you apply an electric field to a quartz crystal, it actually causes a mechanical compression or expansion of the crystal lattice, right? And so applying a charge creates a deformation mechanically of the crystal, and if you were to mechanically deform the crystal, you can create a charge separation, or you can create a voltage, right? And then it shows these different modes. So you've got this crystal lattice that quartz is made out of. It's made out of atoms, and these atoms are all in positions in a 3D matrix, a crystal lattice. And then depending on how you move this crystal around, right? So here's shear mode. Remember, shear is like this. You pull two things apart. Longitudinal mode is you stretch and compress. Flexure mode is when you bend. Face shear mode is when you're going like this. And there's many, many, many different kinds of things. So basically, we can apply a voltage to these, or a signal to these crystals, and what's going to happen is they're going to resonate, and there's going to be one frequency or a number of frequencies that they'll resonate at, and this resonation is kind of the frequency that they're tuned to and designed to. Any other frequency will get dampened out very, very quickly. All right, so you can keep reading through here, but what I want you to see is this. So this is the equivalent model of one of these quartz crystals. So this capacitor right here, this represents the capacitance of these plates. So there's actually a quartz crystal, and it's soldered to some metal. Some metal is either deposited on the two faces of the quartz, or however they want to make contact to the quartz. Those metal plates create a capacitor. So that's what the C naught is. All right. Now, the C1, this L1, and this R1, these are abstract. There's really not a capacitance, an inductance, and a resistance. What there really is these things have to do with the stiffness and they have to do with the mechanical properties of the actual piece of quartz. All right, and then each one of these has an analogy mechanically. So if you look at mechanical systems like springs and whatnot, there are analogies to capacitors and inductors and resistors and so forth. So these right here are kind of what these values would be if they were electrical values. So we can model them with electrical values and do the math. And here's some of the math right here. Now, a couple things. When you use these crystals, and let's see here, I'm just going to scroll through here for a second. I want to see if I can find a picture. Yeah. Yeah, here we go. So see this picture right here? This is one of these things opened up, and you can see here's that quartz crystal. It's completely clear, and then here's this deposited metal contact, and there's another one on the other side, and then they go down to these two little posts. And here's another one showing this one, which is more rectangular. So there's actually metal deposited on here, and then that's how you make the contact, because it's crystal. It's like a piece of rock. If you go out, you can find quartz crystal. Go outside and you can find quartz crystal. If you could shear this and cut this and polish it, you could make quartz crystals if you wanted. All right, and they would do what they're supposed to do. All right, so let's go back up here, and so there's a couple different modes of oscillation. All right, and there's series oscillation, there's parallel oscillation, or resonance, parallel resonance, series resonance, and then there's the crystals have a fundamental frequency that they'll oscillate at, and then they'll oscillate at harmonics, or they'll resonate at harmonics, all right, and then also overtones. So either odd or even multiples of whatever their primary resonant frequency is. So the whole point of it is when you buy these things, they're going to have a frequency on it, and that frequency might be 1 megahertz, or it might be 3.57 megahertz, the NTSC signal. Whatever it is, that's kind of its fundamental. Under these circumstances, if you hook it up in this way, it'll oscillate or resonate at this frequency. But you can make it resonate or oscillate at higher frequencies if you like, and even lower frequencies, right? Which can be odd or even multiples of the fundamental frequency. And that's what you don't want to do many times. Many times you want to make sure the thing oscillates at 1 megahertz, but if you set the circuit up wrong, it actually might oscillate at an even or odd multiple of that, which would be very bad, right? Then your system wouldn't work as expected. And then it just talks about temperature effects and those kind of things, all right? And then it's talking about different packaging of these crystals and so forth here, what they look like. So, take a look at that. There's some raw quartz crystals. So, it's really actually quite interesting. All right. And these are also used for sensors. So if you take a quartz crystal and you apply a force to it, a pressure to it, it'll actually generate a voltage, right? Now, if you hold it, it'll stop, but it basically can measure dynamic changes, right? And it can create charge for dynamic changes. All right. And what I wanted to get you to, yeah. So this thing is called crystal cuts. So there's all these different kinds of cuts of crystals. And just like diamonds, you hear how people cut diamonds in different ways. Same thing here. And there's a lot of them. Typically, you're going to hear about an AT cut, an SC cut, and it's pretty much the typical ones you'll see, these AT and these SC cuts. And you can read about them here. There's for different frequency ranges. They have different properties. Some of them special cut is much more accurate, but much more expensive. So typically, we're going to see these AT cut from half a megahertz to 300 megahertz crystals. They're great, whatever, but they're not as accurate as, say, an SC cut. And there's many, many different kinds of cuts. And you can see this table is rather large, right? A lot of different cuts in here, and you can read about them. This is a whole big subject in itself, right? So that is the crystal. So the whole point of the crystal is that it allows us to use it in a circuit as a resonant tank. So remember, if you take a capacitor and you take an inductor, we can create basically a resonance. There's one frequency, all right, that this thing will want to resonate at, and it becomes purely resistive, all right. And there's this thing called the Barkhausen criteria, and the Barkhausen criteria, what that talks about is if you want to make an oscillator, basically you need an amplifier, you need some feedback, and you have to have these different criteria. And I think, yeah, I have it right here for you. So it's called the Barkhausen stability criteria. So what this talks about is how to make something oscillate, all right? And it's a condition that allows you to figure this out. So here's our amplifier, which we've made amplifiers, and we could take the output of our amplifier and we could surely put it back to the input, right? Now, the criterion here for oscillation here, all right, is the loop gain is equal to unity in absolute magnitude, right? And the phase shift around the loop is an integer multiple of 2 pi. So what does that mean? It means that the gain is 1, so the total gain is 1, and the phase shift is a multiple of 2 pi, or 360 degrees. In other words, the input and the output are completely in phase, all right? Then you'll get this oscillation happening, and you'll get sustained oscillation, all right? That's the Barkhausen criteria, Barkhausen criteria. So this is something, if you get an EE degree, you'll hear about this and read about this and do these calculations. But that's kind of what we need. Loop gain equal to 1, maybe a little bit greater, and then we want to have the phase of the feedback back at 0 degrees or 360 or 720, a multiple of 2 pi, a multiple of 360. All right, so that's kind of how things oscillate. Remember, I don't want to really talk about oscillators too much here. All right, so let's go back, and now what we're going to do is we're going to take a look at the crystal oscillator. That's an oscillator, and we're going to look at just taking a crystal and making an oscillator, right? So let's take a look at doing that, all right? So let's go back to our document here. All right, so what we're going to do first is we're going to go onto the bench here, and we're going to build an oscillator. And what we're going to do is first we're going to build an oscillator using, let's see here, what I want to do is I want to build an oscillator super simple using a clock oscillator. So inside of this has got a crystal, it's got an amplifier, some resistors, capacitors, got all those things. So that's got everything in it, and we're going to create an oscillator like that just by using a chip and plugging it in. Oh, and there's one other thing that I want to talk about before we go do that. And okay, why do we use crystals? That's a question, so I didn't answer that. Why do we use crystals? The reason why we use crystals is they have what's called a very high Q. And Q is called the quality factor, and it means different things depending on the context. But what it means is this, is if we were to we can make an oscillator with an inductor and a capacitor. But the inductor and the capacitor, because they're made out of real parts, are very lossy and they're not very accurate. A crystal is different. It has a very, very, very high Q, all right? And so and Q can be defined. Q can be defined as, for example, the inductive reactance over the resistance of the circuit, right? So in an oscillator based on a quartz crystal, it'll have this super high Q. It could be thousands, right? Where the Q of just an inductor and a capacitor is very low. So what that means is that the oscillator will oscillate at one very specific frequency, so it's very selective. So the whole point is that sure, we can make an RC oscillator, right? We can make an LC oscillator using simple parts, but they're very, very inaccurate, and they change over temperature and this and that, and they have very low Q, low quality, because these values have resistance in them, they have capacitance, they have inductance stray. So if you have an inductor, that inductor's got some resistance in it. If you got a capacitor, it's got inductance in it, it's got resistance in it, so they're not ideal components. The crystal is near ideal, and even though it had that model that we showed that had the capacitor in parallel, the resistor, the capacitor, and the inductor, the reactance of the components compared to the inductive reactance is very small. So it's dominated by its inductive reactance, which has to do with the crystal itself. So the point is, the reason why we use crystals is they have extremely high Q, which means they make extremely accurate oscillators. One part in 10 million, one part in 50 million, one part in 100 million, they go off frequency. So that's why we use them, and they handle temperature variation very well, and the document on Wikipedia showed that. All right, so, okay. So anyway, so now what we're going to do is we are going to go over to the bench, and we're going to build some oscillators just based on these pre-made oscillators which have crystals inside of them, right? So let's go over to the bench and let's take a look at doing that. All right, so here we are on the bench, and the first thing I want to show you is what these things look like. So here are some right here, and I've got many of them. And you can see if we just grab one randomly here. So this is one of the larger ones. So this is like a 16-pin or a 14-pin. Let's see. I think it's 14-pin. Yeah. So let me see. 1, 2, 3, 4, 5, 6, 7. Yeah. So basically they're designed so that if you had a 14-pin standard TTL dip chip, it would fit in the exact same footprint of it. But notice there's only four pins on here. Only 4 pins. All right, so that's the full size oscillator. Then the half size oscillator, let's get one here. Here's a half size, And this little one right here, you can see I've got writing on it, and I think this says 25 megahertz of 5.0 volts. All right, so matter of fact, let me zoom in just a little bit here. All right, so that, and then what else we got here? So here's some more here. You can just see these different kinds of packaging. And now the ones that are written on, the reason why they're written on, these are programmable oscillators. So you can go to places like DigiKey and Mouser, et cetera, and you can buy oscillators which are electronic. So inside of here, it's electronic. You can actually program the frequency of it, all right? And then you've got fixed oscillators like this one right here, this blue one, all right? And this is 100 megahertz. That's a 100 megahertz oscillator, 100 megahertz, all right? All right, so, and then again, these are all metal, and the reason why they're metal is because it protects the oscillator so it can't radiate. That's one thing. But if you want to save a little money, you can get these plastic ones. So that's a plastic one right there. So that's a P-dip plastic one. And then, there it is compared to the metal one. It's got the exact same footprint, so it'll fit in the same way, right? But it's plastic, it's cheaper, okay? So, all right, so these are all oscillators, all right? And then we can just basically go through here and pick anything we want. I've got, every frequency you can imagine. I've got hundreds of these, actually, hundreds of these that I use for different things, right? And then I take them out and I put them back, okay? Now, what else? So now what I've done is, now normally I like to build things in front of you, but the reason why I'm not going to do that completely this time is because these oscillator circuits are fairly hard to get working properly and clean, and I just didn't want to waste too much time just messing around with it. So this is the 555 circuit, which we haven't talked about that. This is an actual oscillator based on just crystals, so you can put a crystal in there and this will oscillate, right? But we're not talking about that yet. All we're doing is this. So right now we're on this guy. So basically this is very simple. Basically, you've got power, you got ground, and you got an output, and then you got that bypass capacitor right there. Now, this is the half-size oscillator right here, and this one is what, 10 megahertz? Yeah, 10 megahertz is made by ECS, okay? 10 megahertz, and you see those decimal places there, 10.000, and typically it may have more precision on the value, and then if you look it up, it'll say how many parts per million this is accurate to, and so forth, all right? Now, so that fits in there, and if I were to put this in here, it fits perfectly. Now, but what if I wanted to change it to a, let's say we're going to build an old Pentium computer, and we need a 33.33 megahertz oscillator. So if I put this in here, what I've done is I've kind of already figured out where the pins would go. So here's another ground and another output, right? And I'm not hurting anything by just having those wires there. So now no matter which one you put, both outputs are tied to the same pin, both are grounded, and then I use the power as the reference point. And this is a good trick. So if you design a printed circuit board and you want to put different oscillators in it, you give yourself a little bit more flexibility by supporting either the 8-pin dip package, this one, the 8-pin dip, or this 14-pin dip, all right? And then you can just put either one in there, all right? Okay, so let's go back to this, and we're going to go ahead and hook up the oscilloscope to this, and we're going to see what happens. So, and make sure we put it the right way. Typically there'll be a little dot right there that says that's pin 1, and that is pin 1, so that is the orientation that it goes. Okay, so that looks good. And what I'm going to do here is I'm going to go ahead and turn the power on. All right, and then I'm going to get an oscilloscope lead, and very carefully so I don't mess everything up. There goes all the resistors as usual. Okay, and I'm going to ground it right here. Okay, and then what I'm going to do is I'm going to set the oscilloscope up here a little bit for you, so I'm going to see what's going on. Okay, all right, now we're going to put the lead right here. All right, and now let's go take a look at the oscilloscope. Okay, so we're looking at the oscilloscope now, and we can see the signal. So the first thing that should catch your eye is this does not look like a square wave. So this looks like a triangle wave or a sawtooth wave, right? And you can definitely see the capacitive charging and discharging. And we're also having trouble locking onto it. But the frequency is 10.001 megahertz, so that's pretty good. So the first thing that we're going to do here is we can try and get a better lock on it with the oscilloscope. And I could probably play with that to get that to do that. And if we want to play with this for a long time. All right, but see here, trigger menu, and now I want to leave it like that. All right, and I'm going to stop this so you can just look at it. Okay, so that's what we've got, and we're putting out, 10.001 megahertz. Now, what is happening here? Well, I'll tell you what's really happening. I'm going to turn this back on, and we're just going to lose it a little bit. It's having trouble tracking. What's happening is we're seeing this triangle wave and all this capacitive charging and discharging. The reason why is because we've hooked up the oscilloscope cable, if you can believe that. The probe itself is causing this problem. So what we need is this probe to be a way higher impedance. So come back over here on this camera, and I want you to take a look at something. So, and we've talked about this before. So here's the oscilloscope probe, and see it's got ×1 and ×10. Let's put it on ×10. So this is going to increase the impedance of this probe. It's going to make it less of a load. So we're going to put that on there as ×10. All right. Then we're going to go back to the oscilloscope here, and I'm going to say the probe is ×10. Now we're going to adjust this, and if you take a look, already we've got a better signal here. It's a square wave. All right. And I'm just going to stop it for a second. So you can see again, we've got the same frequency as 10.001 megahertz, and then we've got our square wave, but now we're getting some of this noise right here. So what's happening here is this. When we have these fast changing edges, all right, these fast changing edges are causing basically these overshoots and undershoots are caused by inductance and capacitance. And what we need to do is we want to dampen these things out. So we want to filter these undershoots and overshoots and square this up a little bit. So we can do that with some capacitors or with some inductors or one of each, and clean that up. All right. So that's what we're going to kind of give a try and see if we can do. All right. All right, so the first thing is I've got the signal here now straightened out, and I've got it triggering on it a little bit better. All right, and you can see what's interesting here is that this is changing. So the signal is kind of modulating all over the place, but just here and here, the edges aren't too much, right? So every time the signal changes a teeny tiny bit, and this is a property of oscillators, all right? And if they move back and forth in time a little bit, we call that jitter, all right? So this is kind of what happens with these oscillators. So now what we want to do is we want to get rid of these overshoots and undershoots, all right? So we know that these have, here's this frequency here, which is 10 megahertz, right? 10 megahertz. And if we go look and we say measure, we can see that the peak to peak is this value, the RMS is this, the mean is this, the duty cycle is 50% perfect, so that's all good. So, but the frequency of these little oscillations that are occurring here because of these fast moving edges, and this is why you don't want fast moving edges. So really when you have a clock, you want the clock to be more of a trapezoid rather than a perfect square, because these edges will cause this. Let's see if we can dampen those out. So let's come back to the bench here, and so let's see, why not try, let's put a capacitor and let's try and slow this down. We'll put a capacitor to ground. And now we could do some calculations, but now what I want to start doing is I want you to get comfortable with your intuition. All right, so let's just start off big. So let's start off and we'll put a 0.1 microfarad capacitor, 0.1 microfarad, all right? So that's big, that's pretty big, all right? And let's just see what happens. Let's see if this helps us or hurts us. All right, so we're gonna put it right here. All right, now I want you to look at the signal. We've killed the signal. All right, so we've killed the signal. Now remember, a square wave is really an infinite sum of sine waves, right? And so what's happened now is we filtered just about everything out, and we're just barely getting these edges. All right, so let's go back. Let's get rid of that. All right, let's put another capacitor. Let's put something small. Let's put 47 picofarads. Okay, very small. All right, we're trying to see, does this help? Does this help? So I'm putting it here on the output. So take a look what I'm doing here, just right there. All right, now look at our signal. So that's not bad. So I'm going to get rid of, okay, so that's not bad. Let's try a 22 picofarad, 22 picofarad, okay, 22 picofarad, all right, and I put it in there. No help there. So the 47 seems to help a little bit. Okay, so that's one thing we can do here. All right, so that seems to really straighten that out. So that kind of makes me happy now. But let's try a different thing. What else can we try here? Well, can we filter this with an inductor? So remember these things, these ferrite beads? So here's a ferrite bead, right? And so we're just going to put a ferrite bead right in series with the output. So right in series, and let's see if we get a better signal, because it's going to, remember, it has high impedance. So the ferrite bead, its impedance goes up, right? What is it? 2 pi FL, right? 2 pi FL goes up proportional to the frequency. So the higher the frequency, the higher the impedance. So we're trying to get rid of some of these really high frequency little pieces of noise here. So we put that, oh, look at that. Now look at our oscilloscope. That's beautiful, right? So that's good. So now let's get rid of the capacitor, all right? And so if we put the capacitor back in, we kind of get rid of a little bit of the overshoot and undershoot, and then we have, basically a nice square wave here. So now we could go like this, and kind of take a look at it, right, at different scales, all right? And there we go, all right? So now let's go back to what it was before. I'm going to get rid of the capacitor. Now the capacitor is gone, and now I'm going to get rid of the inductor, and so you can see where it is. So we definitely like this small ferrite bead, all right, and we definitely like this small capacitor, all right. And so what's really happening there is the 10 megahertz is if we were to look at this as an extremely high quality oscilloscope and probe, the signal would probably look okay. But what's happening is the probe itself is acting as an impedance, so we're dampening that out as well. But again, this is kind of what you need to do. So if you're dealing with these higher frequencies, you have to figure out how to get the signal clean. So now let's go ahead and let's just flip this for a different frequency. I'm just going to pop that right out. I'm just going to hot swap it. All right, I'm going to go over here and we're going to look. Let's see what else we have here. Anything fun? Let's see. How about let's do what was that? That was 10 megahertz. Let's go faster. Let's go 100 megahertz. That's going to push the oscilloscope. Let's go 33 megahertz. So I'm going to put a 33 megahertz in right here. Boom. So there goes my 33 megahertz. Now look at my oscilloscope now. So now look what we've got here. So this is getting very triangular. Let's take out the capacitor. So now look, taking out the capacitor, that helps us right there. We're not getting any overshoot or undershoot. What about if we take the inductor away? So that's definitely ugly. So the inductor definitely helps us, or this ferrite bead definitely helps us. And that gives us something that is more like a square wave, right? So that looks good. All right. So that's more reasonable. And then, and if we look at the frequency, what's the frequency sitting here at as it samples? 33.3327, and it says 33.333. All right, so that's very accurate, and we're getting 33.33 megahertz, so that's good. Okay, now we'll do one more. We'll do one more, and let's see if we can do 100 megahertz. I'm looking for 100 megahertz. Here's one. Here's 100 megahertz. So here's 100 megahertz for fun. Okay, put that in there carefully. There's our 100 megahertz. And this is not working. So this particular 100 megahertz, I may need an enable on another pin. Let me try another 100 megahertz. Here's one here. And I didn't try all these. I'm just grabbing them randomly. So remember how I said you may need an enable to get the oscillator to work. There we go. So this is 100 megahertz. And so the first thing is I'm going to take away the inductor. It's not really even having an effect here. All right. And now this is kind of what we're getting out of here. So we're getting 100.002 megahertz. And the bottom line is this is such a high frequency. not, by the time it starts rising, it's got to start falling, right? There's just not enough time, so you're going to get very little of a square wave out of it. It's going to look like this. It's going to actually look like this triangle wave. Now, one thing you notice is, look, it's going a little bit negative here, right? So it's going a little bit negative there, all right? So we're actually getting some negative movement below zero, right? Now, if I put that inductor on there, notice I get rid of it. I get rid of that. All right, so that's good. And remember, the cable itself is having a big effect here also, and we could compute that if we wanted to get into all that, but we're not going to. So just realize the probe itself to the oscilloscope is affecting the measurement. So make sure you have really good probes. You're going to start messing around with high frequencies. All right, so that's 100 megahertz. That works good. And so that's all there is to using crystal-based oscillators. Now the next thing that we want to try here is just hooking up a crystal and make an oscillator circuit ourselves. So we're going to kind of make what's inside of there, all right? So that's the next thing that we want to do. So so why don't we stop right here and let's go back and we'll start again on the blackboard and we'll talk about how to make something with a circuit, okay? All right, I'll see you then. All right, welcome back. And so now we're continuing with our discussion of oscillators. And we already did the oscillator that was in an integrated circuit. So the pre-made oscillator that kind of had the crystal and the analog electronics built inside of the can. Now what we're going to do is we're going to actually build an oscillator from a crystal and some discrete components. So now if we recall the Barkhausen criteria, right, if we can take a look at that, if we can find that again. So the Barkhausen criteria is we need an amplifier and then we need to take some of that feedback and put it back in 360 degrees, is got to be the phase, which means 0, right, or a multiple of that. And we want the gain to be about 1, all right, a little bit over 1 in reality is kind of the sweet spot. All right, so what we're going to do is we're going to use that to build an oscillator. Now, if you look up, if I can find this, yeah. So, for example, if you just Google and say, inverter-based oscillator, you can find many, many references for creating an oscillator based on an inverter. So a standard TTL or CMOS inverter will do this, and typically the CMOS inverters are used, which is the 74HC04. So here's a document, for example, from TI, which is this is a good document to read, and I'll put it in the the materials also specifically. But it's SZZA043. If you just Google for that, the use of the CMOS unbuffered inverter in oscillator circuits. So the whole point of it is this, and this circuit is one you'll see over and over again. And, and there's that amplifier with feedback, right? And there's the model of a crystal, right? And talking about all that, the equivalent circuit, and then figuring out how to make it oscillate. That's what all this is about. So you could read this and kind of get that detailed analog information again. But here's what we need to build. So we've got C1, we got C2, we've got our crystal, we've got an inverter, all right? And then we've got this feedback resistor here, which takes the output back to the input. And then so the whole point is this. The inverter gives us 180 degrees of phase, right? It takes the input and inverts it 180 degrees, right? So if you put in a small input, you'll get a small output, and but it'll be inverted, all right? That's the whole point of an inverter. So we kind of take advantage of that, but we need another 180 degrees of phase shift. That's what the capacitors are for. All right, and the crystal itself also. So when you add all this together, you end up getting 360 degrees of phase shift, and then we get our feedback through this feedback resistor, and then also we add another resistor right here typically, which is to control how much power goes into this network here so we don't saturate it. So there's a lot of times you'll see another resistor here, and I use that version of it myself. So you can read through all of this. All right, and this is, again, very complicated. Just this document on how to make these oscillators is, I don't know, what, 20 pages, and it's 20 hard pages. This is not easy stuff. But at the end of the day, all we really need to know is use a CMOS inverter, put our crystal in there. We need to figure out these capacitors somehow, and here's where all this these calculations come, right? But someone can go through this and kind of do it for you and come up with these values, right? So, and the oscillator type is called a Pierce oscillator. There's different kinds of oscillators, many times named after the people who invented them a long time ago. There's Pierce, there's Colpitts, and many others. But this is a Pierce oscillator configuration. So what I've done is I've come over here into a Proteus and created a little circuit. This won't work inside of Proteus as is. I'm sure I could make it work, but I don't really care. I just wanted something to draw this for you so you could see it. So, so again, this is a Crash Course CE inverter Xtal oscillator 01, and that'll be with the files for the lecture. But you can see that we've mimicked the circuit here. So we go back, we've got our inverter, and there should be a dot on that also, right, to show that it's an inverter, because as drawn, that's just amplification. Crystal, 2 capacitors, and a feedback. So we got our crystal, we got our 2 capacitors, and here's our feedback resistor. And then this other resistor right here is something that I add and many others do, just to control the amount of power that's going into this circuit right here. All right, now, then what I've done is I've kind of built up this little table here, which is through calculation and experimentation and just picking some common values you can find off the shelf for these different capacitors. So if you're going to make a 1 megahertz oscillator, use a 1 megahertz crystal here. These capacitors C1 and C2, make them 47 puff, picofarad. All right, and then R1 will be 10K. That's that R1. If you're going to make a 5 megahertz, use 33 puff, and so on and so forth. And then this feedback resistor, try 100K. If it doesn't work, try a meg, all right, for the feedback resistor. We just need to get some feedback, but not too much. So 100K to 1 meg. So this table gets you up to like 33 megahertz, and you can project it from here, right, if you want. Now, so here's our oscillator. Crystal-based oscillator, but what's this? What's the business? What's going on here? Well, this circuit right here has got all kinds of impedance connected to it, complex impedance, this and that, feedback. So we want to take that signal and now buffer it. So we put it into yet another inverter. And then this inverts the signal again, but we don't care, it's just a clock. And then this buffers it and amplifies it. Now, what if we wanted to have a lot of drive? Well, we could do that. What we could do is, see, this is, say, a 74HC04, 74HC04. Let's go take a look. 74HC04. So if I type in 74HC04, that is a CMOS hex inverter, meaning there's 6 of them per package. Go here and pick somebody, pick the Texas Instruments version. All right, and then here's the page, and then I think I've already got it open here someplace. Let's see, 74HC04 inverter, yeah. So here it is right here, and so there's 7.4 and 5.4. And we'll scroll down here a little bit. You can see the pinout of it. You can see the inputs and the outputs. So the bottom line is there's 6 of these. Let me see, is there a drawing in here? The drawing helps a little bit more so you can see where they are. And again, I'm sorry for scrolling. I know this hurts some people's eyes. No, there's no drawing. But the way that this looks is like this. Let me go back to the pinout. So there's an inverter here, 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 an inverter here. It's in, out, in, out, in, out. So A is in and Y is out. So that's how these operate. So there's basically 3 here and 3 here. All right. So going back to our circuit schematic, we've got this one right here. Now, what's the current drive capability of this? All right, so if we go, let's go back to the page here. So the current drive, the output of this is output high and low is 5.2 milliamperes. That's it. That's not a whole lot of current, right? So what we could do is we could do this. So we could go back here and we could grab this guy and we could say, give us another inverter from the package. So this is all U1. So this is ICU1, but there's there's A, B, C, D, E, and F, right? Because there's 6 of them. So here's C. Now what I could do is I could just go like this. See, I just put it in parallel, right? And I could do it again. Let's move this. Here we go. So now what I've done is I've said to myself here, I want to have a lot of current drive. I'm using this one IC for an oscillator, so I might as well take all the other inverters and I can tie them all together in parallel. And now we'll get 15 milliamps of drive out of this, right? And what is there? There's 2 more, right? There's 2 more of these, okay? So let's undo that, but we could have done that, right? if we wanted more drive. All right. So this is all we've got to build. We just got to build this right here. So we're going to take one inverter, the first one, which is on pin 1 and pin 2. All right, and then we're going to have this resistor here, we're going to have our crystal here, we're going to have our 2 capacitors here, and our feedback resistor here. Then we're going to take the output of that first inverter, now it should be oscillating, and then we're going to take that and we're going to invert it again. We don't really care because we're creating a clock, but what we're really trying to do is buffer it. All right, now if we go to the data sheet for the TTL chip here, or the CMOS chip, we see that power is at pin 14 and ground is at pin 7. This is typical with 14 pin, 8 pin, 16 pin, etc. Usually power is on the corners. So, but check it. You never know. Sometimes it might be in the middle. So we need to put V sub CC here. We're going to use a 5-volt system, and we're going to put ground right here, and then we're just going to wire this thing up. So we're going to wire this up to mimic this circuit. All right. So let's go over to the bench and let's do it. All right, so here we are, we've got our circuit, and I've actually got power on here, all right? So let me turn the power off for a second. And we had our probe on our oscillator, which is our CAN pre-made oscillator. Now we've built this, which is basically what's inside here. So let me zoom in a little bit so you can see this a little bit better. And we're going to probably go a little bit beyond what the camera can focus. Let me see if I can get it to cooperate with us. It may not be able to focus at that distance. Let me back it off just a little bit. All right. There we go. All right, so we've got our 74 HC04 hex inverter package right there. We've got our ground here. We've got our power V sub CC going up to the top pin, which is 14. Pin 7, of course, is this ground. Notice I have my 0.1 microfarad bypass capacitor there for noise filtering. And also, this could be 0.1 or 0.01. Both are fine, but you need to have it on every one of these little ICs as a minimum. All right, here are 2 capacitors. These are each 22 picofarad. Now, when you're doing oscillator circuits, typically I'd make these completely flat and super neat, but again, I don't want to spend forever making these circuits. But even these little leads on here are more inductance, and we want to get rid of that. So we'd want to shorten all this up, but this is fine, it works. So these are 22 picofarad each, all right? They've got it on there, and you can test the values if there's nothing marked on there with your meter. All right, and then here is our 100K. This is our feedback resistor. So this is going from the output to the input. So we've got pin 1 and pin 2. So pin 1 and pin 2 make one single inverter. And then pin 1 is the input, pin 2 is the output. So pin 1 is input, pin 2 is output. And so now we want a feedback. That's what that 100K. So that's what that brown, black, yellow. So I could put a brown, black, green, which is 1 meg if I wanted, but the 100K works good. And then I've got a 1K. That's our resistor, which I'm calling, I believe, R1 in the circuit. Yeah, so R1 in the circuit, and that's our, reduces the amount of power that's going into the network, and it also isolates the inverter from the impedance, complex impedance of these 2 capacitors. So that helps. All right, and then we've just got our crystal. That's it. Just a piece of crystal right there. That's it. And so when I turn this thing on, it should start to oscillate. And then what happens is this other yellow wire takes the output from pin 2 and puts it into pin 3. And then here on pin 4, that purple wire, I get the output. So I get it inverted again and buffered. And then it's right here. Okay. So let's go ahead and let's hook up our oscilloscope probe. And I think this is still on 10 times. Yeah, so it's on 10 times. Let's leave it there so we don't put a huge impedance on it, because that seems to work better. And I'm going to move the ground here a little bit. All right, and always be careful. Things will get pulled up and shorted potentially, so you want to be really careful when you're doing things like this. All right, so get that in there. Good, and I'm going to zoom back a little bit here so you can kind of see the red LED. You can't really see anything because this is going to happen at 10 megahertz, right? Okay, so let's go ahead and turn this on. All right, so I've turned it on. I want you to take a look at the oscilloscope here. And sure enough, the oscilloscope is showing the signal. And so that looks good. And we've got 10.0058 megahertz. Now, one interesting thing here is, now remember the crystal itself has a very, very high Q, very high quality. All right, so it means it resonates at a very specific frequency or a multiple harmonic or overtone of that. But when we make this feedback network, what we're doing is we're creating kind of a filter here, and we can shift the frequency slightly by playing with some of these values. So see, right now we've got 22 microfarad capacitors here, and we're getting 10.0058 megahertz out of here. Now, do we believe it? Maybe, right? If we had three different meters, three different oscilloscopes, and we had a $10,000 or $90,000 O-scope from Agile or from HP or Textronics or something, I'd believe it a lot more. But with this one, 10.0058, but we're just going to pretend that it's correct for now. Let's see, if we change these values right here. So right now, my little table, if you go look at the little table, so back here, we're looking at this table, and it says at 10 megahertz, 22 puff, and about 470 ohm here, 470 ohm. And I've got a 1K ohm, right? So I made it a little bit bigger. But the point is that 22 puff, and this is just a suggestion. So let's make it a little bit less. Let's see what happens, all right? Okay, so what we're going to do in real time, and we can't hurt anything, so this is okay. I'm going to get a couple more 22 picofarad or 22 puff capacitors. I'm looking for them, all right, and I'm just going to put them in parallel. So remember, if we put the capacitors in parallel, right, it's going to increase the capacitance. It's going to increase the capacitance. All right, so I'm going to put them in parallel, and we're going to see which way that this goes. All right, so we were at, so hold on here, we're at 10.0058 megahertz. So here we go, I'm putting one in parallel with this one. So I'm getting a little bit more capacitance there. And where's our other 22? All right, and I'm going to put this one in parallel. All right, again, we're increasing capacitance. Capacitors add in parallel. So we got 10.0038. So it looks like if we made that capacitance a little bit bigger, we could probably get this thing a little bit more accurate, right? So maybe we pull these out. Now watch what happens. It's going to stop oscillating, or it's just going to go crazy. Right, so now whatever, so what's happening is basically it's gone up to 100 megahertz. It's gone to you know, an overtone or a multiple here based on just what the stray capacitance is. All right, so it's not doing what it's supposed to do, but that's exactly what it should do, right? Which is kind of interesting. So without these capacitors, this thing just runs wild, right? It's like oscillators running wild. Okay, oscillators gone wild. All right, I'm looking for a 47 puff. I've got one. All right, so I've got two of them. So let's put the 47 in there, and we'll put another 47 because 22 and 22 is 44. But we've got a lot of lead inductance here too, which is having an effect as well. All right, so now I put the 47s in there, and look, we're at 10.0037 megahertz. We're a little bit closer to what we're supposed to be of 10.00 megahertz, all right? So that's good. Now, so now let's try something. So I've got these different crystals, and just to show you how many of these I have, so I mean, these are all crystals, you know, probably 100 of them here of all kinds of different frequencies, right? But I just pulled out a few here. So let's go ahead and let's grab something else here. Let's grab a 4 megahertz. So I'm just going to hot swap this out and pull it out. All right, take a look at the oscilloscope. It's going crazy. All right, and now I'm going to put it back in and watch it lock in. So it's at 3.99979. Now this value here, is large. So can we, if we make it smaller, can we get that closer to 4 megahertz? Right? It's very close right now. But let's go ahead and let's put the 22s back. All right, let's put the 22s back. Put in the 22s. There's 122 right there. Here's our other 22. All right. And so see now, so we went down, right? And we went in the correct direction, but we went too far. All right, so now we've got 4.0028, but it's only supposed to be accurate to 4.00, so that's actually good. So we'll just leave that. But the whole point is these capacitors will make a difference. So you'll see an Arduino design or something like that, and it'll say, here's the crystal, and put 18 puff or 22 puff or whatever. And if you put those, it'll work, and surely it'll work. But if you play with it just a little bit, you can get it more accurate if you care that much. All right, now we've got this noise stuff going on here. We've got this this oscillation at high and low, right? So we've got this kind of ringing occurring here. So can we get rid of this again? All right, so we're back to this. So let's go back to the board here. And let's go ahead and let's put a capacitor. Let's put a capacitor right at the output. And let's just start off with a 47 picofarad. All right, 47 picofarad. And I'm going to put it right here. This is just a wire going here, right? So I'm just putting it right there at the output, just a wire. I'm putting 47. Now, look how nice that looks. Let me pull it out. All right. And see this down, this undershoot right here, that ringing down there. Don't like that. And I'm going to put that 47 back. All right, and we just add a little bit of capacitance, just 47 puff, and things look a lot better. Now, can we also add an inductor here and get rid of a little bit more of it? So I'm just going to move this probe right over here. No harm done. I'm just going to put an inductor, a ferrite bead, and we're going to see if we can get that a little bit cleaner. All right, so here we go. You should see nothing on the oscilloscope right now because I've basically disconnected it. All right, there we go. All right, now take a look at that. That's nice. All right, so that's pretty nice. And let me show you. So that's with the ferrite bead and capacitor, and just the capacitor. See that little bit of ringing right there, and we put in the ferrite bead, and that cleans it all up. Okay, so we'll just leave that for now. All right, and again, looking here, we just kind of play with this a little bit. You kind of do this, kind of see what it looks like, and so forth. Right, just kind of play with it, get a feel for it. Very nice. All right, now let's put back our 10 megahertz, and let's see if that still looks good. Right, because we're changing frequencies here. All right, so now with our 10 megahertz, see, we're kind of getting this happening right here. So if I pull out the 47, all right, we're still, that's worse, right? We're getting those little tiny peaks and valleys. So the 47 looks like it's helping us, right? So we're going to keep that. Now, what about the inductor? Let's see if we get rid of the inductor. Yeah, see, we're getting those larger undershoots there. We're getting a little bit more square. So I like that. So I'm going to leave it like that. Okay, so now we've got, there's our 10 megahertz coming from our custom-made oscillator circuit. Here's an oscillator circuit that's just off the shelf. Now let's put in its 10 megahertz. So we're getting 10.0057 or 58 there. We'll undo that, and now we put this one in, and this one's at 10.0001. All right. So again, you know, use our own, and look at the oscilloscope there. Or we use the off-the-shelf one. All right, so they both work, and you know, and that's pretty cool. So if you're in a pinch and you don't have an oscillator, and these are okay, this is another thing. These are not cheap. These are actually pretty expensive. If you go onto DigiKey and you start looking for these things are a couple bucks a piece. They're extremely expensive actually. Because of the metal and this and that and so forth, they're not cheap. So that's why a lot of people, they'll just use an oscillator, a discrete oscillator from a crystal, a couple capacitors, resistors, and a little 10-cent inverter. That ends up being cheaper than putting this in. But this is going to be a little bit more accurate, right? So it's up to you what you want to do. So me, if I'm building something, right, if I'm building a microcontroller-based computer, I'll use a crystal because the microcontroller's got a built-in inverter and so forth. All you got to do is add a crystal and a couple capacitors, and it'll oscillate and it'll be pretty good. And you just get a good crystal, right? If I'm building a circuit that doesn't have a microcontroller and I need a very accurate clock, I'm definitely not going to use this discrete. I'm going to use one of these off the shelf. And of course, they have these in surface mount and as small as you want. These are just so you can handle it and do this prototyping. This is old school, old school, old school, old school. All this stuff is surface mount, of course, now, since the 90s, you know. Okay, let's do one last one. We got both of these at 10 megahertz. Let's switch them up both to NTSC color burst. All right, which is 3.579545. There we go. Got one right here. All right, there's that one. And then let's see if we can find a crystal that's a color burst. There's one right there. All right, and I'm going to pop that out. I'm going to put this in. All right, so now looking at our oscilloscope. All right, so right now we're looking at the oscillator, the off-the-shelf oscillator. We're getting 3.5796, 3.5796. All right, and then we're going to go look at our homemade one, and we're getting 3.5797. All right, and that's a nice looking signal right there. And we look at the off-the-shelf one, and we got a little bit of these happening here, these undershoots and overshoots, right? Of course, we could adjust that, right? We could clean that up too. All right, so that's it. So that's the clock signal. So that's how we generate clock signals with discrete crystals or off-the-shelf crystal oscillators. But remember, the crystal is inside of here usually, and then along with all these electronics. Unless it's programmable, then it uses a different kind of technique. It uses a high-frequency oscillator and then frequency division or a phase lock loop, some other techniques to generate the desired programmed frequency. But to typically, these things basically have all this stuff inside of here. And then we've just got one inverter for buffering and amplification. We've got all these other inverters here. There's, what, 1, 2, 3, 4 other inverters. We could put them all in parallel, and this one purple wire would represent 4 or 5 times the amount of current, or 25 milliamps high and low we could get out of that. So if we wanted to make this a really good driver chip, bam, we would put those all in parallel, okay? Okay, so I think that's good. So let's go back to the Blackboard, and so let's talk about the 555 timer. So here's just a little preview. That's the 555 timer. I had to build it up to start this thing off and make sure it worked good, because I don't want to waste too much time putting it together for you. But let's go and let's do some drawing and do some design on there, and then we're going to actually work through this circuit and see what this thing's doing, all right? So I'll see you back on the computer. All right, welcome back, and we are on the next lecture. We're continuing with the discussion of oscillators. So we just got finished with the bench work doing the crystal oscillator and then the standalone oscillator, and so we're all done with that. So now what we're going to do is we're going to come back and talk about the 555 timer. And remember, this is just one of thousands of different timing ICs. There are countless timing ICs. I don't know if there are thousands, but there are at least hundreds of them if you were to search on different distributor websites and manufacturers. But the 555 is an old standard that everyone knows about, and it's great to start off with because it's very reliable and fairly easy to understand. So on the screen here, you see one page of a data sheet. I believe this is probably a TI data sheet. Anyway, now the 555 timer comes usually in an 8-pin DIP package. It used to. Now there are surface mount versions of it. There are dual timer versions of it. And there's also a CMOS version of it that'll go faster than the standard TTL version. All right, so anyway, we had a couple different modes of operation. And one is monostable, which just allows you to kind of do single shot or to have a pulse and then to output another pulse that's a stretched version of it or a short version of it. All right. Another mode of operation is astable operation, and that's the one that we're interested in, which is just an oscillator. All right, and we can control the frequency and the duty cycle. And the basic circuit is the one that you see here. Based on the 8-pin version and the LM555 version of the timer. The pinouts are always the same. I'm not going to say always. I'm sure someone's got a variant of it, but usually the 8-pin version, the pins are always the same. Trigger, output, control voltage, threshold, and discharge. And we're going to look at the data sheet in just a second here. So the resistors in the circuit are typically called RA, RB, and they're usually in these positions. RA is from the power rail to pin 7, then RB goes from pin 7 to pin 8, which is really this discharge and threshold, and then the capacitor goes from pin 7 to pin 6, and then the capacitor goes from pin 6 down to ground. Then there's another capacitor here, which you'll see sometimes on the control voltage. The control voltage is used to modulate the signal. Typically, we don't use this feature in most cases, so you can just put it to a 0.01 microfarad to ground, and that'll be fine. All right, so there were these equations, which basically I've just copied these out of the data sheet, and these are pretty standard to figure out what the period is and the frequency is based on the two resistors and capacitor, and then what the duty cycle is in a percentage. And based on these equations, you basically just plug the values in, and the thing will oscillate, and it'll do what it's supposed to do. All right, now, what I'd like to do is look at the data sheet for this. So if we type in LM555, we'll get a bunch of different components. And as a matter of fact, let's go take a look here. So this was an LM555 search. Let me just do it again. So LM555, and I'm using DigiKey here, obviously. And integrated circuits will go here. All right, and then you can see there's a couple of vendors here, Texas Instruments and Fairchild. There's more manufacturers, but many of them don't use the LM prefix, so that's why we're only finding these two. So we could, click any of these links and see the IC, but you notice there's the surface mount. These are small outline ICs, and then here's the DIP package. So those are the two common packages, and if you go to other vendors, you can surely find other variations of it that are much smaller. So here's the data sheet for the LM. Now actually this is the LMC, so let's go back here and we'll open up this data sheet here. All right. And so we just got as a matter of fact, let's not get a Fairchild. Let's try and get a Texas Instruments version of this. So let me back up. And let's see, a Texas Instrument, Fairchild. Here's a TI version, so right here. All right, LM555. All right, let me zoom into this. The reason I like this is because it has a little bit more information. So the first thing you see here is it comes in these three packages from this vendor, SOIC, PDIP, and VSSOP, which is really, really small, 3 by 3 millimeter. And then it shows the actual circuit in here, right? So if you wanted to build it, you could do so if you wanted to. And we know enough to actually go through and figure out this whole circuit, right? Here, Darlington pair. These are all transistors. There are current mirrors in here, emitter followers, just all kinds of stuff. So we could figure that out if we really wanted to. But what I want to bring your attention to is this kind of block diagram. And the block diagram is kind of showing what is really going on here. So there's this output, there's a flip-flop, there's a comparator, there's another comparator, and then there's this transistor right here, and then there's some resistors inside of here. So the whole idea of this thing is it's really an RC circuit, right? There's a resistor and a capacitor, it's charging up, and as this thing charges up, it gets to a certain point, and this comparator and this threshold are used to determine that, and then the capacitor triggers something, and then flip-flop flips, and then the circuit resets it by discharging the capacitor. All right, so basically it's an electronic circuit that as the thing charges up, it's monitoring this, and there's like this 1/3 V sub cc and 2/3 V sub cc levels if you read through how the thing works. And as it's going through here, it's tripping these thresholds, and these comparators are firing off. And a comparator is an analog device that it basically has two inputs, and if one input is greater than the other input, then it turns on. If it's less, then it turns off. All right, and so anyway, it's basically an electronic switch that monitors the charging of a capacitor, and once this capacitor charges up, then it electronically discharges it. It connects it back to ground and discharges it. All right, so that's what this is all about. So you could do worse things than read through this, and I'm sure you could Google or you could find a YouTube video of how someone that goes through the exact operation of the circuit. But we don't really care. What we're really interested in here is let's get down to the examples here. And then here's another nice block diagram. All right. And this is an interesting little note. So for timing from microseconds to hours. So you can accurately do microseconds to hours. Now, how accurate is up to the RC circuit and so forth. But the point is, that's pretty good. So microseconds to hours, that's many orders of magnitude of operation. So that's pretty cool. All right. And that's why people use it. It's pretty simple. All right. And then here's that monostable operation, which basically you kind of have top trace is the input, right? And this is triggering it. And then what's happening is this middle trace is the output. And in this case, no matter what size you use for an input pulse, the output pulse will always be this size. So basically, say you had a pulse that varied a lot. Maybe it was something mechanical, right? And you wanted an output pulse that was exactly, in this case, what is it? The time is 0.1 milliseconds per division. So you wanted exactly 0.1 milliseconds, right? So, or 100 microseconds. Then you could use this monostable version of it. So it basically monitors these input pulses, and no matter how they vary, you always get this 0.1 millisecond or 100 microsecond pulse out, right? And then the bottom trace is showing that capacitor charging. So it charges and then discharge, charge, discharge, all right? And then the other version is the astable operation. And here's the circuit right here. All right, and there's that, this mode of operation, the capacitor charges and discharges between 1/3 and 2/3 V sub Cc. So as it's charging, it hits 1/3 and then 2/3 discharges. So that's kind of where those thresholds and triggers are set with these different resistors in this configuration here. All right, and then one thing to note is here the output pin is on pin 3, and you can either put the output here, and then you can put a load here to ground. So that means it can source current, right? So it can source current, or you can use the output and then tie it through a resistor up to V sub Cc so it can sink current. And this is very important. And depending on the kind of output this is, right, you could source or sink current. If you can only do one of them, you got to be very careful, but it can source or sink current, which is really nice, all right? And then you can go up in the data sheet. So let's take a quick look here. This is worth it. So right here, so see this output to output voltage drop. So iSync is 10 milliamps, iSync 50 milliamps, iSync 100 milliamps, 200 milliamps. So this is saying, you know, what's happening if you had different V sub Cc levels. Here is 15 volts. Here, if you've got 5 volts, then you're basically going to be able to put out 8 milliamps nominally, or 5 milliamps in this case right here, which is, this is having to do with the voltage drop low. So this is when you're getting a voltage droop on the output. But the point is, this is how much it can sink, all right? And you can just look through here and kind of find various different pieces of information, electrical characteristics. It's fairly limited on this IC. All right, now this right here, rise time of output and fall time of output. Now, these are propagation delays to make it for the output to rise and to fall. They're 100 nanoseconds in both directions of the waveform going up and going down. So that means no matter what, the absolute fastest this thing can run is 200 nanoseconds. 200 nanoseconds. And if I invert that, that'll give me the frequency. And that's 5 megahertz. So basically, you can't get any faster than 5 megahertz, all right? So 5 megahertz is as fast as this thing is going, this particular chip right here. So that's it. And so that's kind of gives us a top speed there, all right? Okay, so let's go back down to the circuit here for the astable operation. Okay, and let's look at the equations that govern this. So here they are here, and this is inside the book. These are copied basically right out of here when I wrote that. So the charge time, discharge time, the total period is this, the frequency is this, and the duty cycle is this, all right? So this is all you really need to know. So let's go ahead and let's design a circuit based on this astable mode of operation, all right? So we're going to base it on this right here. So what I'm going to do is I'm just going to pop this over here, move it out of our way for a bit. All right, and then I'm going to copy this circuit down and then add a couple things to it, all right? So let's do this. All right, so the first thing is pin 4, and let's see, what color here? Why don't we use something that we'll be able to see a little bit better? Okay, so pin 4 goes to pin 8. Okay, so that's one thing. All right, pin 4 goes to pin 8, and pin 8 here is V sub Cc. So this is V sub Cc, and we're going to say that that's going to be 5 volts. All right, so far so good. Then pin 2 goes to pin 6 always in this mode. So I'm going to draw it like this, and when you're drawing these kind of schematics, go like that, and you can kind of hop over a trace. All right, and that way it doesn't it doesn't look like it shorts, so you can be careful there. All right, so that's good. And of course this does connect right there. Okay, so we need that right there. And then here's ground, so we're just going to put that right to ground. There's ground. Now on this V sub Cc also, what I'm going to do is I want to just make it clear, I'm going to run a line out here, and this is going to go to a capacitor, and this is going to go to ground. This is our bypass capacitor, and this is going to just be 0.1 microfarad, 0.01 microfarad would do as well. Either of these, that would be fine. Just a bypass capacitor to keep the power clean on here and keep the noise in and out of the IC here. All right, so what else do we have? Let's see. Looking at it is we got the output there, we got pin 7, we got pin 8, oh, and we've got pin 5, and this is going to go, you don't have to do this, but I do it because I don't like it just hanging there. This goes to a capacitor. This is the control voltage. So this is output, trigger, reset, V sub CC, discharge, threshold, control voltage. This is if you want. This is for an advanced function if you want to modulate the signal. We're not going to do that. So I'm just going to set this to 0.01 microfarad. Just leave it like that. Monolithic capacitor. Okay, so now what we want here is we want to set up the resistors here that we're going to make work here. So now typically there's two resistors. Right here is one, all right, and it would go like this, and then the other one goes here. Excuse me, it goes like this. And that's why I have this in front of me. I've built this a million times, but I still can't, I don't have it memorized. I don't know why. All right, so this first one is RA, and then this one is RB. All right, so that's the circuit that we're making, RA and RB. And then there's another capacitor, and it goes right here to ground, like that. All right, and then this is C. All right, now we can set these to anything we want, RA and RB, and we can set C to anything we want as well. When we do that, then we're going to have that equation we have to deal with, which is this equation right here, a formula. And this formula right here says for RA and RB and C, here's what the period is, or the frequency, and here's what the duty cycle is. All right, so there's basically three dimensions here, right? So let's just set one of these to something. So we'll set this at 0.01 microfarad, okay? So we're going to have that at 0.01 microfarad. And then RA and RB can be whatever we want them to be. Now, what I want to do is I want to use a potentiometer here. All right, so we're going to use a potentiometer for RA and RB, and then that'll allow us to do two things. We'll be able to adjust the frequency, which is a function of both RA and RB, and then we'll be able to adjust the duty cycle as well. All right, and so that's what we're going to do here. Now, if you remember a potentiometer or a pot, right? The symbol for it looks like this. Remember this? And this might be called A, and this might be called B. And then you might have a little arrow here, and this is called W, the wiper. And then as you turn this wiper, however it works, then the resistance varies. So say if this is a 10K potentiometer, then from points A to point B, that will always be 10K, all right? But from A to W, that is going to be from 0 to 10K, and then from W to B will be the other value that would sum up. So let's just do an example. So say that we turn this and we measure between A and W and we get 2K. Then from W to B has to be 8K. So no matter what, these two numbers have to sum up using the wiper as the center point here. They have to sum up to the total value, which here is 10K. All right. So we're going to use one of these potentiometers. So kind of, I'm going to get one of these things, and it's going to look like this. It's going to have a little wheel. Let's make that a little bit bigger. It's going to have a little wheel on it, like that, and typically it's got something, like a screwdriver, so you can put a Phillips screwdriver in there for this particular model that I'm using. And then it's got a little housing like this, and then it's got 3 leads coming out of it. 1, 2, 3. So this is like A, this is like the wiper, and this is like B. All right, and then on here someplace, if we go look at this thing, then we would see that it would have a value on it like 10K or 100K or 50K or whatever. So what we're going to do is, it does us no good to connect between A and B because that would always be the value, 50K, 100K, whatever. What we're going to do is we're going to connect between A and the wiper or B and the wiper. So we're going to basically use this kind of connection, and we're going to put one here for RB, and we're going to put another one right there for RA. So we're actually going to put potentiometers inside of each one of these. Okay, so these RA and RB are going to be potentiometers, so we can vary them. And I believe I've got 50K or maybe I've got 100K, I'm not sure. So anyway, so that's the circuit we're going to literally make exactly like this, and that's it. And then we're going to take the output here. So there's our output. All right, and we'll do that in red maybe. So here's our output right here. And this is where we're going to see this square wave coming out, hopefully. All right, and then we're just going to put that onto the oscope, and then we're going to see if there's noise on it and that kind of thing. And then the other thing that we're going to look at, the other thing that we're going to be concerned about is if we put this on a graph here. So here's one cycle, right? Here's one cycle of this, right? And then here would be another cycle. So it would be cycle 1, cycle 2. And then the duty cycle is how much it's on to off. So here's how much it's on, which is the red, and then this portion right here, and I'll just kind of mark that in blue here. This is when it's off. So basically the ratio of red to the total length of this thing, that is the duty cycle, all right? So that's another thing that we're going to measure. And then we know that the height here should be about 5 volts, okay, because we're using a 5-volt system. All right, so that's the 555 timer. So let's see. Before we go build it, let's do a couple more things. Let's bring this back up here so you can see this. So now this was the LM555, but now there's also the LMC555. Here it is here. All right, and this is a little bit more expensive. Now this one, industry's fastest frequency, this one will go to 3 megahertz. So this one will go to 3 megahertz, so this is faster. Now, even though the other timer, if we did the calculations, we saw that, let me scroll down here and see if I can find the same value here. Yeah, so take a look here. So see the output rise and fall time, see this is only 15 nanoseconds now. 15 nanoseconds, and the maximum frequency it actually has it is 3 megahertz. So even though on the other version, this LM version here, plain LM, if we go down to this table, and I believe it's right here. So rise time and fall time is 100 nanoseconds, 100 nanoseconds. When we took that 200 nanoseconds, right, 200 nanoseconds, basically and inverted that, we get 5 megahertz, right? Do it again, 200 to the minus ninth, right? And then we invert that, all right, and then we get 5 megahertz. So we would think this thing can go 5 megahertz, but that's just the rise and the fall time. So then how fast can this thing operate is on top of that. So that's theoretically the fastest it could go, but it doesn't go as fast as the other version, which is the LMC. So the point I'm trying to make is if you want a faster version and you need something to go quicker, then you need to use this LMC version. And then there are other versions also that can go even faster, like 80, 100 megahertz that are variations of the 555. Okay, so but the other point is it's exactly the same, and these circuits will look the same on it, and you can see it right there. So this is just the LMC version. That's all, and then that's that. Okay. All right, so let's get back to our drawing here. Where did our drawing go? Here it is. All right, so this is what we're going to build. So you have everything that you need to know, and we basically want to make this adjustable. All right, so let's go to the bench, and we already built it, which you've already seen, but we're going to go to the bench and start playing with it now that we see exactly what we're expecting here. Okay, so I'll see you at the bench. Okay, here we are at the bench, and we've got our solderless breadboard here with everything on it. And as you can see, there was our discrete crystal version, and then there was our off-the-shelf oscillator version, and then here is our 555 timer version. So let me, there's a couple little things here, a couple little tidbits, which won't hurt to show you. Now, this can be, and let's just move this off here, the oscilloscope probe. All right. Obviously, this can be done cleaner, right? We could make these totally flat, these wires totally flat. We could clean this up if we wanted to, and put everything totally flat to the board, which is what I recommend if you're going to take one of these solderless boards and put it in a box and use it as a functional prototype. But when you're just doing this kind of thing, just keep it clean. This is clean enough, right? Everything's about how much time do you have to put in to get a good result, right? So this is good enough. But one thing you'll notice here is notice I have these 2 wires, and these are the wires that are going from like pin 2 to pin 6 and pin 8 to pin 4 here. Notice how they hit at 90 degrees in the middle here. And that's on purpose. So remember, if you've got parallel wires, you can induce currents in it, right? And induce noise. But if you've got them at 90 degrees, you can't induce anything, right? So the current is going to get induced perpendicularly, and it's not going to go anywhere. It's just going to go, across the cross section of the wire, and that's it. So whenever you have signals, especially in timing circuits, run them across each other at 90 degrees, all right? Very important when you're doing this point-to-point wiring stuff. All right, so let's take a look at the circuit here. And let me get something here, kind of something to point with, maybe here. And so we've got our 2 resistors here, all right, and these are in the form of potentiometers. So this guy right here is our RA, and then this one is our RB. And then here is the capacitor. Let me move it away a little bit. here's the capacitor that's going to the control pin, and that's just a 0.01, which we don't even really need that. But this capacitor we do need. This is C, and this is the capacitor that's important, which is the thing that charges. So this is a monolithic 0.01 microfarad, all right? And we could have made that much smaller. We can make it much smaller, and there are limits to how small you can make it. So the smaller we make it, the higher the frequency we can go, all right? But for now, we'll leave it at 0.01, all right? And then these potentiometers are, let me look at them. Yeah, these are 50K. So these are 50K, they're matched potentiometers, same manufacturer, and same value, okay? So they'll work roughly the same. And then you can just turn them. I'm just going to turn them here with my finger, but if I wanted to, I could turn them with this. Say if they were inside of something, inside of a housing, I could put this Phillips screwdriver, and then I could, turn those and tighten those, okay? All right, so the circuit's ready. The output is right here. We've got ground, we've got power, we've got our bypass capacitor here somewhere, which is, let's see here. As a matter of fact, so let's get a bypass capacitor on here. So I left that off. So let's get the bypass capacitor on there. Let's just put a 0.1 on the power rail here, right there. And that always makes me feel better. There we go. All right. So there we go. So our circuit should work, and I just tested it. So what I'm going to do is I'm going to hook the probe up, and I'm still going to leave this on 10 times so it has higher impedance. And put the probe there, and ground goes here. All right. Okay, so now take a look at the oscilloscope here. So we're on the oscilloscope. We've got the vertical division for 1 volt per division. I've got it at 200 microseconds for the horizontal timing sweep. And let's turn on the 5-volt supply. And there we go. And if I hit measure, all right, we've got a peak-to-peak of 5 volts, which is exactly what we expect, right? Should be 5 volts. And then this RMS doesn't make too much sense for the square wave, right? It's computing the RMS average and then the mean average. These are really more for sine waves, but anyway. And then the duty cycle is 50%, all right? And then that's it. So we got a nice clean signal there. So we got a little bit of noise here, right? A little bit of noise. So the first thing let's do is let's go back to the circuit and let's see, can we get a little bit rid of that noise? We don't want to put too much capacitance on it, but what if we were to put, say, a 22 puff? Can we get rid of a little bit of that noise? Let's find out. So I'm going to go on the circuit here, and let me move this away a little bit. Let me put the ground here, give ourselves a little bit more room, and I'll put that right there. All right, there we go. Okay, so let's go ahead and put the 22 on here and see what happens. All right, not much help right there. All right, so let's try 47. Try 47, if I can find one. And we're just trying to clean up some of that noise, right? We see noise. We just, it doesn't hurt to give it a try and see if we can fix it a little bit, all right? All right, that helped a little bit. So now take a look at the oscilloscope. That's with the capacitor in, and that's with the capacitor out. So that helps a little bit. So, we could put that, putting a little bit of load on there, and that gets rid of a little bit of that noise. But let's go ahead and let's try a ferrite bead also, just for fun. So I'm going to put a ferrite bead in here, and let's see if we can get rid of some of that noise with the bead. And again, it's a little bit better, but not too much. So I'm going to take that out, and I'm just going to leave that 47 picofarad in there to just take a little bit of that noise out. All right, so there we go. We've got our circuit. We're sitting there at 1.5 kilohertz roughly, and a 50% duty cycle. Okay, so now I'm going to play with the 2 potentiometers, RA and RB. All right, so now I want you to keep your eye on the oscilloscope as I play with these 2 things. All right, so I'm going to just sit here and move RA. And then notice what's happening. I'm changing the duty cycle, and the frequency changes too, right? So both of these are going to affect this, all right? So there's RA. Now I'm going to play with RB here. All right, now RB is very dominant on the frequency. As you can see, I'm changing the frequency very quickly here. So 4 kilohertz. Now let's change the sweep so we can see this better. All right, 6. Okay, now look at the duty cycle. So we've almost collapsed the duty cycle here. It's at 81%. So now I've got to do something here to change the duty cycle. So now I'm going to RA and changing that, and now I'm getting it lower. Oh, and then I just lost the signal. All right, there we go. Now it's at 50. All right, and then we can speed this thing up some more. All right, speeding it up. There we go. So basically I got to adjust both these things, but I got to be careful of the duty cycle also, right? So now I've got one of my potentiometers is all the way, RB is all the way turned in one direction. So I'm at the highest frequency, see at 320 kilohertz here. So I can adjust this a little bit. I'm adjusting RA, and then once this duty cycle gets a little bit too small, it's probably going to stop. There it goes. It's got to be at least 50 or it just collapses. All right. So that's about as fast as I'm going to get with this capacitor. So I've got 300 kilohertz roughly in a 67% duty cycle. Let's get the duty cycle back. Let's get the duty cycle back to, let's see if we can get it to around 50% here. All right, and so you can see it, and I'm just playing with this. And because this is a fairly big potentiometer, as I move this thing, I'm affecting it greatly, right? I'm affecting it greatly. And so now let's back this off so we can see what we got here. All right, so we got our 1.23 kilohertz again. So again, I'm going to try and speed this thing up and try and maintain the duty cycle. So just bear with me, and let's squish this way. It makes it a little bit easier to see what we're doing. All right, and making it faster, and then reducing that duty cycle. There we go. And let's just try and shoot for 100 kilohertz. Let's try and get 100 kilohertz here. And you can see now what's happened is we've lost it again as I modify this thing, right? Because these values are changing so much. I'm going to go back again until I can get this thing to fire back up. There we go. So you can see it's tricky. You can see it's tricky, and this is why when you play with these 555 timers, and you can just see me adjusting this thing here. When you play with these 555 timers, if you just start off with resistors and you don't kind of go through this experimentation, you kind of don't get a feel for how these things are affected by the two different resistors. So by doing this, you kind of get a feel for it, and then you can see what you can do and what you can't do. There we go. And let me open this up. And what I'm trying to do is get this frequency up higher. Get the frequency up higher. There we go. And I just flattened it out again. There we go. Just try and get a decent value here. Okay, here we go. So it's 120, and we can slow this down just a little bit. That's good. That's good enough. So 120 kilohertz. So the point is when you do these calculations, you can do them on paper and you can solve for one or the other, but you've got to solve for both the duty cycle and you've got to solve for the frequency you want, right? So you've got to find these two values that give you both of these things simultaneously, all right? And that's what makes it a little bit hard. So you can kind of play with it like this using potentiometers. All right, so that's that. Now, can we slow this way down? So let's do another experiment. Let's slow this way down. All right, so let's see here if I can get this back down here to what we want. So there's 4 kilohertz, and I'm trying to slow this down. And let's change the sweep rate here. All right, much better. All right, and we've got 1.25 kilohertz here, and then we've got kind of a crummy duty cycle. All right, so 1. All right, so now, so with these resistor values, about the smallest I can get this thing down to before it starts collapsing is about collapsed. Okay, I'm going back down. Okay, let's go, let's go, let's go. Here we go. All right, and I'm going to slow it down some more. 1.3. And that's it. So I can get it down to about 1 kilohertz, and it's surviving. So let's do this. Let's go change what that capacitor is. So now it's 0.01. So if we change it to 0.1, it'll be 10 times slower. So instead of 1 kilohertz, it should be roughly 100 hertz. So we're just going to do that. So what I'm going to do is I'm going to find a 0.1 microfarad. I'm going to turn the power off for a second. And let's go replace this capacitor, which we're calling C in the design. This is C. All right, that needs to go to ground. So let's put that inside of there. So we're replacing it. There we go. Okay, let's turn the power back on. All right, and there we go. We've got roughly, let me change the sweep. So now I've got like 90 hertz, right, which is what we're expecting. Now, can we make this even slower? Can we, let's use a 1 microfarad, and now we should get like, 10 hertz or something. All right, 1 microfarad. So I'm just gonna pop that out and just leave the thing on and just let it free run, go crazy. And I'm going to put a 1 microfarad. I'm actually going to put a tantalum capacitor in here, which normally I wouldn't do. We would use monolithic because we want them to be more stable. But we're just playing around here. So, and we want to make sure we put this in the right polarity because these all are polarized, and that's not long enough. So let's find another one. Find another one. Here we go. All right, so this is a 1 microfarad tantalum. Actually, this is a 10 microfarad tantalum, so, but that's okay. So this will be 100 times slower. All right, so let's give this a try. Now, watch this. So now it's looking like 1 hertz, and so it's very, very, very slow. So if we put an LED on this output, we'll actually see this LED oscillate or go back and forth here. So let's go ahead and let's put an LED. So first, let's take our output and let's put a current limiting resistor here. So we'll put a 220 ohm resistor. All right, so we've got our output. We're going to put a 220. There we go, which is this is 330 actually. So this is red, red, brown, red, red, brown, 330 ohm. And we're going to put our LED here. All right, so there we go. So check out the LED. All right, and so the oscilloscope, let's put this back on here. Now take a look at the oscilloscope. It's saying it's going to have a hard time figuring out what the frequency of this is because it's so slow. All right, it can barely do it. But let's speed it up a little bit. So we'll speed it up a little bit. And so there I go. I'm speeding it up, and I'm going to speed it up some more. There we go. And because the capacitor is so big, right, I can adjust these kind of slowly. All right, so there we go. And the duty cycle, I'm not too happy with it. So let's see, can I change the duty cycle here? I'm going to change the duty cycle and get it more even. You'll see the LED is going to look more even. There we go. All right. Oh, just lost it. There we go. And we're going to speed this thing up more. Here we go. And there we go. That's about 5, 6. Let's get it to like 10 hertz. All right, so it's at 10 hertz. You can see it on the oscilloscope, about 10, 11 hertz. The duty cycle is a little bit big. Let me see if I can back it off and square it up a little bit, get it at 50% roughly. And we lost it. There we go, 50%. So there we go, 56%. We got about 14 hertz, and we've got our little LED blinking there. The camera now, I don't know if you can see it on the camera. It might be the camera's frame rate. It's interacting with the frame rate, which is an interesting little thing. So the frame rate is either 30 here or 24 frames a second. So if we adjust this to make it faster, so let's see something. So I'm going to put it at the frame rate of the camera roughly, which I think is it at 24 or 30? I think it's at 30, the way that this is set. So this will be kind of an interesting experiment. So I'm going to go a little bit faster. I'm at 26, says the oscilloscope, 27, 28, 29. There. So look at that. So I can see the LED blinking. I don't know if you can. It might look like it's just glowing on the camera. Yeah, so it looks like it's glowing through the LCD at least because we matched the frame rate here. So anyway, that is the 555 timer, the famous little 555 timer. You can see you know, drive an LED right off it. Now let me show you something else you can do with it. You can just take a speaker. We're going to take a speaker right here, and we'll just connect the speaker directly up to it. And let's see if we can hear it. Yeah, not loud enough though. Let me hook it directly up. And that's too much load. So let's change that resistor. Let's change it to like a 33 ohm. 33 ohm. Let's see if we can find a 33 ohm. Something small. 33. There we go. We don't want to try and drag too much current. So we'll take the output. There we go. And all right. Now you may not be able to hear that, but as I turn it up, you may be able to. Can you hear that? So it's directly driving the speaker there. Okay. Let me just pull that out. So that's it. So that's the 555 timer. Now what's cool about this, what we could do is we could have RA and RB, and we could have the capacitor C. Then we could fix RA or RB and C, and then we could just have a bunch of different RAs or a bunch of different RBs connected up to buttons. And then those frequencies could be notes of an organ, right? You know, the diatonic scale or whatever. So we could have, you know, C, D, E, F, etc. as buttons, and we can make a little organ out of this. And we're actually going to do that with this. All right, so we'll do that in a later experiment. We'll actually make a little organ out of this to show you how that would be done. All right, so that's about it for this lecture. So that's the 555. So now we've done discrete oscillators with crystals, we've done off-the-shelf crystal oscillators, and we've done timer ICs with the 555 timer. All right, so that's a good amount of information on clocks, and we need clocks to generate signals so that all of our synchronous logic can operate off it, or we might just need clocks to do things with them of different frequencies, all right? Like we want to transmit a signal or receive a signal, etc. We need to create, you know, clock frequencies so that we're doing something at some specific time on some time interval, and that's what clocks are for, all right? So that's it. I'll see you in the next lecture. All right, welcome back, and we are on the next lecture. And let's see here, we're on chapter 4 of my book, which is now we're going to dig really into digital electronics and move away completely from the analog stuff for the most part. And so, just like the analog, we're going to have to learn some terminology, some rules, some language to discuss digital. Now, we could just skip all of this and just start building things. But you know, the problem is then you don't have the fundamentals, you don't have the foundation, and you don't know what you don't know. And that's the most important thing, I think, in electronics is you need to know what you don't know. And if you know that, then you realize that there's probably a better way to do this. But if you think you know everything, then that's really bad. So we're going to do this chapter 4 here and probably do this in a couple lectures. We'll see how it goes. But I want you to read this carefully and go through it carefully because this stuff is actually really, really important. All right, so what we're going to do is we're going to use the book, we're going to use the Blackboard, the drawing program. I don't think we're going to do anything on the bench in this lecture. We're just going to go through here piece by piece, and I'm just going to discuss this stuff. Some of it will be reviews, some of it won't, and let's just see how this goes. All right, okay, so first thing is entering the digital realm. All right, so let's see, logic conventions, we've kind of discussed this. So in a digital system, a logic high is denoted 1, right? And it's the highest voltage in the system, like +5 or 3.3 volts, all right? And then a low would be a 0 volt, right? And that would be what's called a positive logic system. Now there's also a negative logic system, which is the opposite. In a negative logic system, the high is considered false and the low is considered true, right? It's just an invert of it, that's all. We're not going to worry about that, but just in case you ever hear that, a negative logic system, it's kind of like in a computer programming, if you ever heard big endian and little endian, right? The order of bytes, big endian, little endian, which comes from Gulliver, I'm having a hard time saying this, Gulliver's Travels, the book. And it was how they opened up the eggs. So they did it little endian or big endian, and that's where that actually came from. But same thing. So we're typically going to only be using positive logic systems. So a high is true in 1 and 5 volts or 3.3 or whatever the voltage in the system is, and a low is 0 or false. All right, that's all. Okay, standard IEEE logic symbols. IEEE stands for Institute of Electronic and Electrical Engineers. So these are the symbols that you'll typically see representing these things. So we've got and, or, and not, and then we've got all of their inverts. We've got NAND, NOR, and a buffer. And one thing that you notice is to create a NAND gate, you just put a bubble on the AND gate, and bubbles mean inversion. So bubbles mean inversion, or dots mean inversion. And if you put 2 bubbles, that would cancel each other out. So not is the original. So if you put a bubble on the not, you're going to end up with a buffer, right? So X would equal Y, and here, if the output was Y, Y would equal not X, that kind of thing. All right, and then we have the special one, which is the exclusive OR, and that one was that logic gate is high when both of the inputs are opposites, and then low otherwise, and then the XNOR is simply the opposite of that. All right, so these are your basic building blocks. Okay, and then this kind of goes through and describes each one of these. We have already done this. One thing is in the text, you're going to see a slash variable name like this example right here. That's because it's hard to put the bar on top of a variable. So this means not. So whenever you see a bar next to something or on top of it, typically it means inversion. Okay. All right. So the not just inverts it. The buffer just buffers it. It's an amplification function. And means both inputs have to be true. NAND is the opposite of AND. OR means either input can be on or both can be on, and then the NOR is the opposite of that, and then XOR, we just talked about that, only when they're opposites. All right, it's a high output. Okay, this is now where we want to go. So we want to talk about this whole concept called Boolean algebra. So the number system that we're all typically very familiar with is the decimal system based on 10. So 1, 10, 100,000, 10,000, and so forth, right? If you're a programmer, hopefully everybody watching this is somewhat of a programmer. You're probably familiar with binary systems and or hexadecimal systems. So binary systems are base 2, and hexadecimal systems are base 16. All right, so let's take a quick look at that just to make sure that concept is getting through there. If you're not a programmer and you're just kind of learning electronics, and even if you are a programmer, a lot of programmers that program web applications have probably never dealt with binary numbers or not comfortable with them, or hexadecimal numbers. So let's take a quick look at this. So over here we've got decimal. All right, and that's what we're used to, right? So let's say we had the number 351. All right, so this right here, right, that's the ones place. This 5 here is the tens place, and this 3 right here is the hundreds place, right? Hundreds. So if you want to figure out what this number is, well, it's 3 times 100 plus 5 times 10 plus 1 times 1, 351. Okay? So that's our decimal system that we're all used to using. Now, now there's binary that the computer uses, right? Binary. And that means 2, based on 2. And so it only has 2 symbols, 0 and 1. Now, of course, decimal has 10 symbols, right? It has 0, 1, 2, 3, dot, 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 up to 9, right? Let's make that 9 a little bit better. 9. So that's 9 symbols plus the 0 is a total of 10 symbols, right? 10 symbols. And I'm writing 10 with decimal. Now in binary, we only have 2 symbols. We've got 0 and 1, right? Those are our 2 symbols. That's it. So now if we have a number in binary, every one of these places is a power of 2. Over here it was a power of 10, 1, 10, 100, right? So what this really was over here, this was the 10 to the 0 place, this was the 10 to the 1 place, and this was the 10 to the 2nd place, right? Does that make sense? All right, let's make this a little better comma right here. Let's make this a better comma. So we're trying to show binary here is 0 and 1. So those are the two symbols. Or we could say, you know, binary consists is the set of symbols with these two symbols, 0 or 1, right? Okay, so now let's write a number in binary. All right, so let's start off with something simple. Let's do a 4-bit binary number. So how about 0, 1, 1, 0? All right, so the question is, what is that number? All right, so let's figure out what that number is. So the first thing is, let's figure out what these places are. All right, so what I'm going to do here is I'm going to write, let's do the arrow thing again. Let's see if we can fit it. So this first place right here is the 2 to the 0 place. This one right here is the 2 to the 1's place. This one right here is the 2 to the 2's place. And this one right here. And this is why in computers, obviously you got to be careful with your off by 1. So if you thought this was the 1's place and said it's 2 to the 1, that would be incorrect, right? You got to be very careful. This is the 0th place, right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. And now I'm going to write each one of these in decimal. So 2 to the 0, anything to the 0 is 1. Then 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So this is the 1, 2, 4, 8's place. All right, so now let's figure out what this number is, right? So therefore, let's write what this number is. That's an arrow, by the way, but it looked like a smiley face, so now I'm going to make a therefore. This is a therefore. All right, so now what is this? So let's go down here and let's compute it. So this is the 8th place, right? So this is 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. 0 times 1, all right? And so if we add this whole thing together, we've got only the two ones here, so we've got a 4 and we've got a 2, which is a 6, right? So this equals 6 in decimal. How would we let someone know that this is decimal and not some other numeric system? Well, you could just put a base down there. So you can put 10 down there. So I could put a 10 down here. And when I write a binary number like 0110, I can put the base down here in 2. Now you could get kind of crazy, and you could say, well, what base is the base written in? And the base could be written in a different system, but typically write the base in decimal. So anyway, so this is a binary number. That's how we figure it out. There's a decimal number, decimal binary. Now, let's look at the third system. Let's look at the third system. And you know what? Let's do a more complicated example. So let's go ahead and let's do a bigger number. All right? So let's do a bigger number. Let's do an 8-bit number. So we're going to do an 8-bit number. Let's do 1 0 0 1 1 0 1 1 2 3 4 5 6 7 1 1 2 3 4 5 6 7 8. So there's 8 digits right there. All right. So now what I'm going to do is I'm going to write what these what the powers are under here. So this is the 1's place, the 2's place, the 4's place, the 8's place. Then this is the 16's place. This is the 32's place. This is the 64's place, and this is the 128 place. All right, so now those are the multipliers. So all we really do is just add these things. Wherever we see a 1, we just add it up. So this is another way to kind of look at it. So you can see let's use this color here. So now wherever I see a 1, I'm just going to add that number. That's another way to kind of think of this, right? So I see a 1 here, so it's 128. Plus, I see 1 there, so 16. Plus 8. Right, plus 2, plus 1. So let's add this all up. All right, so 128 plus 16 is 128 plus 16 is 138, and 6 is 144. 144 and 8 is 152, and then 2 is 154, 155. All right, 155. Let's check my arithmetic. I'm not a calculator, but let's see. 16 plus 8 plus 2 plus 1, 155. Okay. All right, so that's correct. So that's how you do that. Now let's count in binary. Let's count in binary. Let's do some counting. All right, so let's say if we had 4 digits, 0, 0, 0, 0. So there's a 4 digit. So we're going to do a 4-bit count. And when we're developing electronics, typically we'll be working with 1 bit, 2 bits, 4 bits, maybe 8 bits. And so if you have these things memorized, it really does help so that you don't have to figure things out. So if you can remember the powers of 2 up to 8 bits, that's really good. 16 bits is even better. But usually if you can do it up to 4 bits, you're okay. And then 8 bits is ideal, because as you compute things and figure things out, it's nice if you can kind of say what's that number in your head and kind of figure it out, or at least be able to count. All right. So here's the trick to counting in binary, all right? So let me show you this so you always know how to do it. The trick is this. You start off with all zeros, and then all you do is you flip the leastmost bit. All right, so here we go, 0, 0, 0, 1. All right, now you, for the next number, you turn that back to 0, and then you flip this bit. So 0, 0, 1, 0. All right, now you keep flipping the lower bits. So 0, 0, 1, 1. Now they're all ones, so now we go and we flip this bit, and then we reset the other bits. Can you see this pattern forming? 0, 0. Now we go here and we count again. So every time you add another bit, you just are recounting the lower bits. You're incrementing again. You're just kind of repeating the pattern. So 0, 1, 0, 1. All right. Then 0, 1, 1, 0. Then 0, 1, 1, 1. Now we're going to go flip this bit right here, 1, 0, 0, 0. So now you can see right here we've gone half of the series and see these. So you can look right here. So here's you counting, and let me kind of show you this, and I'm going to kind of erase it. So here's us counting with just 1 bit. That's what it looks like, 0, 1. That's all there is to it. Now here's us counting with 2 bits. So there's all permutations of 2 bits, 0, 0, 0, 1, 1, 0, 1, 1, in order. All right. Here's us counting with 3 bits. Do you see this pattern here? Here's us counting with 3 bits. All right. And so now we've set this bit high. So what we can do is we can just copy what we just did here. We can just copy it. So now watch this. And we can do that all the way through here. So now we're just going to go 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7. All right, and then so we start here 0, 0, 0, and then you can just copy this down, 0, 0, 1, 0, 0, 1, right? Then the next one is 0, 1, 0, then 0, 1, 1, then 1, 0, 0, then 1, 0, 1, then 1, 1, 0, and 1, 1, 1. Okay, so those are all the numbers. Now, what do these represent? So in order here, right? So this would be 0, this would be 1, this would be 2, this would be 3, this would be 4, dot, 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 just go down here. What's this one? This would be 8, right? 1, 2, 4, the 8's place. Therefore, this is 9, this is 10, keep going, dot, 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 and down here would be 15. All right, so notice we have 4 bits here. All right, so let's look at a formula here. So if we call this n, the number of bits. So what's the highest magnitude that can be represented with n bits? Okay, so highest magnitude with n bits. That's the question. So let's try. Is it 2 to the n? Is it 2 to the n? Is that the highest magnitude? Well, let's see. So we have 4 bits here. So 2 to the 4th. So 2 to the 4th equals 2 times 2 times 2 times 2. 2 times 2 is 4 times 2 is 8 times 2 is 16. Look at this number here, 15. So it's not equal. All right. So, but it's almost equal. It's almost equal by a difference of 1. And it turns out that the highest magnitude is 2 to the n minus 1. Not 2 to the n minus 1, 2 to the n minus 1. So 2 to the n, 16 minus 1 would be 15, and now they would be equal. So if you have n bits, the number of different permutations of the bits is 2 to the n. There are 16 combinations here. 0, and then all these 15, right? That's 16. But what's the largest magnitude, binary magnitude, non-signed magnitude? That is 2 to the n minus 1. Okay? All right. Now, so that's a binary, and then real quick, let's just let's look at hexadecimal here. I'm not going to go into a big thing here because we're not doing computer stuff. So hexadecimal, that means base 16. Base 16. All right, so let's take a look at that. So if we've got, let's say, 2 digits, let's say 2 digits. So if we've got a number that's like 34, all right, we've got these 2 digits. So this first place is the ones place again. All right, so this is the ones place. All right, ones place. And then now here's where things get interesting. This one is the 16s place. All right, or 16s. Okay, and then the next one would be the 256 place. All right, so the next one, if we had another digit, let's say 1. Let's get that color right. Say 1. This is the 256. I'm just going to write it 256. All right, so 1, 16, 256. And the reason why is because each place, so this is the ones place, the 16s place, and the 256. All right, and just to prove it, if we take 1 times 16 is 16, then 16 times 16 is 256, right? And then if we kept going, we could keep doing all these different places, right? But we're just going to do 3 for now, 3 places. All right, so 1, 3, 4. And so that means these are the multipliers for each one of the places. So we've got 1. So we've got 1 here, and that's going to get multiplied by 256. We've got a 3 here, and then we've got a 4 here, right? So this is really 1 times 256 plus 3 times 16 plus 4 times 1 equals, right? And let's do the calculator here. So we've got 256 plus 3 times 16, which is what, 48? Plus 4 times 1, which is 4, and that's 308, if my arithmetic is right. 308, and let's be careful, that's base 10. And what was this? This was base 16. Okay, so now the first little problem should, kind of hit you here is, if this is base 16, well, this is base 10. We've got the symbols 0 through 9, which are 10 symbols. In binary, we're only using 2 of the symbols, 0 and 1. But in base 16, what are we using for the other symbols? If you're a programmer, obviously you know what they are. But let's write them down here. So hex. So here we go. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry. 11, 12, 13, 14, 15. Now remember, that's 16 total numbers, 0 and then 1 to 15 is 15 plus 0, 16. The hex value here, this is 0. This is 1. This is 2. This is 3. This is 4. This is 5. This is 6. So far, so good. This is 7. Nothing weird. This is 8. This is 9. This is 10. This is 11. Oop. And I got overzealous there. Now, when we hit 10, this is A, this is B, this is C, this is D, this is E, and this is F. So you got to look these up. You got to memorize these. No way around it. So those are the symbols that represent the numbers, okay? And that's just all there is to it. There's also another system called octal, which is base 8, and but that became unpopular. I don't know, maybe in the 60s, 70s, octal kind of went out of use. But hex and binary, very, very useful. And of course, obviously decimal. So if you represent numbers, let's do one last little example here. I'll do it right here. How about this? Let's do a famous number here. We'll do, FF. And oh, and also, if you have a hex number, you'll see a couple different things. You'll see like a dollar sign, like that, and then you would see the hex number. So if we had the hex number 01, that would just be 1, right? If we had the hex number 0A, that's actually 10. If we had the hex number 0F, that would be 15, right? See how that works? Now what's 16? 16 is 1, 0, because this is the 16's place, so that's 1 times 16, that's 16, and then 0 is 16, so that's 16, all right? So you'll see either a dollar sign, So you could see something like $FF is the same number, and then you might see 0x and then FF. So in the computer, typically with a lot of C-based compilers, this is the notation, 0xFF for hex numbers. And then this $ notation, you might see that in BASICs and things like that. All right, so what is FF? Well, let's figure it out. So F is 15 times, this is the 16 place, plus another 15 times the ones place. All right, and so that number right there is 255. Again, it's not 256. There are 256 total symbols, 0 through FF, but the largest magnitude is 255 base 10. Okay? So there are three different number systems that we might be interested in: binary, decimal, and hexadecimal. All right? And converting through each one of them is very simple. You can just go from either system to decimal, then go from that to the other system. All right, and then you typically don't want to do math with each one of them with different systems. You want to do the math in the same system: decimal, binary, hexadecimal. Everything works the same. You just have to create new rules and make sure the rules are consistent for addition, subtraction, multiplication, division. We'll talk a little bit about that in binary when we get a little bit farther. So, all right, so let's go back to the material here in the book. All right. So what I'd like to do is I want to kind of make these lectures. I want to break these up a little bit. So let's go a little bit. We'll go a little bit longer here. All right. So now we're going to start talking about what the basic laws are. Now, just like in base 10, we have addition, subtraction, multiplication, division with numbers, and with Boolean algebra, right? We have the same kind of laws, except they're tricky because when you look at them, you think you're looking at decimal numbers. You are not. You're looking at binary numbers, so you need to keep that in mind. There's only 1 and 0, 1 and 0, 1 and 0. It's not representing 1 from 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just representing 1, and that's it. All right, so keep that in mind, and that'll throw people off. So here's the additive law. This is OR. So this is not normal addition. This is Boolean addition with Boolean or binary numbers. So a 0 or a 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. And 1 plus 1 is 1 in this case, because this is an OR. So this is an additive law for OR, all right? So now we're not adding binary numbers right now. We're not adding binary numbers, but these are Boolean laws. So this is like the OR gate. So 1 plus 1 is going to give you a 1, all right? Okay. Let's go to multiplicative. So this is the AND law, right? So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. And again, these are times. We use the time symbol. 1 times 1 is 1. All right. Now, if we keep ORing all these things together, no matter what, we're always going to get 1. As long as one of these is a 1, we're going to get 1. All right, and the same thing if we were using multiplicative law. If we had one multiplication or AND of 0 in there, the whole thing turns to 0. Okay, all right. Let's look at some of these algebraic identities here. And again, I don't expect you to memorize all this. I just want you to see these things to kind of see that there is something going on here with these numbers. So if you have a variable which can represent 0 or 1, right, and you were to add it to 0, the result is always going to be that variable, because if this was a 0, then the result would be 0. If this was a 1, the result would be a 1, which is the same as the initial variable x here. So the additive property, you always get the variable if you're adding to 0 or ORing with 0. Now, the additive property of 1 is a little bit different. It doesn't matter what x is now, 0 or 1. If you're ORing it with a 1, or adding 1 here, you're going to get a 1 out, no matter what. OR 1 is always going to give you a 1 if you've got at least 1, 1, all right, in Boolean algebra. All right, and then adding to the self again, remember the biggest number we can have here is 1, right? So x plus x, so if x was 0, 0 or 0 is 0. If x was 1, it would be 1 or 1, and we would get a 1 out, all right? So that's adding to the yourself. Adding to the complement. So this is interesting. So if x was 0, so 0 or not 0, which would be 1, so that'd be 0 or 1 equals 1. And if x were 1, 1 or not 1, which would be 0, so 1 or 0 is still 1. All right. So OR is this this function that no matter what, if you got 1, 1 there, the output's going to be 1. And same thing with an AND, all of them have to be 1 to get an output. All right, so now let's talk about the multiplicative property. This is the AND function now. So 0 and x, or 0 times x, is always 0. So no matter what, if one variable is 0 and you AND them together, the result is always 0. So this is used in gating, right? So if you want to turn something on or turn something off, right, then this by multiplying, you can just shut it all down or ANDing it, and that's that. Okay. All right. Multiplicative property of 1, same thing. Now, instead of being 0, right? So 1 times x, or 1 and x, is going to be x. So if x is 1, 1 and 1 definitely equals 1. But if x is 0, 1 and 0 is going to equal 0. So now it's whatever x equals, whatever the input variable. All right. Squaring, again, we only have 2 symbols, 0 and 1, so we can't get anything bigger. So this is interesting. So x and itself equals x, right? Does that seem right? X and itself equals x. Let's look up here. Remember this one? Adding to self, x or x equals x. X or x equals x. So this is interesting because 0 plus 0 equals 0, that's true, and 1 plus 1 equals 1, that's true too. And then, but here, in the multiplicative version of it, if x is 0, 0 and 0 definitely equals 0. 1 and 1 definitely equals 1. So they're the same. So that's kind of an interesting little property of this number system. Okay. And multiplication with a complement. So this is very important. If you ever AND a variable with the not of itself, it's always 0, right? Because whatever the original variable is, right? If it's 0, then the not of it is 1. If it was 1, the not of it is 0. When you multiply or you Boolean them together with an AND operator, you're always going to get 0. So this is very key. So if you ever see a function, so like if we have a big function out of a bunch of variables where you've got x's and not x, they're going to cancel out themselves if they're multiplied together or ANDed together, all right? You don't have to compute them. So this is part of optimization. When you analyze a circuit and you say it's this or that plus this and that and so on and so forth, if you see x and not x, or variable ANDed with the invert, it's 0. Get rid of it. You don't need it, okay? And then here's the table here, okay? And let's take a look here at some of these algebraic properties. So commutative property, remember what commutative means? It means if you take something and then flip the order of it, so x or y equals y or x, that's true. Commutative property of multiplication, x and y definitely equals y and x, same thing, no magic there. So order is unimportant, all right, when you're doing Boolean algebra, just like normal decimal algebra, all right. Associative property, same thing. So if you've got x plus y plus z, you're going to get the same result no matter how you order these. So if I now put the parentheses around x and y, I'm going to get the exact same result. All right. So the order that you do this in does not matter. All right. Associative property of multiplication. So associating means we're basically going to do the same kind of thing. We're going to change the order that we're going to do this in. So no matter what, if you do x and y and z, first you do y and z, that's equivalent to x and y and z. No matter what, you're not going to get anything different. Distributive property, remember that from if it's been a while that you've gone to high school or whatever, or college, done the algebra, you just distribute it over there, x times y, and then plus x times z. So x times y plus x times z. So this and or turns into this. So it's a sum of products, and that's all there is to it. So it's exactly what you would think. And then here's some of our properties right here in a table. Okay, so hopefully there's no typos in here. But I want you to read over that. All right, so let's go ahead and stop here and let your brain simmer for a minute, and I'll meet you back in De Morgan's theorems and bubble pushing. All right, so now we're going to learn some Boolean laws to help us do this math a little bit faster. So I'll see you in the next lecture. Bye. Welcome back. We are on the next lecture, and up here on your screen you can see we're looking at De Morgan's theorems or De Morgan's laws and bubble pushing. So we're still in chapter 4 of the book here, and we just went over some of the binary, hexadecimal, and decimal number systems. So now we're going to talk about this law, and we're going to make this a short lecture and just stick to just this right here. So again, the material that we're going over is very important. You can still build electronics without it, but it's actually really nice knowing this stuff because it allows you to optimize your simple circuits and at least know this this kind of math exists. All right, for Boolean algebra. All right, so let's get right into this. So De Morgan's theorem, De Morgan's law. What they basically say in a nutshell is this. They talk about if you have the sum of products or the product of sums, you can turn these formulas into either or. So if you have something based on a sum of products, right, then you could turn that into a product of sums, right? And then the simplest form of it is this right here. And there's two different formulas or two different equations. And so remember, the bar just means inversion. So typically we'd draw the bar over things if we could, but it's too hard in the text, too much editing. So we're just going to leave it like this. So what this says is this is x and y. So the invert or the not of x and y is equivalent to not x or not y. And similarly, the invert of x or y is equivalent to not x and not y. All right, so that's very hard to understand when I say it, but if you look at it, so basically if you were to invert either, so this is a product and this is a sum. If you invert a product, then it's the same as the sum of the variables inverted. And if you invert a sum, it's the same as the product of the variables inverted as well. Graphically, and so let's look at it graphically. Graphically, what it says is that if you have an and, right, which is, and then you invert the output, that's equivalent to an or with the inputs inverted, or if you like it without the inverter symbol. If you have a NAND here, right, it's equivalent to this right here, all right, which is an or with the inputs inverted. All right, that's all there is to it. So what it allows you to do is it allows you to convert AND gates to OR gates or OR gates to AND gates as long as you have inverters, right? So we call this bubble pushing. And so these little bubbles, right, which represent knots or inversion, you push them. So if I take this bubble and push it through this AND gate, it turns the AND gate into an OR gate, but then the bubble gets replicated on both inputs, and here it is here. So I push the bubble through, the gate turns into an OR gate, and then we have the bubbles on the inputs here. Okay, so that's what this looks like. Now, before we go on, I wanted you to take a look at the Wikipedia page for this. So if you just Wikipedia search for De Morgan's laws, you can read about it. So he's Augustus de Morgan, a 19th century British mathematician. All right, and what this is really all about, this is more has to do with set theory. All right, and the set theory can be applied to binary because binary can be thought of as a set where the set is 0 and 1 and that kind of thing. And so if you look up and you read a little bit about set theory, if you haven't done it, there's a couple words, conjunctions and disjunctions. They mean OR gates and AND gates. So a conjunction is like an and a disjunction is like an OR gate. All right, so we can find these analogies to things. All right, and then here's the math right here. So if you remember in set theory, U means union, and remember the upside down U means intersection. So this is interesting. So what this says is it says that the if you were to take the negative, right, or the invert, the complement in set theory, right, that's that bar. So if you take A union B complement, that equals A complement intersect with B complement. Likewise, if you take the complement of A intersected with B, that's equivalent to A complement union with B complement. And then they show it graphically over here. All right, so this is exactly, we can map this into the Boolean space with just two values, 0 and 1. And then you can go through some of this. It's just set theory and logic notation. And if we go down far enough, we'll see under engineering, there it is. So A and B not is equivalent to A not or B not. Additionally, A or B not is equivalent to A not and B not. And that's exactly what we have here. All right. So you can read through this, but that's basically the gist of it is just these two simple formulas can be mapped into a Boolean logic. Okay, all right, so De Morgan's laws, what they help us do is convert AND gates to OR gates to AND gates, and they also help us do optimization because we can simplify things by, say if you've got, for example, say you've got a circuit you've designed and it's all AND gates except for one OR, and you're like, God, I just wish I could get rid of this OR. You can. With De Morgan's law, you can convert the OR into an AND as long as you have enough inverters, all right? And we'll take a couple examples. We'll look at that on the blackboard in a minute here. All right, so again, I'd like you to read through this, but I'm just going to kind of go through this. So here's another example. So this is saying that z equals x and y, right? And we've just got the bar over there, just showing graphically the bar is the notation that you would normally use. And there's physically an inverter there. This whole thing creates a NAND gate, right? That's equivalent to this right here, all right? And again, the exact same, z equals x NAND y, z equals x NAND y, all right? Or you could say z equals x and y inverted if you want, but that is the NAND gate, all right? So if we discretely have an AND and an inverter, that's the same as a NAND gate, all right? Now, when you're designing little combinatorial circuits, so we've learned that there's ORs and ANDs and NOTs and XORs and so forth, and say you're designing a little circuit and it's like when one signal is a 1 and one's a 0, or this other signal's a 1 and this one's a 1 and this one's a 0, then I want to output a 1. That's a combinatorial circuit. You've described like an if clause, right? An if clause in a C or JavaScript or something. And that's the kind of things that we want to be able to implement in electronics with basic gates, with basic logic gates. So we have this concept of a sum of products and a product of sums. So sum of products simply is like a big OR list, right? So z equals x and y, or A and B, or F1 and F2. So see, sum of products. So the products are the ANDs. So these are your AND terms, all right? And then it's all ORed together. And you've got one big Boolean expression that's going to output a 1 or a 0, all right? Now, so you've got this thing right here, and now you've got AND gate. It requires AND, and it requires an OR gate, right? But maybe the gates that you have don't fit this, right? So you could apply De Morgan's law to this. And so we can't change the meaning of this. So if we were to invert this, right, that would be incorrect. But if we invert it twice, it would be the same. So what we'll do is we'll invert it twice. We'll use De Morgan's law with one of those inversions, right? And then we'll leave the other inversion there. So in other words, it's like if you want to do something to a number, you can surely multiply it by another number or add a number, but you better divide and subtract if you want to be equivalent, all right? So it's like doing algebra. You want to maintain the value, but you can play around with it to transform it. All right, so if you take a look here, this is what's happened. So I've parenthesized this expression. Then I've said, let's go not. So not is going to give us back the original value, right? Okay, so we haven't changed the value, but now we can play with De Morgan's law, which states that if we have a sum of products or product of sums, it's the same as, equivalent to, if it was a sum of products, now it's a product of sums with everything inverted, or vice versa. Here, we've got a sum of products. So now we look down here. Now take a look very carefully. Look what's happened here. So x plus y turns into x plus y. A and B, or A times B, turns into A plus B. And F1 times F2 turns into F1 plus F2. But we need to invert each one of these. So notice the inversions on it, right? The inversions. So now this is equivalent to this. So let's say, for example, we have a 3-input, let's say we have a 3-input AND gate. So this would be one expression here, one expression here, one expression here. Each one of these, so we've got to AND this, and then we need one OR gate here, one OR gate here, one OR gate here, and then we would have a bunch of inverters, then invert the whole thing, and it would be equivalent to this. So the whole point is you can transform logic using these rules into different forms that might be easier for you to implement with the gates that you have, all right? Okay, so let's move on here. And then this is showing what's exactly happening there. So we originally had this right here graphically. And you know what? No one can figure this. If you just look at this going right over your head, right? It went over my head when I looked at it. You can't keep track of it. But you do it graphically, and then it's pretty easy. So this is the exact same circuit but now graphically. So here's what we began with. All right, and then notice I've got one OR gate that's 3 input, and then I've got 3 2 input AND gates, right? That's what this represents. This is X, Y, A, B, F1, F2. Here's X, Y, A, B, F1, F2, all right? And then I OR them all together. Well, what if I don't have those gates? What if I have a bunch of OR gates and then I've got a 3 input AND gate, right? Well, we can use De Morgan's theorem on it. So here we go. So this is what we got. So I'm going to add 2 bubbles to it, 2 inversions. The result is still going to be the same, right? So that doesn't do anything. But I kind of hold this one off over here, and then I process this one. So I push the bubble through the OR gate, so the OR turns into an AND. Then what happens? Then I get a bubble here, and a bubble here. All these get inverted, right? Then I push those bubbles through, and then it turns each one of these into an OR, and then I got bubbles all in the input. So now, and then I've got our other bubble that we had here, right, because we only pushed one through. So now we've got this AND gate here, right, and with an inverter on it. So it's really a NAND. We need a NAND, so we assume we have inverters, okay? And then we've got all these OR gates with all the variables inverted on the input. So now it's equivalent to this, which is just what we computed mathematically. So I typically do this graphically, right? After I figure out what I want, kind of with logic, I'll do it graphically so I can see what I'm doing and not make mistakes. All right. So anyway, so that's what De Morgan's law is used for. Now, here's the opposite: a product of sums. So here's a sum, and there's a product of the sum. Okay, again, exact same thing, right? Now we just put 2 inversions on here. We bring one of the inversions in, and then we apply De Morgan's law, and then everything just flips. So now it's a sum of products. So there's a product, all right, and then it's a sum. But remember, we got to invert these variables. Now, key thing here, notice B already had inversion. B had an inversion. So now B's doubly inverted, so now it's just B. So now when we simplify this, look at that. So now we have this, and B is just B. So inverted, 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 but B is doubly inverted, which just is B, okay? You don't have to write the double inversion. So there you go. So there's that example, okay? And then again, here it is here, a product of sums. So we had this scenario. So when we designed our circuit, we designed it and we have an OR gate, we got an OR gate, we got an AND gate, and we're like, we don't have that. We've got a bunch of AND gates and like only one OR gate. So we say, okay, well, let's use De Morgan's law on this. So again, we add our 2 bubbles to it. We push one bubble through, the AND turns to an OR. Now we got 2 bubbles here. The bubbles come here. We push those bubbles through. That turns both of these ORs into ANDs, and then we have bubbles all on the inputs. Here we go. So now we got AND, and then this is an OR with an inverter on the output, which is a NOR, right? Okay, so we can call it an OR, or we can call it an OR with an inverter, or we can call it a NOR. And then here's our inputs, and then notice B is no longer inverted because it got doubly inverted, right? And so now there's B. So now we've got a sum of products again, all right? That's De Morgan's laws. That's all there is to it. So it's really important to just know that these things exist. So when you go designing a circuit, and you're some people think in one way, like they think in terms of this expression, or this, or this, or this, or maybe you're thinking and this, and this, and this. Just like when you write code, right? If you write code, you can do it either way. And it works in code too. So if you're doing programming, right, and you have if A, and B, right, that's the same as if not A or not B. Try it. I guarantee it'll work. So it allows you to invert things, and then now here's the kicker. Say you've got, talking about computers, say you've got a computer architecture that can evaluate ANDs or ORs differently. Say that an AND or a compiler. Say the compiler generates a lot more code when you have conditional logic that has ORs in it. So the compiler and maybe even the processor architecture likes AND expressions. So if you could transform as much into AND expressions, that's way better. That's going to get you faster compilation and faster code execution. So that's another reason why this is important. And also, sorry for saying the word and, but you have to. Additionally, the actual gates themselves could have a different speed. Let's take a quick look at that. Just for curiosity's sake, all right? So let's go here and let's look at a 74, let me see if I have this, 7408 is a 2-input AND gate, all right? So we'll take a look at one of these. Now remember, modern technology is LV or LVC, so we're not going to look at that. We're going to look at older technology. So we'll look at a Texas Instruments good old 74 LS08. And what we're going to look at is the propagation delay. All right. Propagation delay. All right. So this is unsearchable, I believe. Yeah, because it's graphic. So let's go back up here. We'll just have to go to the data sheet here. And all right. So what I'm looking for is the propagation delay and electrical. Here we go right here. So this is a T propagation, low to high and high to low. What that means is if the AND gate is high, how long does it take to go low? If it's low, how long does it take to go high? Typically it's symmetrical, but sometimes it's asymmetrical. So it's showing here that a low to a high is 17 nanoseconds and 27 nanoseconds maximum, but a high to a low is 12 and 19. It's faster, which is interesting. So we'd like to spend our time going high to low. In any case, the bottom line is we've got a 17 and 27, a 12 and 19 for the AND gate. All right, so 17, 27, 12, 19. Remember that for a second. Let's go look at an OR gate, a two-input OR gate. So a two-input OR will be 72 LS32. Again, let's look at Texas Instruments. So we're comparing apples to apples. There we go. Okay, two-input OR. Again, these chips are so old, they're graphic. This is a bitmap. It's been scanned in, you can see. Let's scroll down here. Again, shows the circuit design. If you're crazy and want to build this, aha! So this is interesting. So the low to high and high to low is 10 and 15 and 14 and 22. On the other one, look at that. It was 17 and 12, 27 and 19. So 15 and 22, 27 and 19. So one of these is faster. Which one is that? This one is. So the OR gate is faster. So if we can do something that uses more OR gates, we want to do that because we're going to have faster propagation delays and we won't have to wait. Those AND gates are slower. So this is why knowing this stuff is very, very important if you want to do crazy level optimization. So again, say I'm doing something, say we're building a computer and we're building a circuit and we've got a microcontroller, all right, like a Raspberry Pi or an Arduino or whatever, and we've got some circuit and we know that the processor is going so fast and we want to do this computation electronically, we want to do something electronically, we look at the propagation delays, we're going to add them all up and we're going to say, wait a minute, we won't be able to do this because when you add all these propagation delays up, it's going to be too long. It's going to take too long for how fast this processor is going or whatever. We got to do it faster. Well, wait a minute. Can we turn our ORs to ANDs or ANDs to ORs? Right? And yes, we can with De Morgan's law. And then in this case, in the LS technology, the OR gate is faster. Maybe in a different technology, say LV or LVC, the AND gate is faster, right? So you would look at that. But this is a level that if you want to get down and optimize, you need to know this math and these things so that you can do that. And again, just know it. Just know that it exists so you can say in the back of your head, I know I could make this faster. There's some law or something I read. You can go back and always figure it out. But if you don't know this, then some other person can make this circuit go faster. And you're, how are you doing this? That's what happened when the Apple II computer was made, right? Or the Apple I computer, Apple II computer. It was so optimized. Steve Wozniak optimized that computer so crazily. Just every day he was like, I can get rid of one chip, I can get rid of one gate, I can do this. People could not understand how he put so much into so little. There's like so few chips on it compared to these other computers with all these boards. This is how he did it. And that same way of thinking, that same paradigm works today with anything, with code, with electronics, you name it, you can still optimize it, all right? And that's important to do. All right, so let's go back to our text material here. All right, switching standards and logic families. So let's go ahead. We've talked about this before, so we're going to go through this pretty quickly, but let's go ahead and stop here. And this is a good place to stop. De Morgan's laws, remember them, and play with them and experiment with them. And we will come back in another lecture and start on this other material. So I'll see you in the next lecture. Bye. All right, welcome back, and we are continuing on with the material here in Chapter 4, and we are going to be talking about switching standards and logic families, which we've kind of discussed this before. All right, and we'll see how far we can get in this lecture, and we'll probably break this up into 2 or 3 lectures. This material. But before we do that, let's go back to the blackboard here, and let's go ahead and do a quick quiz on De Morgan's law here, and see if we can remember what we were doing here. I just want to make sure that you guys get this, and I wanted to just kind of put a couple examples. So the whole idea is let's forget about the math part of it, and just remember, OR gates turn to AND gates turn to OR gates, and we just have to invert signals. And let's just do this totally with bubble pushing. So we're just doing De Morgan's law or De Morgan's theorem here. So let's say, for example, we had a circuit, and let's start off and let's kind of draw this. Let's say that we have 2 inputs here, and they're going into an AND gate, and I'm going to call this A, and I'm going to call this B. All right, so that says A and B, and take that, and we'll take the output of A and B. And let's see, let's do another couple things here. We'll do, how about we'll take C, and then we'll also take D, and then we're going to invert D like that. All right, so this signal right here is D naught. This ends up being D naught, right, this signal. So we've got those, and let's see, A, B, C, D, and let's also bring in E, and here's E. So if A and B, or C and not D, or E, those are the 3 different cases that we want this signal to be high. All right, so then we basically just go like this, and we're just going to draw this OR gate here. All right, and then kind of do this kind of thing. So here's our OR gate, like this. Okay, and we can put multiply times each one of these and OR here. Now, there's a couple quick things I want to show you. So how many layers or how many levels is this gate network? Well, it's 2 layers. Here's layer 1 and here's layer 2. All right, and so if we go like this, kind of go like this. So for the signal to propagate through this entire network, first it's going to have to propagate through the AND gate, and then it has to propagate through the OR gate. And remember, we looked at the AND and we looked at the OR and we looked at their propagation delays. All right, so regardless of what they are, we're just going to say a number right now, just for fun. We'll say that this is 15 nanoseconds to get through here, and we'll say that it's 10 nanoseconds to get through here. So as we put the signals on A, B, C, D, and E here, the entire network is going to take a total of approximately 25 nanoseconds before we get our output here, which we'll just call this Z. All right. So now someone says, well, I don't want to use AND gates, I want to use OR gates, and I don't want to use this OR, I want to use an AND. All right. So what we're going to do is we're going to do this whole bubble pushing thing. All right, so let's use a color that's really has a lot of contrast. So what we'll do first is we'll put 2 bubbles here. We can't just put 1 because that would change what the whole meaning of this is. All right, so now as I push this bubble through here, it switches the gate. So if it's AND, it's OR, it's OR, it's AND, and then the bubble comes to the inputs here. So we're just going to kind of mimic this. So here's an OR gate, so this is going to turn into an AND gate. So there's our AND gate. All right, and now we've got these 3 inputs right here. Now each one of those inputs gets a bubble on it. So we're just going to put a bubble on here, put a bubble on here, put a bubble on here. All right. And now you see we had an AND here. So if I take that bubble and I keep pushing it through, right? So if I take the bubble and I keep pushing it through, this first AND, as I take this bubble and I push it all the way through, is going to turn this into an OR gate. All right. So that's going to turn to an OR gate. This one's going to turn into an OR gate with the bubbles on the inputs. So, well, as a matter of fact, let's just leave that like that. All right, and then let's show, we're going to take this bubble here, we're going to take this bubble here, All right, and then we had an AND gate here as well. So we're just taking these little bubbles and we're pushing them here. There they are at the inputs. All right, and now I'm going to push it through the gate. And as I push the bubbles through the gate, so I'm going to take it and push it through the gate. Just erase those. It's a little bit tricky doing it like this on here, but so now it turns it to an OR gate. This one also turns into an OR gate. And now those bubbles go on to the input. So now we have a bubble here, we got a bubble here, we got a bubble here, we got a bubble here. Okay, let's get our green back. Okay, so now we have A here, we have B here, we have C here, and we have D here. But remember, we had D naught. We already had a bubble, so we'll just kind of put this other bubble here. There's already a bubble there. All right, now this this bubble just stays there, and this is just still E. All right, so now this is really, we're going to put E naught inside of here to get this signal. So we're going to put E naught, and if we put E naught, we can get rid of this bubble. All right, we can just erase the bubble if we want, but I'm going to leave it there just to kind of show that what we're going to do is we're going to put E naught, and there's no bubble, or we can think of this as E with a bubble. Either way, we have to invert it. All right, so now these two bubbles, these are going to cancel out. So now we've got no bubble. So now what we have here is just plain D. So we just have plain D here, oops, just like this. All right, and then like I said, what we can do is if we want to push all these bubbles all the way, and we can invert what these variables are. So we can go ahead and we can say A naught, B naught, C naught, then we can erase these bubbles. So if we have those signals, so I'm going to kind of mess this up a little bit, and I'll fix it. Okay. All right, that's not bad. And then this right here really looks like this at this point. Right, before we just had E, now we've got E with a bubble, so we could send in E and then take out the bubble. All right, and then now over here, we've still got one bubble. We only pushed one bubble through here, so we still need inversion here. And then the final output here, Z, is still Z. All right, and then that's it. So you can see the OR gate turned into an AND gate. Then you can see as we push the bubbles, the ANDs turned to ORs. Then all the variables got inverted, A, B, C, and then D got inverted again. Now we just have D. All right, and then be careful here. Technically, this is not D naught and a bubble. What I'm trying to say here is this is going to turn this into D naught. So if we want to be very correct here, what this really looks like is like this, and I'm saying there's D, but since there's a bubble on it, this is equivalent to saying D naught. We could take out the bubble if we want, but I just want to emphasize that when that signal comes in there, it's coming in as D naught. So either way, you can put D naught here, or you can add the bubble here and kind of erase the bar over it. All right, there's not really a bar at this point if you put the bubble there. But I just want to emphasize that this variable is either inverted or we had an inversion on the input there. But anyway, so that's the whole idea of De Morgan's law. It's really simple. You just push these bubbles. Now the other thing is you can push them in the other direction too. So real quickly, say that you had an AND gate here, and then say that just for kicks, say you had A naught and B naught kind of coming in here, which really means that you have A, and then you have an inversion here, and you have B, and then you have an inversion here. All right, so these two things are equivalent. Right, so then what we can do is we can take A and B here, and we can push these bubbles through here, and then this whole thing is equivalent to this. and now we'll get an inversion on the output. And then we still put A and B here. So the AND turned into an OR, and then these two bubbles push through, and then we end up with a bubble there. All right, so these are graphical methods to do this De Morgan's law. That's all, just graphical methods to do it. Okay, all right, cool. So, all right, let's get back to the information at hand. I just want to do that because we kind of already went through this these few pages here. So again, we're in chapter 4 here. Kind of find your way in here, but we're talking about this whole concept of switching standards and logic families. All right, so let's just again, I want you to read this. Take your time and read it. But we're gonna go through it right here, and I'm gonna kind of talk you through this to give you some context. So there are many logic families now, right? So these are not all there are, but these are some of the main ones. And there's the 5-volt TTL, transistor logic, and then CMOS, complementary metal oxide semiconductor, and then low voltage TTL, and low voltage CMOS, and lower voltage CMOS. Then all these little acronyms stand for different things. And these are all the different voltage levels, the lows, the highs, the noise margins, and so forth. And we've talked about what these things mean a bit. VOH, VIH, V, T, V threshold, VIL, VOL, etc. So we've kind of talked about these, all right? And typically you're going to use 5-volt systems or 3.3-volt systems. Most of the time these days you'll use 3.3-volt systems for your discrete electronics, and then processors may run down to 2.5, 1.8, or 1.2 volts, all right? Okay, so the two main families are TTL and CMOS. We've talked about that before, and they're variations of both. All right, 3.3 volt low voltage TTL, for example. All right, and let's go through here. And then some of these versions, you can kind of figure out what these acronyms mean. So HC, for example, means high speed CMOS, and then HCT means high speed CMOS TTL, so it can tolerate TTL inputs. All right, so some of these things you can kind of figure out. Otherwise, just kind of memorize them or look them up or just know they exist. That's half the battle with this. There's just too much to remember, and it changes constantly. So just know that these things mean something. You can look them up on your data sheet or your books and all that kind of thing. We've talked about reading data sheets before. We've been reading them, we've been looking at them, so we've been learning how to read data sheets, all right? And so typically data sheets have, you know, the picture of the chip, its pinout, package options, description, functional descriptions, application notes, how to use the thing as examples, both AC and DC characteristics, meaning AC meaning non-static characteristics and DC static characteristics, all right? All right, and then just some references that we don't really care about there. All right, and then we have a couple gates right here. So we've got an inverter gate and we've got an AND gate. And so this is just a little figure kind of showing some of these values, some of these symbols, what do they mean? So you got two inputs, X and Y here. And this inverter has a propagation delay, we call that TPD, propagation delay, time for propagation. And whatever that number is, that's how long it takes a signal to get from this end of the inverter to this end of the inverter, from the input to the output. And this AND gate has a propagation delay as well. Again, from these inputs to the output, that's its propagation delay. They're not equal, all right? I'm using the same symbols here, but they're not equal. They're two different things. And then, when this inverter is driving this output here, we got a couple things. So V output high, V output low. So what is the voltage when it outputs a high? If it's a 5-volt system, it's around 5 volts. If it's a low, it'll be around 0 volts. If it's a 3.3 volt system, it'll be around 3.3 volts, V output high, and it'll be around 0 volts when it outputs a low. But it doesn't necessarily have to be that, and that's what these charts tell you. So these are the maximums. So this is V output low, V output low, V output low. Here's V output high, V input high. So here's all these different ranges of these imperfect ICs and showing you that they're not perfect. So in a perfect world, V output high, right, would be 5 volts. But this is saying it can be anywhere above 2.4. I guarantee you it'll be 2.4, but that's all I guarantee you. So that's kind of bad, right? So we really would love it to be 5 volts, but this is the maximum guarantee for this logic family is the output high is guaranteed to be 2.4 volts, and that's it, all right? So let's go back down there. So that's what these things are all about, and just showing what they are. And then we have V input high, V input low. That's the opposite sense. That's what do we need to detect that this is a high or assert a high, and same thing, what do we need to assert a low? Then we have these things, the I output high and I output low. So these are the currents, right, which can flow into, so this can source current or it can sink current. So when you're outputting a high, you're going to source current. That's I output high. That's how much current I can source. Now, if I'm putting out a low, a 0 voltage, current is going to flow into this device because this will be a higher voltage. That's I output low, all right? So that's I output low, all right? And then there's also I input high and I input low, all right? So there's every version, every possible variation of this. That's what these data sheets tell you, all right? And then going through here, this is actually not bad. If you can find references that have all of these things labeled out, but here they are here. So V output high, V output low, V input high, V input low, and so on. You can just read through these. I'm not going to read them. You can read these. Now, these propagation delays are sort of important. So there's all kinds of different propagation delays. There's a total propagation from one end of the IC to the other, from input to output. That might be just TPD, T propagation. All right, but then there's also T propagation high uh, to low and then low to high. So that's saying if you're at a high, how long does it take to get to a low? And if you're at a low, how long does it take to get a high? That's all that is. And it may be asymmetrical. There may be some hysteresis going on. It may take it longer to go in one direction than it does in the other direction. And we proved that, right? We went and looked at, if we can find it, yeah, say like this 7432, right? This OR gate. And if we look down at its propagation delays, where did they go? They're right here. So we've got 10 and 15, we got 14 and 22. They're asymmetrical. On average, they're 40% different, right? So they are not the same, all right? Okay. F max, sometimes you'll see this, and this just means the maximum switching frequency. So this would be T high to low plus T low to high plus some propagation delay. You add that all together, you invert that, and that's going to be the maximum frequency. And TA, temperature ambient, the range of ambient air temperatures the device can operate without external heat management. So this is just saying anything hotter than this, you're going to have to pull heat away somehow because it's going to get too hot. So there's a lot of stuff about heat, which we're not going to get into too much. Just keep these things at room temperature-ish or up to 100 degrees Fahrenheit or so. They'll be okay. After that, you have to start worrying about them getting too hot. 110, 120, 130 degrees Fahrenheit, you're going to start cooking things a little bit. All right, but these ICs can actually take quite a bit of temperature. But the hotter they are, the faster they fail, right? So you really shorten their lifespan by running things hot. Now, CMOS data sheets are different. So since CMOS are not based on standard junction transistors, PNP, NPN types of transistors, they're based on FETs. So they're not current devices, they're voltage devices. And because they're voltage devices, and remember what a FET looks like. A FET basically is a capacitor, right? It's got a gate, and then you apply the voltage to the gate, and that causes, remember, the channel gets small, and you cause charge to move into the channel, and then from source to drain, current can flow, remember all that? So it's basically little capacitors. So what we care about with CMOS is capacitance. All right, so some of the things you might see in CMOS data sheets, V sub CC is the supply voltage. All right, we've seen that, we've used that term before, and some of these terms are kind of old. You know, V sub CC, V sub D, V sub DD, V sub E, and some of them come from the 30s, the 40s, the 50s when we're talking about vacuum tubes and stuff, and that's where that labeling kind of came from. You're like, where did V sub DD or V sub C or V sub CC? Where's this all coming from? It kind of comes from that back then when they were dealing with vacuum tubes and they had all these different voltages and they labeled them, and that kind of transitioned over into kind of modern semiconductor stuff a little bit. All right, fan out. What this means is how many ICs can the CMOS device drive. So typical fan out is 5 to 10, meaning you can drive 5 to 10 other standard CMOS devices of the same family. All right, so and the other thing that is going to be important is how much current. So remember with the TTL stuff, two things. The fan out, you're going to have capacitance, which you need to worry about, and then the fan out itself is how much current this thing can drive. So remember, CMOS devices don't need current, but TTL devices do need current, all right? So we got to be careful what we're hooking up with CMOS and driving with it, make sure we have enough current. All right. Same thing. They have a lot of these same V output high, V output low, V input high, V input low. Now, Because they're voltage devices and not current devices, they do not need current to be driven high or driven low, all right? So there's no input I low and input I high and input output high and input output low. We don't have those, but what we do have is this input leakage current. So the transistors, the FET transistors, the field effect transistors are not perfect, and they have some leakage current. And these leakage currents are microamperes or nanoamperes or picoamperes, but they do make a difference. So you have to concern yourself with that. All right. But they don't work the same as transistors, standard junction transistors, so those currents you don't care about anymore. But what you do care about is the input capacitance of things and what the drive is. So here, this says the input capacitance, this is the amount of capacitance a CMOS input has. It's on the order of 1 to 10 picofarad. So when you have a CMOS device, it'll say how much it can drive, and it can drive like 50 picofarads. So if it can drive 50 picofarads, all right, then that means that you could drive like 5 of these devices, all right? So the load and the load capacitance is what that is. This is the amount of capacitance a given CMOS output can drive. All right, and it can typically drive more, but this is how much it can drive before things are going to start drooping and not working right. All right, again, here's those propagation delays, high to low to high, F max, same thing, temperature ambient, same thing. So really these are very similar, except the currents, the input and output currents when you're driving things go away. That's not important, but the capacitance is important because these are capacitive devices and they only can drive so much, all right? Okay, let's see here. TTL loading concepts. So this is, and we've talked about this before. I don't want to go, again, too much into this, but this is the whole idea is when you have TTL, right, these are transistors, PNP, NPN, and they need current to be turned on, right, and turned off, right, and they also output current. You drive the next stage with current. So this concept of TTL loading is what this is all about when you read this section here. All right, so this is kind of showing, again, another graphical TTL output high and low situation. All right, so, okay, so in this situation here, we've got one TTL inverter and another TTL inverter. And this is showing exactly where the currents are, what is going on. So we've got one inverter here, it might be a 74 LSO4 package and another 74 LSO4 package, a sixth of each one, so this might be a hex inverter, right? And so each one of these are kind of individually wrapped. So we've got them hooked up to the same power supply. So on these ICs, they've only got one power connection, one ground. So they all get the same power, the same ground, right? All right. So now let's just say that we just hooked them to each other, right? So inside of this package, and let's take a look here. And let's see if we can find our inverter here quickly. 74 and 555, and that's another 555, and here we go, right here, here we go. So here's our 7404 inverter, and that's what each one of these look like. Now this is an HC, but the LS is the same thing. But what I want to show you is the package, and so it's here's one here, so here's one inverter, another inverter, another inverter, so it's in, out, in, out, in, out, in, out, all right? So back in the pages of the book there, what we're looking at is something like this. So we just have our 74 LSO4, all right? And we got pins here 1, 2, 3, 4, 5, 6, 7. And we got 8, 9, 10, 11, 12, 13, 14. All right. This one is going to go up to V sub CC. This one is going to go to ground. Ground. All right, this is pin 1, 2, 3, 4, 5, 6, 7. This is pin 8, and this is pin 14. All right. Now, what's in here looks like this. It looks like this. There's an inverter here, just like that. There's another inverter here, just like that. Another inverter here, just like that. And then another inverter here, and it goes in the same direction here, like this. In, out, like that. And this one's like this, like that. And finally, this one goes like that. And you can look at that in the data sheet, right? So what we're doing right now, when we're looking at this drawing right here, is if you can imagine, we've just taken this and connected it right here. And then here, this becomes our input, So this is our input here. So here's in, and then here's our output right there. So there's our in and there's our out. So we've got kind of this situation going on here. So we've got two of these inverters. There they are right there. All right. So that's all we did. We could just do that and we could start measuring this stuff. So here's the deal. So say in the situation that you're outputting a high. So this inverter is outputting a high. Okay. So the I output high, it can output 0.4 milliampere max drive in this situation. All right. And I input high, this requires 20 microamperes to drive it high. So we definitely got 20 microamperes. 0.4 is much larger. That's 400 microamperes. So we're good there. All right. And now what's going to happen is this current is going to flow from the power source here. It's going to flow through the electronics of the inverter into the input of this, and then it's going to go sink down to ground. Okay, so this is kind of the flow of current and the flow of signal in this situation here, right? So we're outputting a high, and then so if we output a high here, a 1 here, we got a 1 here, we're going to get a 0 here, right? Now, here's the case we're outputting low, and this is a little bit tricky. All right, so we're outputting a low. If we're outputting a low here, we're outputting a 0 voltage here. So now what's going to happen is current is going to flow from the source here through this inverter, through its input, back this direction and sink down here. Now this is called I output low, and it says it's 0.4 milliamperes, all right? So this is this, and I input low is minus 0.4 milliamperes, okay? So one has got a minus sign, one's got a positive sign because one is going this way and one is going this way. So this one is sourcing negative current, this one is sinking this positive current. So that's what these two symbols, IOL and IIL, mean, all right? And then what's the maximum this can sink? 8 milliamperes. All right, so 8 milliamperes. So we only need 0.4 milliamperes to drive this thing low, but here's where the currents go. So this is kind of important to understand. There's no magic going here. Where are these electrons and holes coming from? They're coming from the source, they're coming from the ground, they're going into the ground, going into the source, and that's all there is to it. So that's what this whole concept here we're talking about, this TTL loading, where are things going, and that's that. So this example talks through what we just did. All right, so you can read through that. CMOS loading is the same kind of thing, except we're dealing with capacitance now, right? So capacitance becomes the thing that we're worried about. We don't care about current anymore. So say if we have a CMOS type gate, like an HC, a high-speed CMOS, or a version, another low voltage TTL version, or low voltage version that's a CMOS, right? So we read these things and we see what these things can drive, right? And then we read about their capacitance driving. All right, so now this, so we've got an output here, and how much capacitance can this drive? Well, every one of these HC gates basically looks like a capacitor to this output, and so it can only drive so many gates, and so we have to make sure we're only going to connect it to that many gates, otherwise we won't be able to drive it. All right, and that's what these things, the CL, the C load, and the CI. The C load is how much total capacitance can I drive? Maybe it's 50 picofarads, maybe it's 100 picofarads, don't know, got to look at the data sheet. And CI is the C input, that's what this gate looks like as far as input capacitance. So when you hook these things together, you have to have enough drive to drive all of these gates. If you don't, because remember they're capacitors, they're going to take time to charge up, and you're going to violate the timings of these ICs. So these ICs, the specifications in the data sheet are based on these rules being maintained. You can violate them, it'll still work, it just won't work as the data sheet says, right? So go ahead, take an output and connect it. Maybe you can connect 10 ICs to it, so you can take one output and fan it out to 10, right? Maybe that's what the data sheet says you can do. Hook it up to 20 and then push the speed up, and you'll see you won't be able to maintain that speed, all right? Okay, and then when you mix TTL and CMOS, you got to be careful of that, because in one case you need current, in the other case you need voltage, and also the voltages are slightly different, all right? And here, these are, and of course, there's many technologies now where these are very slow. 9 nanosecond, 22 nanosecond, very slow. So you can get things that are way faster. You can get things that go, sub nanosecond, no problem. All right. Tri-state logic. Now this is kind of important. So let's take a minute to talk about this. So what tri-state logic means is, when we have our IC, we've got inputs and we've got outputs, and maybe we want to connect something together. We want to tie two outputs together. But because they're both being driven by transistors, if we just connect them together, something bad is going to happen, right? We're going to short them together. So if one is high and one is low, or one's low and one's high, they're going to short, we're going to have a problem. So on the actual output architecture, they have extra transistors that basically disconnect the outputs. So they tri-state them, right? They go to infinite impedance or very high impedance. So for all intent purposes, these things have infinite impedance and they've just been disconnected. So for example, if you take a look at this little figure right here, here's a typical, this is just a buffer. It's got an input X and output Y, and then it's got this little extra thing here called the enable. And this enable, when this enable is on, this thing will just act like a buffer. So X will go to Y. So when the enable's on, that's this middle column here with the ones. Excuse me. This is active. This is active. This is active low. All right, so this is active low. So if we've got the enable, and that's what the bar means, so it's active low. So if it's high, that means the IC is not active. So now you basically turn the output high impedance. That's what these Z's mean. So Z just means, it's another symbol. A lot of times it means output, but Z means high impedance. So it just means infinite impedance. So if this enable is not asserted, right? And asserted in this case means a 0, right? So that's why there's a bar over it. It means to turn this thing on, you got to put a 0 on there. If you put a 1 on there, then it turns the output off. And if you try and connect something to the output, you're not going to get anything. You're just going to get infinite resistance. Now, when you enable the tri-state buffer by putting a 0 on this enable line, then 0 outputs a 0, 1 outputs a 1. That's all it does. I know it sounds simple, but it's very, very, very useful, okay? And the reason why is because you can connect things together. So here's an example. So say, for example, we have two serial inputs, two RS-232 signals. So we've got two TTL RS-232 signals. And what we want to do is, one of them is coming from one computer, one's coming from another computer, and I want to be able to select which one of those are going to some kind of output or something like that, all right? So what we do here is we just tie them together. Now the problem would be is as the serial data came in here, it would cause shorts and all kinds of problems because as one went high and the other one went low, we've got these things wired together. You can't just wire gate outputs together. That won't work, right? You'll short the transistors and burn them up and cause all kinds of problems. But if you have these output enables or these tri-state controls on them, now we can take this tri-state control and this tri-state control, and here's a little switch, and all the switch does is just switch which one we enable, all right? So in one position we enable this output, and then so what's going to happen is we're going to get this output here, we put the switch in the other position, and then this will output. Now, this is still staying on. We're not turning the power off of it. We're not turning the power off. All we're doing is disabling or enabling this output enable so we can tie these together. So we could tie a bunch of these together. So in theory, for example, say for example you had a TV signal, an analog TV signal. You could get an analog switch. It's called an analog switch, and it would have an enable, and you could tie a bunch of these together and have one for each composite video signal. And then by enabling one or another, you could basically route which video signal went to a single output, all right? But it has to be an analog switch because it's an analog signal, all right? So you can read through that, and that just kind of goes through that example. Okay, so the next thing that we're going to talk about are timing diagrams, and this is fairly complicated, so I want to spend some time on this. So what we're going to do is we're going to go ahead and we're going to stop this lecture right here, and then we'll pick up and we're going to go and talk about timing diagrams and just give you the language and the notation conventions of timing diagrams also, which again is kind of tricky. All right, so I'll see you in the next lecture. Bye. Hey everyone, welcome back, and we are on the next lecture here doing our digital coverage, and we're just basically going through the language and some of the concepts before we dig into a bunch of different ICs and playing with them. So we got to learn how to discuss various concepts with digital electronics, just like we did with analog, and it just get the vocabulary for it. And so now the next thing that we're going to talk about is a timing diagram. So here in the book, our book that we've been going through, we're in section 4.6, chapter 4.6 here, and we're going to talk about timing diagrams. All right, so let's jump right into it. Timing diagram is basically, and then all ICs are going to have timing diagrams, and some of them may have it in the data sheet, or they may not publish it in the data sheet, but still at some point someone created a timing diagram or figured out the timing of the IC, obviously, since they designed the IC. So in the data sheets you're going to find these things called timing diagrams, and what these do is these kind of describe how the IC works and the timings from the inputs to the outputs and so forth. All right, so that's why this is important. It's something we have to be able to read, and surprisingly, a lot of people don't really know how to read timing diagrams that well, especially if they haven't done like a formal engineering degree. So it's pretty important just to be able to read it a little bit and kind of figure it out. And some of it is pretty cryptic, but at least the basics are important. All right, so let's take a look here. So this image right here that I'm looking at is just a square wave, all right? And obviously it does not look like a square wave, right? And we've seen on the oscilloscope as we play with our various circuits that we've been building so far, square waves really aren't square waves, right? They're more like trapezoids. There's a rise time, there's a fall time, there's a little bit of overshoot. Once the voltage gets to whatever the level it's supposed to reach, it doesn't just stop there perfectly, it overshoots it, and then it kind of comes down and it stabilizes it. It may ring a little, there may be some ringing in here going up and down, and then it falls, it undershoots, and then it goes up and goes down and rings a little bit. So the real waveform is pretty messy, but these overshoots and undershoots are on orders of millivolts or tens of millivolts usually, so we kind of ignore them. And this rise time and this fall time, right, as compared to the perfect square wave, is usually pretty small too. It might be nanoseconds, maybe it might be microseconds. It was a very slow system, but typically it's nanoseconds, all right? But nevertheless, this is really what the waveform kind of looks like, of just any kind of little square wave going on. So first thing is we've got this thing called rise time. And you'll see in timing diagrams, you'll hear the word or the phrase, something will say the rise time or the fall time. And that's what is being discussed when they're saying rise time and fall time. What's being discussed there is how long or how fast the waveform rises. So this leading edge is the rise time. And typically it's from the 20% mark to the 80% mark of whatever the voltage is of the system. So in this system right here, say this was 1 volt, and we had a 1 volt system where this is 100% signal. At 20% of that is one mark, and at 80% would be another mark. The time it takes, so if you were to drop down 2 verticals here, and this is time on the horizontal axis, and measure that amount of time from 20% of full signal to 80% of the full signal, right? That is the rise time. Similarly, the fall time is from 80% down to 20%. All right, so that's rise time and fall time. All right, now another thing, let's see if we can find another good picture here. Yeah, so using the 50% mark to measure delays. So like if you want to measure one waveform to another, so in this picture right here, what we have is we've got the horizontal axis, which has time. The vertical axis again has voltage or the signals. There's 2 signals here. And in these cases, we're labeling them as 0 and 1, 0 and 1. So we're not showing this as a voltage. The 1 maps to a voltage. It might be 3.3, it might be 2.5, it might be 5 volts, right? But we're just abstracting it as 0 and 1 in this case. So in this case, then we might ask the question, what's the delay from S1 to S2? All right, so now what's the delay from S1 to S2? Well, what do you mean? Do you mean when S1 is high and S2 is high? Or do you mean when they're starting to become high, or when they're low, or when they're starting to become low? So we have to have a frame of reference. So typically what's used is the 50% mark. So on this rising edge or falling edge, it'll be the 50% mark of the rising edge, all right, in the 50% mark of this rising edge, and that's where you'll figure out what the time is. So you'll drop down and look at what the time is there. Maybe it's maybe this was 6 nanoseconds here, and then maybe this is like 20 nanoseconds here. So then this delta t would be the 20 minus the 6 nanoseconds. But the whole idea is you have to have a common frame of reference or a convention, and so we'll use the 50% mark, right? So looking back up here, this would be the 50% mark. So if someone wanted to say, hey, what's the time from one waveform to another waveform to compare them, you would just first go out to this 50% mark, you would drop down, and that is the time reference. Because since this thing changes over time, we have to pick something, right? And so we could pick this, we could pick this, we could pick this middle maybe. That really wouldn't make sense. So what we do is we pick this 50% mark, because ideally, this edge right here happens in 0 time, right? So it's almost 0 time, but it could be high for a very long time. It could be low for a very long time. But the rising edge and falling edge in a digital system, typically or ideally, we want these things to be 0 time, right? But they aren't really, because there's capacitance, and that's why you see this capacitive kind of effect here, this charging and discharging curve, all right? Okay, so that's kind of the 50% rule for measuring things. Now, here's another timing diagram, and we're just going to kind of look at some of these symbolisms here. So again, in this case, we got 1 and 0. This really represents a voltage, 3.3, 5, 2.5, 1.8, whatever the digital system is. But we're abstracting it to 1 and 0 just to mean high and low voltage. All right. Now, as you read through timing diagrams, depending on who makes these timing diagrams and what the IC is and the manufacturer and what year it is and so forth, you'll see some little, kind of some different conventions now and then, and sometimes you're like, what is this? It's almost like if you get a degree in math and you get a degree in physics and you get a degree in, say, electrical engineering, each one of those different fields has slightly different mathematical notation, and if you, like electrical engineers call imaginary numbers J, mathematicians call them I, right? And the same thing with timing diagrams. Different companies kind of have their own little conventions, and they draw things a little bit differently sometimes, so you get a little bit confused and just kind of read through and figure it out. So some of this text here, these handmade figures are a little bit hard to read, but this says tri-state right there, but it's kind of these quaint figures that were hand drawn when I did this book. So anyway, so in this signal right here, this is a representation of just some signal, and here it's low, and then here it's going from low to high, and that's that transition, right? So we showed as this kind of trapezoid. And then we might say, you know, how long this is. There might be a T, some kind of timing in there that says, and it might be called T rise, right? T rise time, and that would be that delay. And then the signal is high for some amount of time, for whatever reason it is. And then here's it going low from high to low. There it is low again. All right. And then depending on the convention, when the signal is drawn between high and low like this in the middle of the vertical range, typically that's tri-state. And again, what tri-state means is the impedance is high, right? So it's got infinite impedance. It's like, it's not going to draw any current or put any current out, right? So Z is like megohms or, tens of megohms, that kind of thing. Okay, so that means it's tri-state. And then here would be a low to tri-state, and then here would be tri-state back up to high. So in other words, the output was tri-state, so it had infinite impedance. And all of a sudden, I want to drive it high, so it turns to an output, and then it drives high. How long does that take? And the same thing, you were at a low, and I want to tri-state it. How long does it take to get into tri-state mode? All right, so that's kind of what this one is showing here. Now, this one here is a little bit more complicated. All right, so first we start off in the middle here, right? Again, we're in the middle of the range, right? So the 1 would be up here and 0 would be down there, right? So we're in the middle, which means we're tri-state. Then this funny little thing here, what does this mean? So typically this means that the signal will be either high or low, or it's a set of signals. It could be a bus, right? And when we're doing electronics, when we group a bunch of signals together, we call them buses. And there's data buses and address buses and control buses and all that. So this might represent a single signal that could be either high or low. You don't know what it is. Or it just could be a bus, and it represents n signals. And it's just saying there's a bunch of signals in here. I'm representing them symbolically. They could be any value. I don't really know. But it's going to take this much time here to rise up or to go down to a low. And then for this time, those signals are going to be stable, whatever they are. Then they're going to go back tri-state. Now, uh, this is an interesting symbol right here, and you'll see this. So what you'll see is, so, here's the wave and it's going down, but then it's going down, 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 down. So what does that mean? What that means is in this time range right here, whatever this is, however many nanoseconds or microseconds or picoseconds or whatever that this is, means that this signal could actually change. It may not change, right, until it gets to here, but it may change anytime in here. So this is saying that this is variable. And so it might just immediately change here, or it could go all the way and finally change here. So we don't know. This is question mark. We don't know when it's going to change, but from this point here in time to this point here in time, remember the horizontal axis is time, that's going to change. Then the signal goes low again, right? We know that it stays low this entire time. Then again, it may change here, it may change here, it may change here, it may change here. It's always going high, but it has this entire time to change, right? So we don't know when it's going to change in that range, right? So that's kind of what that's showing. Then now it's back high. So the whole point is, we just want to be able to look at timing diagrams and first understand the symbology and the terminology, so then we can understand what they have to do with the chip that we're dealing with and its timing. But first we need to know what these symbols mean, right? Okay, so let's see, let's keep going here. All right, now this is important. So there's asynchronous timing diagrams and synchronous timing diagrams, right? So asynchronous timing diagrams, what they have to do with are combinatorial logic. So say if we had our inverter, or we had our OR gate, or we had our AND gate, simple gates, whatever, there's no clock to them. They're not synchronized to any kind of clock. They're not running off a clock. You just put an input to the inverter, you get an output. You put two inputs to the OR gate, you get an output. You put two inputs to the AND gate, you get an output. How fast you get that output is the propagation delay. And if you recall, it was like, 15 to 30 nanoseconds or 25 nanoseconds for the AND and the OR gate roughly was kind of the range. And so that's asynchronous timing diagrams, all right? So these timing diagrams won't have any clock in them at all, because there's nothing that's clocked. Nothing is happening on a heartbeat, right? They just happen whenever they happen. Now here's a little interesting little side note. So all the computers that you are going to probably play with right now are completely synchronous computers, meaning they're based on a clock. So there's a system clock, and it's usually in the gigahertz range these days, right? 1, 2, 3 gigahertz. And everything runs off that clock. The CPU runs off that clock, and all of the chips that support the CPU. Then there's a graphics GPU and processor, and it runs on its own clock, and so forth. But everything is clocked. There are actually asynchronous processors, and companies do experiment with this. And the idea is that, well, instead of clocking everything, we'll just let everything free run, and when the computation is done, we'll get the results. And maybe something will come out of this, a better kind of architecture, a faster architecture, a lower power architecture, because we don't need the clock and so forth. And although I haven't kept up on this in the previous couple years, I know that ARM was experimenting with a completely asynchronous processor architecture. They didn't commercialize it or anything, but I know they were working on one. So that might be something interesting to look up, completely asynchronous processor design. So it does exist, and people are interested, computer engineers are interested in seeing, is this a viable kind of solution to get rid of the clock? And is there some gain if you do that? Anyway, interesting. So in this asynchronous timing diagram right here, let's see. So, this is actually an AND gate. So Z equals X and Y, right? The multiplication is AND. And we've got X, we've got Y. So then we see, now here's another thing about timing diagrams. So you look at a timing diagram and you're like, well, what is this a timing diagram of? Well, what the timing diagram tries to do is, within a finite amount of space, to show you all the possible inputs and outputs you could get in their timings, right? Now, because we're dealing with digital systems, if we have n inputs, right, then we have 2 to the n possible permutations, right? So if you had 8 bits, there are 256 possible different inputs, right? That's a lot of inputs. And if each of those required a timing diagram, that would be 256 pages or more of documentation for something very simple. So what engineers will do is they'll try and pick out kind of a generic timing diagram that kind of shows the flavor of, you know, if one input is before the other or another one is before the other one or they come at the same time, kind of what's going on here in general. And then you have to kind of extrapolate that to all possibilities along with the other information in the data sheet. So that's why these timing diagrams will have kind of funny notation so that you can kind of, you know, figure out this general, you know, say for example, we had something that had a data bus and the data bus had 16 bits on it. Well, I'm surely not going to draw a data bus with 2 to the 16 or 65,535 different 536 with counting 0 combinations of bits. I'm just going to show it all like that other timing diagram we had, that this. We're just going to show it like this. Just it's got some data on it. They could be any value, but what we're concerned about is not their value, but their timing. So the rising edges and the falling edges, right? So you'll see this kind of generalization of waveforms in timing diagrams. So be aware of that and don't let it confuse you. Like when I started looking at timing diagrams, I'm like, what am I looking at? Like X and Y don't make any sense. They're like, they could be, you know, 1 and 0. What's going on here? Well, what I was trying to do is, you don't care if it's 1 or 0, right? That's the function of it. But what I care about is when it's either 1 or 0, doesn't matter, what are the timings? Okay, now, so in this particular timing diagram, X and Y, there's 2 bits, so 2 to the second is 4, so there's 4 different combinations, 0, 0, 0, 1, 1, 0, 1, 1, right? So take a look here at this waveform. Here's X, so we basically have all the different combinations here. So here's when they're both 0, here's when they're both 1, here's when they're both 0, here's when this one's 1, this one's 0, this one's 1, this one's 1, this one's 1, and so forth. So all these different combinations here, all right, because it's simple enough, right? And then down, you know, you see maybe some lines, and then they're showing T0, T1, T2, T3, and then in this case it's saying TPD for the AND. This is T propagation delay. So what this is saying is, so here's X, and X is changing, and then now X is stable high, and now Y is here, and it's changing, and it's stable. All right, and then how long does it take before I get this output here? So here's the output, this is the Z. So as the inputs change, the output changes behind them in time. There's a delay, right? So it doesn't follow them immediately. So you can see here, even though both of these are high, so Y is high and X is high, so Z should be high. Z's not, it's low. It took it this much time to get high. To be driven high, right? So that propagation delay, it had to propagate through the circuitry so that we have the high. Now, the other thing that's important is while we're waiting for it, X and Y better not go low again, because if they go low too quickly, then you'll never get the high out of it. So you'll miss it completely. So the other thing is, that you can see from the timing diagrams is how long signals need to be asserted or deasserted. Asserted means on, and that the on might be 1 or 0. The word asserted is generalized. It might mean 1 or 0 if it's active high or active low, or deasserted means it's off, which again might mean it's a 1 or a 0 depending on if it's active high or active low. Either way, like in this case, when the only time you get a 1 out of an AND gate is when both signals are high or asserted, and in this case we have to wait this much time before we see that signal get propagated to the output. So that's important. That's what the diagram is for. So you read through here and you say, it's I need at least 5 nanoseconds for it to propagate, or 15 nanoseconds or whatever. And then it's just showing, you know, okay, so that one stays high and this one goes low, and then here, you know, here's how the output follows, and that's it. So you can read this and kind of get a visualization of what the information is. So remember, take a look at the information. So here's a 7432, and so here's the 74 LS08 again. You know, this is the actual AND gate, and this one doesn't have any timing diagram, right? But what we're looking at is we're looking at all the propagation going through these circuits, right? But the only thing this thing has are these T propagation low to high and T propagation high to low, and this is how long this stuff takes right here, all right? And then the other general term would be T propagation, TPD, and let's see, and these are for all the 3 different chip families. That's why you see 3 different copies of these T low, high, and high, low. So it's not showing that. It's just showing T low to high, T high to low, and then here they are. So that's where you have to figure that information out. So you could draw a timing diagram just from this information. But it's nice to have the timing diagram, especially if it's more complicated of a chip, right? Okay, let's keep going. So that's asynchronous. So asynchronous just means you're applying signals, there's no clock, and you're just waiting for the propagation delay to propagate and for the IC to become stable and the outputs to become stable for the inputs. You want to generalize it. So the manufacturers want to generalize it. They don't want to write 5,000 different combinations. They want to write 2 combinations and let you kind of extrapolate from there. All right, so that's what you're going to be seeing. All right, now synchronous timing diagrams get a little bit more complicated. So when we're talking about synchronous stuff, we're talking about things that have clocks, like computers and microcontrollers and microprocessors, or what are called flip-flops, which are single-bit memories, or registers, or lots of things. Lots of ICs are clocked. RAMs, memories are clocked. And so everything happens on a clock, on a heartbeat, and whatever that heartbeat is. All right, and because of that, because as the inputs are applied to the IC, they have to sit, at those inputs have to sit there for so much time. Then the clock comes, the clock hits, and then something happens, whatever the chip does. All right, so what's important is that we have to learn some new terminology when we're talking about synchronous systems. So one thing is we're going to learn about a little bit later is a thing called a flip-flop. And a flip-flop there's different kinds of flip-flops. There's T flip-flops and SR flip-flops, set, reset. T stands for toggle. There's D flip-flops, which are like memories, and there's JK flip-flops, which have a lot of properties. They can act like memory and they can invert things. Let's take just a little quick look, and we're going to look at ICs that do flip-flops. So that's why I'm not going to go into this. It's not real important right now to know exactly what it is, but kind of let me show you. So flip-flop is basically a bunch of gates, typically NAND gates, AND gates, inverters, inside of a black box, and they kind of give you a 1-bit memory. All right. So the kind of most useful one that you're going to kind of see a lot is called a D-type flip-flop. So D-type flip-flop, and you see this FF means flip-flop. All right, and then Q, and then Q naught. All right, and then you'll have clock, and then you might have clear. All right, so we could look up a flip-flop IC, and with that might have 1 or 2 or 4 or 8 or 16 flip-flops of different kinds. But anyway, so this is kind of a black box of a flip-flop, and let me show you what this whole thing's all about. So you've got D, Q, Q naught, clock, and clear. So clear does exactly what you would imagine it does. It resets the flip-flop to 0, so it puts a 0 inside of it. And clear is typically active low, so you put a bar over it. And it's asynchronous, so I don't care what the clock is doing or the flip-flop is doing. If you hit clear, if you assert clear, it's going to reset it. So in this little circuit, let's just make a little circuit here. So we're going to make clear. And then what we're going to do is we're going to hook up a little momentary switch here to ground, just like that. All right, and then what we're going to do is we don't want to reset this erroneously. So what we're going to do is we're going to hook V sub CC here, our power, with a resistor, a pull-up resistor, and we'll just make that 10K. All right, that's too small. Let's make that a little bit bigger so you can see it. Okay. So 10K. So there's a little pull-up resistor, so this thing will be not asserted normally, and then we press the button, it gets asserted, it gets reset. So now it can be reset. Okay, great. Now here's where this thing gets interesting. So Q is just the symbol for the output, and there's history behind this which I can't remember. You can probably Google this, why things are called Q in flip-flops. But anyway, it just means the output. And then not Q means the opposite of the output. So whatever this is the invert of it. And all it really boils down to is inside of the IC there's like a buffer, and then all they do is they just take it and invert it. That's Q, and then that's not Q. They're just like, for 2 more cents, I can give you an inverted version of it so you don't have to do it. So you can have that. Also, what's nice is as this thing outputs data, 1s and 0s, right? This is outputting the opposite, like this, right? They're exact opposites of each other, right? And that's very useful for some types of circuits. So that's nice to have that feature. Okay, so all this thing does is this, let's say that we had some data coming in here, all right? And just try and follow this. So let's say we have some data coming in on D, all right? And let's say that the data looks like this. So first thing, let's do this. Let's get a timeline. Let's get a timeline. So we're gonna, this horrible line I'm gonna draw, this is time. Oh boy, do that, there we go. Okay, so there's time there. There's that. Okay, so this is time. Time t on the horizontal axis here, all right? And then this is, 1 and this is 0, this is 1 and this is 0, whatever those voltages are, I don't really care, okay? Now, let's say that this is going to be D, and then this is going to be our clock, okay? So now, let's start off here, and we're going to kind of draw some equidistant little marks here that represent the clock. Okay, so now the clock signal here, and let's draw this, we'll draw this in red. All right, so here's the clock, and let's say that the clock starts off low and the clock goes up high, like this, and then goes like that, and goes down, just like this. So here's the clock signal. All right, do one more here. Okay, so we've got, if you look at this, we've got, here's one complete clock cycle. Here's where it's low right there, and here's where it's high, right? Here's another complete clock signal, one whole clock. Here's another complete clock signal. All right, now let's say that our data, looked something like this. Let's just say that it looked like this. And let's say, it could change in the middle here. And let's say that it looked like this. All right, so here's what data look like. We're sampling some kind of digital signal. Don't know what it is, don't care what it is. Now, here's the interesting thing that happens. What happens is this. Let me find a color here. So what happens is this. On this particular D-type flip-flop, how it's going to work is it's going to sample on a rising edge. All right, so you'll see this little symbol here like this, and that means it's going to sample on a rising edge. And so there are level sensitive flip-flops, which when it's high or low, that's when it samples. And there's edge sensitive or edge triggered, and that means on an edge, typically a rising edge or a falling edge, right? It'll sample the input and then make a transition. All right. So in this case, let's look here. So here's this first rising edge, right? And so that rising edge means it's rising up, right? And then here's the falling edge, right? Okay. So on this first rising edge, we go up here, and what is D? What is D right here? We go right here and we look at it. It's high, right? Now, then we go over to this next one. Again, we go up here. What's D? Right here, right? So we're looking here, we're looking here. That's where it's going to sample it. Then it goes, and we have another rising edge right here, right? Here's another rising edge. Put arrows there. All right, and this one goes, and then in time, so there's the sample point right there. So now what's going to happen is this clock signal, right? This goes, basically connects right here. So we just put that clock right there, and that goes right in there, the world's horriblest little arrow. That connects right to there. That's it. And then this D, this goes right in here, right? Goes right in here. This D signal goes right in here. So now what we see on the output is, first it's clocked. So as this clock is clicking, click, 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 it samples, and then the data that's on this D goes out to Q. All right, so only on the clock we see this Q go. So what's going to happen is we're going to see, come out of this thing, we're going to see a 1, a 0, and a 1. We're going to see a 1, a 0, a 1. So this waveform gets sampled on this clock, and we're going to see a 1, 0, 1 come out here. So out here on the output, if we look out here in the output, we're going to see something that looks like this. We're going to see something that looks like this. It'll be 1, all right, and then at some time later on the next clock here, it's going to go down to 0, and then on the next, it's going to go to 1, just like that. That's what the output's going to look like. Now, if the clock turns off and it stays 0, whatever the last value is on the Q, right, on Q, will stay there. That's the idea of a flip-flop. It's a memory. It's a 1-bit memory. So a D-type flip-flop takes whatever the input is and then samples it and then memorizes it, stores it, and then just puts it on Q. And then if you turn off the clock and don't do anything, it'll still be there. So it's a memory. So it's a 1-bit memory. And so you basically can take an input and keep sending it out to an output, or you can just remember something. So say if you wanted a 1-bit memory or an 8-bit memory, you'd put 8 of these together in parallel, and then you could latch a bunch of data, right? So if you had a bunch of switches, you could do this. You could take 8 flip-flops, connect them all together in parallel, hook 8 switches up, then hook all the clocks together, and then if you were to press a button that generated a clock signal, all right, there's a problem with what's called debouncing and noise. Remember all that noise? So like if we press a button, it goes like this, and it goes like this, and it goes like this, and it does all this crazy stuff. So we have to clean that up, so we just get this. But if we could press a button and we get a clean clock, we could clock all 8 of them, and whatever the button settings we had would all get latched into the memory, all right, into the D-type flip-flops. So that's all a D-type flip-flop is. So it's a synchronous clocked kind of device, and it's something that we need to know about. And the only thing that's important is it's got D, which is the input, Q is the output, not Q is the inverted version of the output. There's typically a clock, and the clock can be edge sensitive or it can be level sensitive. There's a clear usually, which is usually active low, so when you assert it, but it's asynchronous, which is interesting, so you can reset it anytime you want. It'll reset it, all right? And that's the D-type flip-flop. Then there's a couple more. There's the T, which is a toggle. And so all a toggle does is every time you clock it, the output flips. Q goes and flips. That's all it does. All right. There's a set, reset, and this one basically has 2 lines: set and reset. Right. So the toggle is pretty simple. It just toggles. So you just got Q here, and then every time you clock this thing, so there's a clock and a Q, it just toggles from 1 and 0. That's it. That's all that does. Set and reset typically looks like this. There's a set, a reset, and then there's a clock, right? And there's a clock, there's set, there's reset, there's Q, and there might be a Q naught as well. And if you click set or assert set, right, then it'll set it. If you assert reset, it'll clear it, all right? And then there may or may not be a clock as well. And then finally, there's a JK flip-flop, which is more complicated, a JK flip-flop. And the JK flip-flop, again, clock, clear, J, K, these are 2 inputs, and then Q and Q naught. And then this has different properties, and it does some special little things. So the JK is the most powerful. It can be any of these other flip-flops. You can make it do any of these other things, right? But it's a little bit more expensive. Typically, no one really cares about toggle flip-flops. No one cares about set, reset. The only thing you're going to ever really see are D-type flip-flops and JK kind of flip-flops. But we're going to get into it. But all I really wanted to focus on right now, just for a minute, was this D-type flip-flop and what is going on here when you have a clocked circuit. Okay, so let's go back to the document here. All right, so this is what this is all talking about. D is the input, clock is an input, then you got Q output, Q naught is an output, and then you got this clear, typically active low, and it's asynchronous. All right, so now we can look at a synchronous timing diagram, and this happens to be for a D-type flip-flop. So now here you go. So now we've got D, we've got the Q and Q naught, we've got the clear. So now if you're an engineer and you built a flip-flop for a company, and you have to say to yourself, well, how do I show a customer all the different variations of things you can do? So you could put a 1 or a 0 on D. While you're doing that, you could hit the clock. While you're doing that, you could hit the reset or the clear, and so forth. So you kind of want to show all these different things and then mark what the different timings are so you can see what's going on. So in this case right here, you can see clock, clock, and then there's this area right here, which just means there's no clock, not doing anything. Then clock, clock. All right, so in this case, it starts off and says, hey, D is low, now moving D up high, right in the middle of this clock going low kind of thing, right? Then what's happening with Q? What's happening with Q naught? Remember, these are outputs, right? And then during this whole time, I didn't mess with clear, didn't mess with it. Then right here, I all of a sudden decided, hey, let's pull clear low. The moment we pull clear low, what happens? Q then goes low, and then see there's a delay here. So we pulled it down here, and then it goes low here, right? So this is a synchronous timing diagram, and it's clocked. So the clock is when things happen. So the clock, the rising edge or the falling edge is when things happen, and it depends on the chip itself. You have to read and see if it's edge triggered or if it's level triggered. Leveled means once it gets up here, right? It's either high or low, then something happens in the circuit. or it means on the rising edge or the falling edge. Things are activated on those edges typically, and that's kind of what you want because those edges are really, really short in time. They're almost instantaneous, so you want things to happen instantaneous on those edges. All right, so now there's some other symbols here, this T hold time and this T setup time, all right, that you'll see, and I think, yeah, so, and I think right here, you know, I described them, but let me kind of tell you what they are. So these are also important things. Now, what these things are is this. So the setup time means this. Before that clock hits, D has to be stable or something needs to be stable. So the setup time typically, and not just talking about a flip-flop, but with any IC, the setup time means before that clock signal goes and rises or falls, whenever the clock signal is going to cause something to happen, you can't have the signals changing. They need to be stable. All right, so they need to be stable for some amount of time before that clock hits. And the reason why is because this chip has, it's a finite velocity chip. It only runs so fast. There are other propagation delays happening. So in this case, you've got D. So D, whatever you want, D's got to be stable. Then the clock hits later in time, in the future, a couple nanoseconds. But if you were to change D and simultaneously let the clock go, the clock has its rising edge, you're going to not catch D. All right, D hasn't been stable long enough, right? You can't see what's going on. So that's called the setup time. So the setup time means how long before the clock signal, rising edge or falling edge, right, or whenever the system is triggered, that all the other signals need to be stable. They need to be stable for so much time, setup time. Hold time is after the clock edge occurs. So say here's where this clock edge occurs. You have to maintain the signals to let the thing work, right? So if you think, oh, I've already, the clock edge has already happened, right? And so I can just change D now or change these other signals. You can't. They need to stay stable. So they need to stay stable before and they need to stay stable after. So that's called the setup time and hold time respectively. They have to be set up and then they have to be held. Not for a long time. It's usually a very short time period, but you still have to do it. If you don't do that, you're violating the timings, right? You would call it violating the timings, and things won't work right. They won't sample right. They won't do whatever they're supposed to do, and weird things will happen. It'd be like, why is this chip not doing what it's supposed to do? And someone might say, you know, what about your setup times and hold times? Are you violating anything? And you're like, setup and hold times, what's that? That's what that is. So you need to make sure that these things happen. So in your design, if you have a bunch of different signals hitting at different times and this and that, all relative to some clock, and then you're putting those signals into an IC that requires you to have various setup and hold times, you may have to tweak those timings, and you might do that by putting time delays in those signals. In other words, what you would do is say you needed some signal to be slowed down. It's coming too fast, right? So what you'll do is you'll slow it down in time by putting it through a couple buffers or inverters so that the signal doesn't change. You'll put it through two inverters, for example. That'll change it from 0 to 1, 1 to 0, back to itself. But each one of those maybe adds 5 nanoseconds of time. So if you put it through those couple inverters, the signal stays the same ultimately, but it gets delayed in time by a total of 10 nanoseconds if each inverter was a 5 nanosecond delay. And that way, now all of a sudden you give your system time to do whatever it needs to do. So a lot of times when you're doing really high speed design, you'll see violations or something won't work right, and you'll look at your timing diagrams, you say, oh, these signals are getting here too fast for this clock. I don't have enough setup time here. So I'm going to slow these things down. So you'll put them all through a buffer or something, just anything to slow them down. And it seems kind of wasteful, but you're dealing with, you know, electromagnetic waves and voltages and currents, and they go real fast, you know. So sometimes they go too fast and you need to slow them down. All right. So that's kind of what is being talked about there. All right. Now, let's take a look here. So yeah, this is exactly what I just said. The propagation delay is the total time from the input to the output. Setup time, I've already described that. Hold time, described that. And there's many of these things. There's probably 200 timing parameters with little names that mean different things depending on the kinds of ICs. Now, where you're going to see a lot of this we're going to see the most of this, honestly, is in memories. Memories and microprocessors or microcontrollers, especially memories. So back in the old days, right, in the 70s and 80s, where memories were simpler, there were what were called static RAMs. Those are pretty simple. They're made out of D-type flip-flops for the most part, right? Then there were dynamic RAMs. They were much more complicated. They had little capacitors. Well, they still do, right? We still have all our RAMs are mostly dynamic RAMs now. DDR RAM, 3, 4, 5, and all these different versions of it that go very, very fast. They're based on storing charge. They have a gazillion, and yes, that is a number. They have a gazillion timing parameters, just crazy timing parameters. Very complicated to understand what's going on. So, as a matter of fact, let me show you. Yeah. So here is an SRAM. So this is a simple static, random access memory that you might see in a simpler system from the 80s or 90s, or if you're going to make a microcontroller system, you might use a static RAM because it's much simpler to operate and interface to than a dynamic RAM, which is much more complicated. All right, and so here you see, here's the address, and there's that symbol where we go both high and low at the same time. It just means it could be either, and it's the address bus, right? And then there's a thing called a read-write signal, and we're not going to talk about computer architecture in this class. That's something for another class, but when you're reading or writing a memory, they have a little signal on it. It says read or write, and that's all there is to it. So read is high and write, read is high and write is low in this case, so it uses the same signal. So depending if it's high or low, it means you're reading or writing. And then there's this thing called CS chip select, and that's how you activate the chip and say, I want to talk to you. And then you have the data on it. So if you look at this particular timing diagram, the way it looks is first get the address on the address bus, way ahead of everything else. Then assert read or write whichever way you want it, down the line here, right? Then assert chip select way down here, right? And then during this time, you're either going to get data out of it, right? In this case, we were doing, if you look, we're doing a write. So we assert this chip select, and then data's got to be valid, and then we deselect and all that. So the point is, this is showing a timing diagram for writing a SRAM memory, right? And so the memory timing diagrams get very, very complicated. Simple ICs like AND gates, OR gates, inverters, shift registers, decoders, multiplexers, which we're going to talk about these things soon in another lecture. They're fairly simple, but memories are more complicated. And that's why it's important, because as you want to start using more and more complicated chips that do different things, you're going to get these timing diagrams, and you're not going to have any idea what you're looking at unless you understand this. So that's why it's important. All right, I want you to read this, obviously read this paragraph. I want you to read the whole book. Read that. All right, and then this section right here, let's not talk about this right now. So now what I want to do is, before we end, I want to go here and I want to look at so what I did was I just searched in DigiKey for an SRAM, right? So if you search for SRAM, as a matter of fact, let's just go do it real quick. So I want you to see this. So we'll search for SRAM. All right, so we search for SRAM and we go to memory. There's 13,000 devices in their database here. All right, lots to choose from. Overwhelming for most people starting out. They just have no idea where to even begin. But let's begin with in stock, lead-free, RoHS compliant. And remember, RoHS stands for Restriction Against Hazardous Materials and Substances. It just means it's safe and clean, doesn't have lead and cadmium and bad things in it. We'll apply filters. We got 1,200 things left. Next, let's get things that are just bulk and cut tape. I don't want to buy big reels of things. All right, we're looking for a SRAM. Great. I surely don't want things that are discontinued, so I want them active. All right. Next, let's use a parallel interface. Maybe we're going to hook this up to an old processor or something. We could use SPI, that stands for Serial Peripheral Interface, but again, this is not a computer course, so we're not going to talk about that. But parallel interface, all right. And then how big do we want it? Take a look here. It goes at 32 megabytes, 32 megabytes, right? That may seem like nothing to you, but it's very expensive. So if we do 32 megabytes, look at this, watch. How much are these things? $26 a piece. That is not cheap, right? $26 for 32 megabytes. You can buy a 16 gigabyte little flash memory for $2. So these things are not cheap when they're static memories. But let's get something a little bit more reasonable, like a 32K by 8, right there. All right, real simple, 32K by 8. And then these are the speeds of it. The faster it is, 10 nanoseconds, that's faster. The smaller the number, the more expensive it'll be. So let's look at 10 and 12 and 15 nanosecond. All right, and then we're left with these three manufacturers right here. So we'll leave them all up here, and we'll sort by price. All right, and then here you can see I picked this one here, and this is from ISSI. I like this company. I use them a lot. And then we're back to this page here, right? Okay, so now we can go to the data sheet, which I've already opened up. And let me zoom in a little bit here. So you can read through this and, read these things for simpler things. Like, don't go all the way to like DDR5 memory and try and understand the 400-page data sheet. It literally is 400 pages or more. This is 11 pages. You can read through this and understand this, right? And then, you do things in baby steps. Again, this is a computer architecture kind of thing, so we're not really going to get too into it, but again, this is showing the block diagram. It's got some memory there, which is made out of flip-flops. Then it's got some addressing things here. It's got an address bus. It's 32K, right? So there are 15 lines. So this is 2 to the 15th power, right? So that would be 32K different addresses. Power, and then I/O. This is the data bus. So data in is 8 bits and data out is 8 bits. Uses the same 8 lines. So they're bidirectional. They go in both directions. And then here's the control bus. It's pretty simple. This is chip enable, which is like chip select. It enables the chip. And then here's output enable and write enable. So in this case, they're 2 different lines. All right. So whatever. Not too interested in all that right now. There's the mechanical of it. What I'm interested in is showing you the data sheet. Now look at all these. See this? So look at all these. Read cycle time, address time, output time, blah, 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 et cetera, et cetera, et cetera. All these different things. There's a timing for every signal related to every other signal. There is a timing. And you see they just kind of make these things up. And you have to kind of understand. But then what we get to are the timing diagrams. And there's a lot of them. So now you remember there was no timing diagram for the 7432 or 7408. It was just like 2 propagation delays. But this actually has timing diagrams. And they're fairly simple. There's only a few of them right there, and we're done. Right? So these are reasonable. All right, so let's get to the very first one. Here we go. So this is saying read cycle number 1. So this is one way to read. Now with these chips, a lot of times there's more than one way to do things. You can do this one way or another way, and it shows you different ways. And here's the good diagram. So here in this one, this looks like this, and this says, let's look here. This one says, all right, so you got your address on the address bus starting here. Then you need to let that set up a little bit, and then you can turn on this output enable. All right, you got to have this chip select asserted first, right? So this is back in time here. Assert this one first. Then you can hit this output enable. You can change this if you're doing a read or a write. In this case, we're doing a read, so we need this output enable to be asserted, which means in this case it's got a bar over it, needs to go low. So first we select the chip here. The same time roughly we're putting the address on there. Then we hit the output enable, we go low. All right, then it's going to take some amount of time, and that's what's happening here before you get valid data. All right, so see, data is all changing here, and there's that high Z in the middle. Remember, the high Z is in the middle. Right? So when you see a bar in the middle, that means high Z, it's not doing anything. Then the chip turns on. See, this output enable happened right here. So here to here, this time right here is how long it takes this thing to stop being high Z. Then this is garbage, and then right here, the data is good. Now, so when should I sample the data? Well, you can sample the data right here. You can, right when you pull this output enable up, or you do this chip enable, this data will be valid right here. So you can sample it right here. All right. So that's what this is showing. All right. And then again, there are more of these. All right. There's a write waveform and there's 2 different versions of the write. And this one says it's WE controlled based on write enable. And then this other one's probably based on something, using a different technique. Output enable is high during the entire write cycle. So there's different ways of doing things, another kind of write cycle. But the point is, this is not too hard to understand. You just have to take your time and understand, oh, there's that symbol there, and that means it could change any time. From here to here, this thing is going to go low sometime in there. We're not quite sure when, right? And then you just read through the data sheet for what these things mean in the context of whatever it means, all right? So anyway, so that is data sheets for you and timing diagrams, which are really important. We probably won't talk about timing diagrams again unless we're looking at a timing diagram. but very important to understand. So just, grab a couple chips and just open them up and, see if you can find a timing diagram. And just like the one we just looked at, if we go to a different manufacturer, this is ISSI, maybe we go to Cypress here, right? And we look at their data sheet and what does their timing diagram look like, So here's a different manufacturer. This one's 15 pages, very short for a memory. Like I said, modern memories are hundreds of pages long. They're just horrible to read. And then we look down here. Sorry for scrolling. I know it hurts some people's eyes. And then here we go again, and right there, there's a read cycle. And now we know how to read these things. We know this high impedance thing is when it's in the middle. We know that this symbol means it could change any time, right? And then here it is, it's solid, but we don't know what the data is because we're not going to have 65,536 different timing diagrams. This means all possibilities of data here could be here, right? That's all we care about. We just care about the timings of these control signals. Data and address we don't really care about. Address, whatever you got on the address bus, great. We don't want to have a million different timing diagrams to show you every possible address you could put, right? So anyway, that is how you read timing diagrams, all right? So hopefully that helps, and I will see you in the next lecture. Bye. All right, welcome back everybody, and we are in the next section here, next lecture. And what are we talking about? We're just following through the material here in the book. And sometimes we go off script here and sometimes we don't, but I kind of want to follow the book here because this stuff is important, and this will give you a second reference. So anyway, we're on chapter 4, 4.7, and talking about real world IC packages, DIP packages, and whatnot here. So I want you to read through this, but it's going to be pretty straightforward. So really, we've already talked about this, the different packages that ICs have, right? Now, when you're prototyping things, what you want to do is make it as easy as possible on you. So typically that's going to mean using through-hole components so you can plug them into those solderless breadboards, the white boards that we've been using. But sometimes you can't, and if you can't and you have to use surface mount components, then you're going to have to get surface mount adapters. So surface mount to DIP adapters, surface mount to dual inline package adapters, which we've seen those, right? And we looked up that company. Beldyne Sys is one of them. Schmart Board is another one. All right, so you can find those. Anyway, but what we're always looking for is a DIP version of the package. Now, of course, this doesn't really work if you have a lot of pins. After about 28 pins, it just gets to be too much. The chips get to be too big, and I'm going to show you that in a second. But another thing is they all have kind of the same dimensions, meaning the pitch between pins is 0.1 inches. So in this mechanical drawing right here, and that's another thing. If you're a programmer or you're getting into electronics, you probably don't do any mechanical stuff either, mechanical engineering stuff. So one thing you have to kind of learn is how to read mechanical drawings, and that's going to be important. And then later you may have to make mechanical footprints as you're doing your circuit board design. You're going to have to get the hang of doing some mechanical stuff and just reading how these things work. So there's lots of references on how to read these. But let's take a quick look here. This isn't going to hurt us. So this is saying that it's a PDIP, which is plastic dip dual inline package, and it says it right here, plastic dual inline package. And this shows the dimensions. So you've got this dimension A here, right? And then we've got this other dimension right here. And then we've got this table here, this legend that kind of says what things are. And in this case, this is saying if it's a 14-pin chip, 16-pin chip, 18-pin chip, 20-pin chip. So A is the horizontal or the width here of the chip in this orientation. And so if you've got a 14-pin chip, then it's going to be 0.775, 0.775, 0.92, 1.06. The top numbers are in inches, and then the parentheticals, those are in millimeters in this case. So that's how these things are. So you see this 0.260, and then you see this 6.60. That's inches, so it's about a quarter inch, and it's about 6.6 millimeters, and they're doing it in parenthetical. So now some manufacturers may have everything in millimeters, right? And they may have no inches. So be careful that you've got your units right, and that's what these parentheticals are. It's just the other units, which are millimeters, which I personally prefer. All right. And then you'll see this like 0.260 over 0.240. It's not a division, it means a range. So it means within, they have some manufacturing tolerance. And because this is plastic, it means that it's going to be between, 0.240 and 0.260, or 240 thousandths and 260 thousandths, right? So there's a 20 thousandth variance there, all right? Or 0.5 millimeters if you were to subtract those numbers. All right, and then the pins typically are, pin 1 is on the left here. This little marking gives you an orientation. So when you see this marking, this is the orientation that helps you find pin 1, which is usually right under it. Then they count up and they go counterclockwise. So 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, up to 16. And of course, if it was the 14 pin or the 18 pin or the 20 pin or a larger 28 pin, then they just, count up and count down just like that. All right. Then it shows you a side profile. Again, it's showing you all the different dimensions of these things and what everything looks like, so you can kind of figure things out. And then, over here, there's a zoomed in version just kind of showing you one pin. And then this is interesting right here. So here's looking on the side of it, kind of a cross-sectional view of it. All right, and then it's showing that there's these angles right here. So these things, these pins are not straight down. And so when you actually get these ICs and you buy some and you're just prototyping, if you try to plug them into a solderless breadboard, a lot of times they won't go. They'll bend and they'll break. So what you got to do is you got to kind of bend these pins inward a little bit to get them to be perpendicular at 90 degrees. Now when robots do this, they'll grab these things and they'll do that adjustment themselves, and they'll kind of push the pins in and then push them into the socket. So that's okay. So anyway, so kind of figure out how to read these mechanical drawings and take your time and see what these things, and some of this stuff just is, you'll have to Google and figure out what these different things mean, especially when there's angles and radiuses and things like that. But for the most part, it's either inches, millimeters, and these dimensions just kind of show you what everything is so you can know what's going on. They all have, the dips all have the same pitch, which is 0.1 inch per pin, and you can see it right here, 0.1 inch from dead center of the pin to dead center of the pin, and then you see it's 2.54. So there's 25.4 millimeters per inch, and that's why there's 0.1 inches, 2.54 millimeters. That's something you should remember. So when you see 2.54, that's the same as 0.1 inches and vice versa. All right. Okay. Then there's a picture here, and we're going to actually get on the bench in a minute, and I'm going to show you. I want to show you some more of these chips. I know we've looked at them, but I want you to see more of them just to get a feel for some of them. So, and here's what I'm saying. So here's a little 8-pin dip. This is like our 555 timer chip, right? Little 8-pin dip, and then here's a 14-pin, a 16-pin. And then I believe this is probably a 20 pin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's a 20 pin. And that IC is actually, what is that? It's a 244. It's a buffer IC. And then we've got this AT29256. This is a 28 pin here. And this is probably, it's a RAM. And then here's one of my favorite chips in the universe. This is a 40 pin. It's a 6502 processor, right? From an Apple or an Atari 800 or a Commodore 64 or a VIC-20 or any of the computers from the 80s, more or less all use the famous 6502 processor. And just a little sidebar, a little tidbit, the 6502 was I think developed in about 1977, 78. We could Google it, but I'm not gonna. But in the 70s, in the late 70s, and it was a big deal because it was really cheap. It was like $25, and it was very powerful. It's a very powerful processor, very ahead of its time. Simple, but ahead of its time and fast. It originally clocked at 1 megahertz, and then it got up to 2 megahertz, 4 megahertz versions. Anyway, there's a company called WDC, which I believe is Western Design Center. They still manufacture 6502s. You can buy them right now, which is really cool. And they make really fast versions of these now, like 50 megahertz, maybe even up to 100 megahertz. And the 6502 core, the technology of the core, this company, WDC, owns the rights to it, the intellectual property, and they license it to other companies. And 6502s are in all kinds of things you wouldn't expect. So that's kind of cool. All right, then next to it is a big chip. Now here's what happens. So if you need like 64 pins, you get this giant chip. And this is why it just becomes impractical to prototype things that have a large number of pins with dip packages. You got to do something different. Anyway, this has got 64 pins. This is a famous Motorola 68000. These were in like the Atari STs and the Amigas and the Macintoshes, right? This is a 16-bit processor, 32-bit processor, and 68,000. So, and this is actually gold here. That's gold, and it's got gold-plated pins. All right, so anyway, so that just kind of gives you an idea of some of these things. And then here's that company I was telling you about, Beldyne Sys, all right? And if you were to go to this, you would see it has all those adapters. We've already done that, right? Okay, and then this has just got, now we've got a bunch of, inside the book here, just a bunch of data sheets. I've just copied a page out of each one so you can kind of see things. You can skim through this if you want. We've been going through enough data sheets where you don't need to look at this, just showing some of the more popular and simple logic functions. But what I want to get to, let's see here. Okay, and then, yeah, so then the next thing we're going to talk about is binary math. We're just going to do a little review. So what I'm going to do now is we're going to go over to the bench, and I just want to look at some chips, and then we'll stop the lecture, and then we'll start up again, and we'll go into a binary math and do a little bit of computer stuff, computer math. And I know I keep saying that we're you know, going to try and keep the math stuff to a minimum, but this is really easy, and it helps a little bit when we're doing things with buses and maybe representing numbers, and maybe we're doing a D to A digital to analog converter or analog digital converter with an Arduino or a Raspberry Pi or something like that, and we need to understand you know, how to count and do math with binary numbers. But we'll get to that. So let's go over to the bench and let's go take a look at some of these chip packages, which are going to kind of blow your mind. All right, so I'll meet you over there. Okay, so I wanted you to kind of see, you know, how I store these, and just to show you some of the packages. So, you know, here's some of these DIP packages that we're talking about. We can see these different sizes here, you know, 14 pin, maybe there's a 20 pin, maybe there's a 28 pin, and so forth. And, you know, you keep them in this anti-static material, this anti-static foam, right? And then, you know, I've just got tons of these, and every one of these little anti-static foams represents something different, a different kind of chip. For example, these are processors right here. These are Atmel processors, and then here are these are some more processors. So pretty much all these are processors of different kinds, different sizes of processor, and some memories and whatnot. All right, and then this is kind of interesting. Show you this. Here's one of these. So there's a 6522. That's an I/O chip that goes along with a 6502. But here I wanted you to take a look at this. So this is an EEPROM, all right, EEPROM, electrically erasable programmable read-only memory. And you can take a look at that. Let's look at it under the zoomed camera. So let me zoom in. So that's actually the chip, and you can see all those wires going out of the IC surface there. Those are called the bonded wires, and they're actually soldered on there. A little robot solders those things. I guess a human could do it. He'd have to have really small hands. But those are all soldered, and that's every one of those connections goes to one of these pins, and that's how it works. And that's actually the IC. So if we put that under a microscope, you would see that it's just the matrix of cells, right? And I can zoom in a little bit more for you here. Yeah, let's really take a look at that. That's pretty cool, huh? So there it is right there, and if you put that under a microscope, you could see that, and you can see all the wires, and one of those wires goes to every one of these pins, all right? And so that's that. That's an EEPROM, all right? Very old, very old. You wouldn't use something like this. You wouldn't see something like this. This chip right here is, I don't know what size this is, but a teeny tiny little surface mount chip is like 100 times bigger than that today, right? So anyway, so that's that one right there. Now another thing, see this IC right here? Let's zoom in a little bit on that. So this particular IC, so that's a surface mount IC, and this is actually an FTDI. This is a USB chip. It's a serial USB chip, and that's in every one of these. Every one of these USB to serial converters that you see and you connect to your computer, you probably got one. There's one of these ICs, a version of it. Now this is a surface mount version, right? And because of that, I had to use this adapter. So this adapter, again, is one of these things you buy, and then you solder the chip to it, and then you can take this and of course plug it into something like this, and then you can work with it, right? But it's, you know, it's a pain and it's expensive and it's time consuming, but you need it. And then here's some more little adapters, right? There's a little 8-pin. This is probably a 8-pin TSOP, it's called, or SOP. And then here's an SOIC, little 8-pin SOIC. SOICs are a little bit bigger. And there's about 100, I don't know, maybe 200 different kinds of ICs, packages. If you just go on Wikipedia, you can find a list, or Texas Instrument has a good list as well. Here's another one. And this one right here, there we go. So this one right there, you know, what is this? CY7C10191B. This is probably an SRAM, I think. And again, so this is called a JLEDed package. And again, there's no rhyme or reason for a lot of these names, but if you look at it on the side, each one of the pins kind of makes a J symbol, a J shape, and so that gets soldered on there. So again, it's surface mount, and then you know I surface mount to solder it onto this dip adapter, and then I can plug it into some and work with it. All right. So again, you got to use those kind of things. Now, what I want to show you is, let me back off here, and you know my chips are, I keep all these. They're history as well. You know, and so like right here, here's some. These are real 6502 processors, originals. Right, and then I probably got all kinds of crazy stuff here. But what I wanted to show you was, oh, here's a Z-Log. There's a Z80 processor right there. So that's what was in your TRS-80 back in the 70s. And then also, that's what's in a lot of games. Namco and a lot of companies, Atari, use Z-Log Z80s because they were fast and cheap. They put 2, 3 of them in a motherboard to make those game systems back in the day. Now, this chip right here, this is called a pin grid array. I wanted you to see this. So this is called a PGA, or pin grid array. This is actually a 68030. So this is like the third generation of 68000. Let's take a look at that at the zoom camera. Pin grid array, all right, and you can see you see this little mark here. That's the flat spot, is kind of where pin 1 is. And then you flip this over. All right, and it's just, that's it, just a bunch of pins. And so the receiver on the board would have a bunch of female sockets, and then this just plugs right into it, and you press it in there real hard, and it goes in, and that's it. And this package is used today because it's very dense, right? You can get a lot of pins inside there. All right, so that's called a pin grid array. So that's another kind of package, and it's a through-hole package, definitely through-hole, but you're not going to put this into a solderless breadboard. It's going to be very difficult, right, because of the two-dimensionality of it, right? Points, circuit leads are in both dimensions here. They're not just in 2 rows, right? So anyway, so that's that, a pin grid array. Another thing I want to show you is some of this stuff right here. All right, so take a look here, and so see all these sockets here, and there's some little hairs here and stuff. These things have been here sometimes for years, little dog hairs and stuff, cat hairs, you know. Anyway, so these are all sockets, and of course these are what the ICs would go into. So say, for example, that I'm building something, and I want to build a prototype. So if I'm doing a solderless breadboard, I would just stuff this right in the breadboard, right? One of these, I would just put it right in there. But let's say that I wanted to make a circuit, and so I want to do it on perf board or something, and but I didn't want to solder the chip because maybe I want to pull the chip out, or if I burn the chip out, I want to replace it. That's what these sockets are for. Or even if you have circuit boards, so you get one of these sockets. Now the chip, the IC, can go into the socket. You put it in the socket, and then the socket goes into the circuit board or the printed circuit board. You solder that, and then you can put the chip in there and pop it out. These cost, you know, 10, 15 cents each, so they add a little cost if you got 50 or 100 of them, you know. But then it allows you to pull the chips out and replace them if they go bad, so you don't have to desolder the chips. Then also, you don't damage the chips because you never have to solder the chips. You just put the sockets in, right? And then you can see I've got sockets here for all kinds of different sizes, 8-pin, 14-pin, 40-pin, and so forth, all kinds of different variations. Now, here's another popular kind of package right here, and this is called a PLCC. And this adapter here, this is probably $60. You can see, not cheap. I'll just show you these right here. So here are all these adapters for different size versions. And so it's basically this rectangular chip, all right? It's called a PLCC, plastic leaded chip carrier, is what it stands for. And anyway, the only way to get this into something is you need one of these sockets. So you have to have one of these sockets. These are very expensive, but yet it was another way to do things. And then, for example, here's another Z-Log. What is this? This is a Z80. Yep, this is a Z80 CPU. So let's see if we can take this out. So let me show you us taking this out. So what I'm going to do here is, very carefully, let me move this away. All right, so let's zoom in so we can see what we're doing here. Zoom in until we lose focus. All right, right there, good. Okay, so now what I'm going to do is I'm just going to get a couple tools here, and there's usually a couple corners where you can get to these things. All right, so after you plug it in here. So I'm just going to put this in here and very carefully just nudge it out. It's been here a long time, and just like when you're tightening bolts or loosening bolts, do one, do the opposite, just that way we don't damage anything. Very slowly take it all out. There we go. And there it is. So now I've popped that out. You can see what that looks like. And you see those legs there, and see they wrap under there. Let's take a look under the zoom camera. So that's what that looks like right there. And I don't know, I can't remember what this is. You could look it up, 49LV1025 Atmel. Maybe it's a memory. Anyway, that's what it looks like up close. All right, and then this is just an adapter. So now if we were building a circuit board, we'd just have just the socket, but this turns the PLCC into a DIP, so we can plug it into something like this, right? So if we wanted to experiment with it, we could plug it into that. All right, so now let's put it back in. And so we got to kind of find pin 1 here. And I believe, in this case, I believe pin 1's there. And then in this one, I think you can almost put it in any direction. Yeah, there's nothing that holds it. So if pin 1 was up here, we'd put it here, and then basically just kind of push it in there and very carefully kind of push it in, careful, and then there. And now it's seated, and then that's it. And then you could use that chip, or you could pop it out or do whatever. So that's a PLCC. All right. Okay, so back here on the computer, let me show you something here. Last thing. So if you go on Wikipedia and you type in a list of integrated circuit package types, all right, and you can also look on Texas Instruments or any semiconductor manufacturer that makes a variety of different kinds of ICs. They'll have these lists. All right, but anyway, it's definitely a good thing to go check this out and look at this list. And just scroll down this thing, and you can read about some of the history of them and all that, and some of these acronyms like DIP and CDIP and SERDIP and QUIP and SDIP. It just, no one can remember all this. Surface mount, it just goes on and on, all kinds of different things. All right, chip carrier, the PLCC we just saw, right? And then you just go through all of these things, and then all these different small surface mount versions, and a couple pictures here. And then let's see, pin grid array, it's here someplace. And then some of the through-hole transistor diode stuff. So anyway, this is a really good a reference, and it shows some pictures here as well. And that's just what we just saw right there, that plastic leaded chip carrier, and goes through here. So now another thing you can do, if I can find it here, which it's not here, but at Texas Instruments or companies like that, they have PDF files that show all of the different packages. And what you can do is you can print the PDF out and then laminate it, and that's what I do. And I just keep it here someplace, and it's disappeared. But and then I look at it and I can say, what is a TV SOP or a TSSOP or whatever, and I can look at that quick reference. So anyway, that is package types. And so when you're doing your prototyping, try and find DIP packages, DIP, DIP, or PDIP, because it's going to be easier for you to prototype, and then later you want to go to surface mount. When you build your circuit boards, you start off with through hole and DIP packages as you get good at soldering, but then you want to go to surface mount stuff. All right. So anyway, so that's it for this lecture, and let's end here, and then we're going to come back and we're going to talk about binary numbers, a little bit, addition, subtraction, just a little bit of how to work with that stuff, and then we'll go from there. Okay. So I'll see you in the next lecture. Bye. All right, welcome back, and we're on the next lecture. We're continuing with some of the digital foundations and fundamentals, and I would be remiss if we didn't go over binary numbers a little bit more. And the reason why is, no matter what, I talk to people that maybe they even if they're professional programmers, a lot of times, or they just got their degree, and they still have trouble with binary and with addition, subtraction, one's complement, two's complement. So it's or bitwise operations. Now we aren't doing programming right now, but what's important, if we're going to do digital electronics, a lot of times we're going to have numbers represented by bits on a bus or something like that. And just understanding binary is really important, because all digital systems are based on binary, right? Ones and zeros. So we do want to have a good grasp on this, and of course it's going to help with your programming as well, that you get a good grasp on what's going on the processor, in the processor when you're doing these operations, these mathematical and logical operations. So without further ado, let's just jump right into this. Okay, so we'll talk about just an 8-bit binary number. So a binary number is represented with ones and zeros, and the value, typically we call it B0, B1, B2, B3, B4 up to Bn, where that is the bit position. Of course, everything starts with zeros, right? We start with 0, 1, 2, 3, and then each one of the positions in binary, it's base 2. So this is the 2 to the 0th position, the 2 to the 1, 2 to the 2, 2 to the 3. So 2 to the 0, of course, is 1. All right, so 2 to the 1 is 2. So it's 1, 2, 4, 8, 16, 32, 64, 128. That is the bit positions. And then if there's a 1 in any of those bit positions, we simply add that bit position to come up with a number. All right. So again, we're in section 4.8 here of the book, chapter 4.8. So you can read through this yourself slowly. I'm just going to kind of go through it and do some examples. All right. And just what we just talked about there, those bit positions. And those bit positions are almost always the highest bit or the most significant bit starts on the left. And then down at the right is the least significant bit. So least significant bit, most significant bit is how we write it. All right. So be careful of that. Now, when you're calculating a number, you can write it in any way here. You can say it's B0 times 1 plus B1 times 2 plus B2 times 4 plus B3 times 8, where these B0, B1, B2, B3, etc., those are either ones or zeros. Or you can write it as B7 times 128 plus B6 times 64, the opposite way. So you can either go low bit to high bit or high bit to low bit. Me personally, I like to still use it high bit to low bit because that's the way that these binary numbers are going to be written when you see them. And especially if you have a compiler or some computer language, you're going to write them like that. So they're going to be most significant bit to least significant bit. All right, so let's just do a couple examples. So if we have 255 in decimal, right, so with 8 bits, that means that every single one of those bit positions has a 1 in it. If you were to add up all these numbers, they actually add up to 255. All right, so 1, 1, 1, 1, 1, 1, 1, 8 ones is 255. If you want 0, you just have all zeros, and there's your 0. If you want 128, you would just put a 1 in the 128 position right there, and then the rest would be 0. So it's pretty easy. It's pretty easy working with binary. All right, now we're going to come to kind of what is the difficult part here. And difficult in as much as if you don't think about it, it may be non-obvious how this works. So when we do base 10 mathematics, right, so let's take a quick look at base 10 math here. So our normal base 10 math, all right, so, and we talked about this already, so base 10 math. So we've got, say, the 100s place, we've got the tens place, we've got the ones place. All right, so if we had a number like, 2, 5, 6, what does that really mean? It means 2 times 100 plus 5 times 10 plus 6, right? So that's 256. Okay, now when we add numbers, so, and again, I know it seems really obvious, but let's just do it. So when we add numbers, we add them in these columns like this. So we get 3, we get 2, we get 6. All right, that's fine. So 623. Let's try again. Let's do 1, 2, 3, and then let's say 5, 9, and let's say 7. Now, here's the case where we got to kind of model this in binary and make sure we do it right. So 3 plus 7 is 10. We don't write 10 down here, now do we? So what we do is it's 0 with a carry of 1. So what happened is, because these two numbers exceeded the maximum number that can be represented in this digit, which is 9, right? We basically put the result 0, and then we carried the 1 over here. Now we're going to add these three up. So 9 plus 1 is 10, plus 2 is 13. Excuse me. 9 plus 1 is 10, plus 2 is 12. So again, we put the 2 there, and we carry the 1, and then we get 2 plus 5 is 7. All right. So now when we do this with base 2, all right, so when you do this with base 2, we only have 2 symbols. All right, so coming back here, so 0 and 0 is a 0. 1 plus 0 is a 1, and the carry is 0 in both of these cases. 0 plus 1 is a 1. That makes sense. Now, here's where things get interesting. 1 plus 1, it's not 2, it's 0, because 1 plus 1 is 2, right? So how can we represent a 2? We need to put it in the next digit. So we put a 0. So the sum would be 0 with a carry of 1. This 1 really means the next digit over is going to have a 1 in it, which in this case would be representing a 2. And then here in this case, we've got 1 plus 1 plus 1. So 1 plus 1 is 2. So, or it's the next magnitude in the next digit plus another 1. So if 1 plus 1 would be 0 with a carry of 1, 1 plus 1 plus 1 is 1 with a carry of 1. All right, so let's go ahead and let's add some numbers. So here's a 3 and 5, and I'm not going to sit here and do this math in this text here, by pointing at the screen. Let's actually do it, but we're going to do the same numbers here. So let's add 3 plus 5. All right, so 3 plus 5 is going to give us 8 here. So let's see what happens. All right. Okay, so let's do a binary 3 here. So we're using 8 digits here. So let's go from right to left. So this right here, 1, 2, 3, 4, 1, 2, 3, 4. So that's a 3. And let's do 5. It would be 1, 0, 1. And you either can memorize these things, you can do them in your head quickly. So this is equivalent to a 3 right here, and this is equivalent to 5. And one thing that I try to do is I try to do them in 4 bits at a time. So that way, if you memorize what all the possible combinations of 4-bit numbers are, you can kind of do them one at a time here. All right. So anyway, so this is 3 and this is 5. All right. And then we want to add these things together. So we'll just put plus right here. And you do it just like you would in decimal, except we've only got 1s and 0s, all right? Now, another thing let's pay attention to. So this right here is the 1s place. This right here is the 2s place, the 4s place, right? The 8s place, the 16s place, the 32nd place, the 64th place, and the 128th place, okay? So those are where those places are, all right? So let's, keep that in mind. All right, so 1 plus 1 is 2. Right? 1 plus 1 is 2. So we can't represent a 2 here, so what we're going to do is we're going to make it 0, and then we're going to carry 1 right here. Now 1 plus 1 again is 2, plus 0 is still 2. So 1 plus 1 is 2 again. We're going to put the 0 right here, and we're going to put this carry right here. All right. Now again, we've got 1 plus 1 again is 2. All right. So we're going to put a 0 here, and we're going to put a carry here. And then finally, 1 plus 0 is just 1. And then we're done. So 3 plus 5 is this number. And what is this number? Well, look at that. We've got a 1 in the 8th place. So this is equal to 8. And of course, we can put base 2 there and base 10 there. All right. So that works. So we were able to add the numbers, and they add up and do what they're supposed to do. All right. So let's do another one here. Let's do another one here. Let's try this one right here. So this 215. So this is 1101. All right, so this is 1. Let's get our color here. 1101, 1101, 0111. So 0111. And then this is 10. So that's easy enough. So that's 0000. And then to get our 10, we want a 1 in the 8th place and a 1 in the 2's place, right? So there's the 8th place and there's the 2's place. All right, so these two numbers right here, oops. You've got to love the way tabbing works in Windows. All right, so the first number is 215 and the other one is 10. 215 and 10, right? Okay, so we'll just put 215 over here so we can remember that, and we'll put 10 right here. So we know when we add these together, we should get 225. All right, so let's do it. All right, 1 plus 0 is 1. 1 plus 1 is 2. So we're going to put a 0 here, and we're going to carry 1 over to the next digit. 1 plus 1 again is 2. So we're going to put a 0 here. We're going to carry 1. 1 plus 1 again is 2. We're going to put a 0 here. We're going to carry 1. 1 plus 1 again is 2. We'll put a 0 here. We'll carry 1. 1 plus 0 is 1. 1 plus 0 is 1, and 1 plus 0 is 1. So now we have 1110 and then 0001. So let's see if The number is the same, so we've got 1110 and we've got 001, and it's 225. So let's actually see if this is 225. All right, so this right here is the 128th place, right? So there's a 128th place. So we got plus, we got 64, plus, we got 32. This is 16, this is 8, this is 4, this is 2, this is 1, plus 1. So if you add those numbers together, get your calculator out, 128 plus 64 plus 32 plus 1 is 225. So this indeed, base 2 is 225, which if you add these two numbers up, you would get 225. Okay, so now when you add these numbers up, binary numbers, obviously one thing you could do is you could overflow. And if you overflow the 8 bits, then the result will be incorrect. All right, so let's do a quick example of that. So we'll just erase this one here. All right, so let's try and add, what's going to happen if we add 255 plus 1, all right? So 255 plus 1, we know that with 8 bits, the largest number that you can represent is 255. And remember the math. For n bits, so for n bits, let's put this right up here. So n bits, all right, the maximum number that can be represented is going to be 2 to the n minus 1, 2 to the n minus 1. So if n is equal to, say, 8, right? So that's going to be 2 to the 8th minus 1, which equals 2 to the 8th is 256 minus 1 equals 255. All right, so there are 256 combinations, 0 through 255, but the largest magnitude is 255. All right, so that would be all ones. All right, so let's do all ones. 1, 2, 3, 4, 1, 2, 3, 4. So this number is 255, and this is a non-signed magnitude-only representation. So we're just using non-signed binary magnitude only right now. Okay, now what happens if we add 1 to it? Well, 255 plus 1 is going to be 256. So what's going to happen is that we can't represent that with 8 bits. We need a 9th bit right here. We need this bit right here. This would be the 256 bit, right? This bit right here would be the 256 bit. But we don't have a 256 bit, so we're going to have a problem if we try and add this. So let's go ahead and let's try and add 1 to this. So let's represent 1. So what's 1? 1 is just a 1 right there in the ones place. Remember, 1, 2, 4, 8, 16, 32, 64, 128. Okay, let's add these together. So let's put our little plus operator. Here we go. 1 plus 1 is 2. So that means we'll put a 0 here and a 1 there. 1 plus 1 plus 0 again is 2. So we'll put a 0 there, we'll put a 1 there. And you can start to see the pattern that's forming here. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. All right, and then that 1 here it's lost. So the result is 0, which is incorrect. That is not correct, right? We want 256. So this bit that went out of here, right? This bit, you call this, and if you're a programmer, you'll know this. This is called, the carry out, right? And each one of these are a carry also, right? All these are carry bits, right? Down here, all these are carry bits, right? Carry bits. All right, and then this is the carry out. So we need more bits to represent this. So that was called an overflow. That's an overflow, okay? Now, so that's all fine and dandy. So we can add magnitude numbers. We know how to do that, but how would you subtract, right? So subtraction is a little bit tricky, and to do that, we have to come up with a different number format. We've got to be able to represent positive and negative numbers, all right? So let's go back to the document here, which I want you to read this. I want you to read this document and this chapter carefully. But if we try to add these numbers, we get this overflow. And if we want to do negative numbers, we need some kind of different representation. Okay, so looking at the text here, we see in section 4811, one's complement and two's complement. So when you have a binary number, a couple techniques have been kind of arrived at to be able to represent negative numbers. All right, so one of them, the first thing that you might think, let's go back to the drawing program here. So the first thing that you might think, let's just erase all this, is, we could just do this. We could just do this. So say we had a binary number, let's say it was 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. So say that was the number 3, right? So that's the number 3 in binary. You could just call this the sign bit. and we could just say if it's 0, it's positive, if it's 1, it's negative. You could do that, right? Nothing wrong with that. All right, so this would be 3, and this would be -3. The problem is if you try and add and subtract numbers, this just won't work, right? It won't work if you try and add and subtract numbers. It's just going to be incorrect, and then if something overflows into the sign bit, then you'll flip the sign. So that doesn't work, right? So no help there. So the other technique is called ones complement, and ones complement, what you do to figure out that is you take your original number and then you invert all the bits. That's why it's called ones complement. So you invert all the bits. So if we started off with the number 1 here and you were to invert all those bits, you would get 1, 1, 1, 1, 1, 1, 1, 1, 0, which is this number. So that's a -1. So any number you want to transform from a positive number to a negative number, you simply invert all the bits. All right, and then if it's a positive number, you don't do anything to it. So if you look at this upper bit here, this is the sign bit. So if you look at this upper bit, that is the sign bit. So that can tell you if the number is positive or negative. All right. The problem is that for one thing, there's 2 representations of 0. So this is called -0, and this is called +0. So if you were to take 0 and do the ones complement of it, compute the ones complement, you end up with this number. So it's valid. So it's a -0. So it doesn't really make much sense. It's mathematically valid in this number system, but you've got 2 different numbers for 0. So that takes up 1 possible value. So that's bad. And then if you try to do math with these things, if you try and add these things together, you actually get incorrect results. All right. So ones complement doesn't work, and you can read up on it and do examples if you want to. So the other technique is called twos complement. So mathematicians, binary mathematicians, people working on binary math, computer scientists, they started, looking at this and saying, well, what about if we try this? And what this was, they said, let's invert all the bits. We'll add 1 to that value. So if you have a positive number and you want to turn it into a negative number, you invert all the bits, you add 1. That is called a twos complement negative number. Now, if you just do the math like you normally would, which we did in the previous example, the results will actually be correct. If you see a 1 in that upper bit, in the topmost bit, the most significant bit, it means it's negative, and to find the positive value, you have to compute the twos complement of it, all right? So I know I just went fast with a lot of that. So what I want you to do also is you can go on Wikipedia, and if you just type in twos complement, you can read this document here, and this goes into all the bloody details of twos complement, why it works, and so forth. You can read all that and some examples, but let's go ahead and let's give it a try and see what happens here. So if we go back to our document here, the first thing is, the nice thing is the numbers that it represents is -2 to the n minus 1 to 2 to the n minus 1. So that means that you get the entire range of values. Now it's not symmetrical, can't be symmetrical, so you get -128 to +127, for example, if you have 8 bits. So the negative range always has 1 value more in its range, or 1 value more negative than the positive. So for 8 bits, it would be -128 to +127. All right. All right. So constructing twos complement numbers. So the first thing is that if you want to construct a twos complement number, typically you're doing that because you want to find the negative version of a number, all right? Or you want to do a subtraction. So, here's 0, here's 1, here's 127. These numbers right here, even if you were talking about a twos complement system, these numbers are not complemented. These are the normal magnitude only. Notice the upper bit, right? The upper bit here, which is the sign bit, is always 0. So that tells us it's not a twos complement number yet, all right? Now, if we wanted to create a -1, for example, so we want to turn 1 into -1. So what's the -1 twos complement number? All right, so the first thing we do is we invert all the bits. That's step 1. So 0, 0, 0, 0, 0, 0, 0, 1 inverted is 1, 1, 1, 1, 1, 1, 0. And then we add 1 to it, so then we have that number right there, and we add 1, and lo and behold, look what we get. We get all 1s. So that's kind of interesting. So that's kind of nice. is that all ones is a -1. Now before, what was that? In pure magnitude, that would be 255, but we're not doing magnitude, we're doing 2's complement. So when we see this number in 8 bits, we say, oh, that upper bit is high, it's a 2's complement number, so to find what its actual value is, unless we've got this memorized, we apply the 2's complement again to it. So if you take the 1, 1, 1, 1, 1, if you were to invert that, it would turn all the zeros, and then add 1, it would just be 1, and we get right back to where we began. So if you have a 2's complement number, if you apply the 2's complement algorithm again, invert and add 1, you get back the original positive number that it represented. Okay, all right, and then here's 55, just which is a let's see here, 55. Yeah, so 55, and just doing the algorithm again. So let's actually go and do this and see what happens here. Okay, so it's 0, 0, 1, 1, 0, 1, 1, 1. Okay, so it's 0, 0, 1, 1. Let's get to our drawing program. All right, so it's 0, 0, 1, 1 is the upper nibble. 0, 0, 1, 1, and then 0, 1, 1, 1. All right, 0, 1, 1, 1. And then 0, 1, 1, 1. All right, so we're saying that this is 55. All right, and we could compute that, right? So let's, again, this is the 1's place, the 2's place, the 4's place. All right, this is the 8's place, this is the 16's place, and this is the 32's place. So if we were to add all this together, so we've got 32 plus 16 plus 4 plus 2 plus 1. So 32 and 16, that's going to give us 48, right? And 48 plus 2 gives us 50, and then plus 4 and 1 gives us 55, right? So that is correct, so it's 55. So now let's compute the 2's complement, or -55. So I want to know -55 in 2's complement, right? So that's what we want to do. So first what we're going to do is we're going to invert all the bits. So we're going to get 1, 1, 0, 0. Then we're going to get 1, 0, 0, 0. Then we're going to add 1 to this. Then you say plus 0, 0, 1, 1, excuse me, 0, 0, 0, 0, 0, 1. So you just add these together. Let's use a different color so if we have carries, we don't mess it up with this line here. So 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1, and another 1. So basically, we just added this 1 right here. You can see it just gets added in there. There's no carries. So this is the number right here. So this, I'm telling you, is -55. So now, okay, well, how do we know it's -55? Well, the first thing we know is, so if someone just gave you this number, you'd look here, all right, and that's the sign bit. So if it's 1, it's a negative number, all right? So that means this whole thing is less than 0. It's negative. So if there's a 1 there, it's less than 0, right? And if there's a 0 there, then it's greater than or equal to 0, all right? Okay, so we know that it's a negative number, so now we want to find out, well, what number was it? Well, we just apply the 2's complement again. All right, so we invert this, so let's invert this right here. All right, so 1, 1, 0, 0, 1, 0, 0, 1, we invert it, so we're going to get 0, 0, 1, 1, 0, 1, 1, 0. Okay, then we go and we add 1 to it. All right, so we just write down a binary 1, and we add to it. Here we go. So 0 plus 1 is 1, and then we got 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, and then we got 0 and 0. All right, and then sure enough, if you just eyeball this, it is the same. So we got back our 55, all right? Now, so the next question is, okay, well, that's all fine and dandy, but what if we try to add a positive number to a negative number, all right? So if we try and add a positive number to a negative number, all right? And I just love the way this does this. It drives me crazy. All right, so let's see if there's an example here. Okay, so here's one. So inside of the book, I do -3 plus 10. So -3 plus 10. All right, -3 plus 10. So let's give that a try. -3 plus 10. So we can actually just do that. So let's just do -3 plus 10 ourselves. All right, so here we go. So the first thing is, let's create a 3. First thing is create a 3. So 0, 0, 0, 0. 0, 0, 1, 1. So does everyone see that this is a 3? So this is 1 place, 2's place, 4's place, 8's place, and so on. So I've got a 1 there and a 1 there. This is equivalent to 3. Okay, that's equivalent to 3. All right. So next thing is I want to turn this into a -3. All right. So then let's apply the 2's complement. So that means let's invert and add 1. So let's invert first. So here we go. 1, 1, 1, 1, 1, 1, 0, 0. All right, then we're going to add 1 to it. So plus 0, 0, 0, 0, 0, 0, 0, 1. There we go. So let's do this, and I'm going to do it fast now, okay? See if you can keep up. Ready? So I'm going to just do it column by column. Here we go. 0 and 1, 1, 0, 1, 1, 1, 1, 1, 1. All right, so that's our result right there. All right, so this is equivalent to -3 in 2's complement. And again, how do we know it's -3? Well, we don't know unless you have these memorized, but we do know it's a negative number because this bit right here is a 1. That means it's definitely negative. We don't know what negative number it is unless you're, you can do math in your head like this, or you have this memorized, but it's -3. All right, so now let's create the number 10. All right, in binary, so we're going to create the number 10. So just look up here, we got our little places. So what if we have the 8's place and the 2's place? That would give us 10, right? So here we go. So 0, 0, 0, 0, and then let's do 1, 0, 1, 0. All right, so this would be equivalent to 10, right? That would be equivalent to 10. All right, so we got 10, we got our -3, so let's write our -3 down here. So here we go, we're going to write our -3, we're just copying this line down to here. That's all I'm doing. All right, so let's copy it down, 0, 1, so that's equivalent to -3. All right, and let's do an addition. All right, you can actually do, the subtraction operation also, but I'm not going to do it. It's just a little bit confusing. You can always think of subtraction as addition of the negative number, right? So let's just keep with that. All right, so here we go. So we've got 10 and -3. All right, and now we just add them. We don't forget about 2's complement, just add them with the rules, right? So here we go. And let's get another color. Let's do this color. All right, ready? So 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. 1 and 1 is 0 with a carry of 1. 1 and 1 is 0 with a carry of 1. 1 and 1 is 0 with a carry of 1. 1 and 1 is 0 with a carry of 1. And 1 and 1 is a 0 with a carry of 1. Okay, so we have this carry out here, right? So just hold off on that for a second. And what is our result? Our result is 7, all right? And it's a positive number, so we don't need to worry about it. So it's a positive number, we don't need to worry about it because we can see that this bit here is 0, and the result is 7, which is actually correct, all right? So in this case right here, we got the correct answer, and everything is as it should be, all right? Now, let me show you something. All right. And let's see here. All right, so now let's try the this one, which is 100 minus 120. All right, so let's do another example and see what happens if we try and add these two numbers. So we should get a -20 when we're done. All right, so -20 when we're done. All right, so these will be a little bit hard to figure out, so we're just going to copy it. So 0, 1, 1, 0. So 0, 1, 1, 0. So we're going to erase this whole thing again so we can write this big. Okay, so 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0. All right, that should be 100. So this is equivalent to 100. We'll check it. All right, and then this should be minus 120. So see that we got that bit right there. So we got basically 1, 0, 0, 0, and then we've got 3 ones down on the lower bits here, right here, and that's it. And this is supposed to be equivalent to -120. All right. Okay, so first thing is we can't, it's really hard to tell, and we're going to add these together. It's hard to tell what this number is because it's in 2's complement. Again, why is it in 2's complement? Well, we know we put it in 2's complement, but this sign bit is 1. Because of that, we know it's a negative number, and we'd have to do the algorithm to figure out what the number is, which means we'd invert the bits and add 1. But since we know that this is -120, we're okay. Right here, we notice that the sign bit is 0, so this is a positive number. It's not in 2's complement, so we could just figure this out. So this is the 1's place, the 2's place, the 4's place, the 8's place, 16's place, the 32's place, the 64's place. So 64 plus 32 is 96. 96 plus 4 is 100. All right, so we're correct. So let's just add these things together. Again, we just add it blindly and see what happens. All right. So 0 plus 1 is 1, and then 0 plus 1 is 1, 1 plus 1 is 0, and with a carry of 1, and then 1 plus 0 is 1, all right, and then 0, 0 is 0, 1, 0 is 1, 1, 0 is 1, 0, 1 is 1. Okay, all right, so there we go. We've got that result right there. So now what do we see? The first thing that we see here is this bit right here is 1. We know it's a negative number, and so we're going to have to compute the 2's complement to figure out what it is. So it's something negative, but we're not sure. All right, so we're going to first, we have to invert it. So let's all invert this. And I'll invert it with, how about red? So here we go, let's invert it. So 0, 0, 0, 1, and 0, 1, 0, 0. There's the inversion, all right? And we could say the inversion operator is, we could put a tilde in front of it, right? That would be inversion, all right? Okay, and now we need to add 1 to this, so we're going to say plus 0, 0, 0, 0, 0, 0, 0, 1. Okay, we're just computing the 2's complement. We're changing this number here into back to a normal number because we already know that this is in 2's complement. We know that this is in 2's complement. So how we get back to a normal number is we apply the 2's complement algorithm again. So here we go. Let's do it. All right, so now we're just adding. So 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. And then 0, 0, 0. 0, 0, 0. All right, so now we see that this bit here is 0, so that means we've got a positive number. We don't have to worry about it. And now we can just look at what it is. So this is the 1's place, the 2, the 4, the 8, the 16. So let's just add these things up here. And let's see here. Hold on, did we make a mistake someplace? Did we make a mistake? We should get minus 20 here. We should get minus 20. We should get minus 20, and we have not got minus 20. So we made a mistake. Where did we make the mistake here? So this is 100 here. So we made a mistake someplace. All right, so we've made a mistake. This number right here, this is 21, right? This is the 1 place, the 2's place, the 4, the 8, the 16. So that's 16 plus 4 is 20 plus 1 is 21. All right, so something went wrong here. So that means that either we did this addition, we did something wrong, or these numbers are incorrect. So let's check again. Is this 100? So 64 plus 32 is 96, plus 4 is definitely 100. So that's correct. Now the minus 120, this may be wrong. We're assuming that this is correct, right? So that means there's a typo in the book if this is incorrect. So that's a possibility. And so we're going to check that. But let's assume that that was right for a second. Now, when we added these two numbers together, this is what we got down here. So let's see if that was right. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 1. There's our mistake. So 1 plus 1 is 1. Excuse me, that's right. 1 plus 1 is 0 with a carry of 1. And then we have 1 plus 0 plus 0 is 1. 0 and 0 is 0. 1 and 0 is 1. 1 and 0 is 1. 0 and 1 is 1. We invert that. And then we should have got 0, 0, 0, 1, and then 0, 1, 0, 0. I know, it's just crazy, huh? All these zeros and ones. And then we're going to add, and then when we add these, when we add this, we're getting this number right here. So I suspect that this is incorrect right here. I suspect that this is incorrect right here. So let's actually compute the 2's complement of 120, all right? So, or let's just actually see what this number is. So this is a negative number. We think it's minus 120, but apparently it's not. So let's give it a try. So we got 1, 0, 0, 0, 0, 1, 1, 1. So we know it's a 2's complement number. We know it's negative because this bit is high, all right? And let's go ahead and let's invert it. So we get 0, 1, 1, 1. And then we get 1, 0, 0, 0. Then let's add 1 to it. So we add 0, 0, 0, 0, and then 0, 0, 0, 1. All right, and now let's go ahead and add. So we got 1, all right, and then we got 0, 0, 1, and then we've got 1, 1, 1, and then we've got 0. All right, so this is definitely an odd number because the 1 bit is there. All right, so let's see, what is this number? So this number is, this is a 64's place, so this is 64 plus 32 plus 16 plus 8 plus 1. There's the 1. So that's what this number is. It is not 120 or minus 120. It is not. So let's see what this is. So 64 plus 64, let's do 64 plus 32 is going to give us 96, right? So we got 96, and then we got plus 16 plus 8, right? So we got 96 plus 16 plus 8, so we got 100, we got 106, we got 112, we got 120 plus 1 equals 121. There's our mistake. So this is minus 121. So it's minus 121. So now when we subtract these two things, 100 minus 121, we get minus 21. And sure enough, this number right here is 21. All right, so that's what's wrong. So that there's a typo which I'll change when I put the chapters in there, so you won't see it. But anyway, so there's a mistake right there. So this was minus 121. All right, minus 121. All right. So anyway, so that's a subtraction, so it works. So again, check your math. When you're doing this manually, you can see how easy it is to make a mistake, right? I just made one, and then there's one inside of the text there, probably from copying and pasting, and as the book gets edited, that happens sometimes, obviously. They're ones and zeros, easy to make a mistake. Anyway, but check your math, and that's why you check it. And one of the easy ways you can do things in binary math to check your math real quick is if this bit here is ever a 1 or a 0, you know that the number is going to be even or odd. If it's 0, the number is even. If it's got a 1 there, it's going to be odd because that adds 1 to it. So if you have something that makes a contradiction, if it's even, but this 1 is there, that can't make sense. And again, if it's odd and there's a 0 there, that doesn't make sense either. So anyway, check your math, be careful, and that way you don't make mistakes. All right, so that's 2's complement. All right, and so that's all fine and dandy. So that's kind of some computer stuff, but why is that important? Because we are going to use these kinds of circuits, or you're going to use these kind of circuits potentially. Maybe you want to add a couple numbers together in a digital circuit, or process them in some way, maybe 2-bit numbers or 4-bit numbers. All right, so the question is, with what we know about logic, can we implement an adder circuit? And the answer is yes, and it's pretty easy actually. So there's what's called a half adder and a full adder. A half adder just adds 2 binary numbers, but with no carry. It doesn't take the carry into consideration, right? A full adder also takes the carry into consideration. So first, if you want to build some kind of logic circuit, one thing we've learned is you create a truth table. So take a look here. So we've got 2 inputs, 2 single-bit binary numbers, A and B, or A0 and B0 in this case. When we add them together, we want to get a sum out and we want to get a carry out, a sum and a carry. Forget about 2's complement. We're just trying to add 2 numbers right now, right? So what we really want to implement is, if we go back up here, and sorry for the scrolling, just close your eyes if you have to. I know it's irritating to some people. If we go back up here, here were all of the so 0 plus 0 is a 0, 1 plus 0 is a 1, and so all the different permutations of adding 1 and 0, right? Okay, so we go down here and we want to build some electronics that does that, that implements that, right? Okay, so let's go back down here. So we want to build a device called a half adder, and so now here's all the different permutations. So 0, 0, 0, 1, 1, 0, and 1, 1. So if we just add these together, so S is the sum, C is the carry. Let's just try and do it ourselves. So 0 plus 0 should be a 0 sum and a 0 carry. 0 plus 1 should be a 1 sum with a 0 carry. That's right. 1 plus 0, same thing, should be a 1 sum with a 0 carry. And 1 plus 1 should be 0 with a carry of 1, right? Because it's really 2. So that means the current digit would be 0, the output sum would be 0, but the next digit needs to be have a 1 added to it, just like in decimal addition. So this is what we need. Okay. So let's look at the sum. First, let's look at the sum right here. So what logic gate, so when it's 0, 0, it gives us a 0. When it's 1, 1, it gives us 0. But when they're opposites, it gives us a 1. When it's opposites, it gives us a 1. So let's go here. Let's erase all this. All right, so let's try and draw this. So here's A0 and here's B0. All right, and we want to have some gate here, which we don't know. that gives us a 1 when they're opposites. So if you remember, what is that? That is called the exclusive OR gate. So remember that, that's an XOR. So this output right here, this is a sum 0, so that's it. It's just an XOR gate, done. All right, and then the symbol for the XOR is a circle, the OR circle, the plus, which is an OR with a circle around it, means XOR, or exclusive OR. So that gets us our sum. So that's part of an adder right there, okay. Now let's go back here. And if we want the carry, so the carry, what's its logic? So 0 and 0 makes a 0, okay? 0 and 1 is a 0, 1 and 0 is a 0, 1 and 1 outputs a 1. So the only time we get a 1 is when both inputs are 1. So what would that be? What would that be? Would it be an OR? No, because an OR would give us a 1 whenever there's any 1s. No, so we don't want that. So only when both of them, when A0 is 1 and B0 is 1, we get a 1 out. It's just an AND gate. It's just a simple AND. So the carry is an AND. All right, so let's go here. All right, and then this is what we're going to do. So why is this important, what I'm doing right now? Well, we're doing logic design. We're designing a digital circuit here, a discrete digital circuit that does something, and in this case, it's a half adder. All right, there's our and go here and do this little jump here, right? So we're not shorting it. All right, so there we go. And we take that out, and then there we go. So there's this C0 or the carry out, and this is just an AND. So that's an XOR, and this is an AND. So there you go. So this right here, so if someone said, so if you had a couple of binary digits, right? You just had two little binary digits that you wanted to add. You know, who knows what it's for in some circuit. You could just take an XOR and there's the sum, and take an AND and there's the carry out, right? And that's it. That's a half adder. Now, what the full adder is if you also have the carry in, right? So let's go look at the text, all right? So just talking more about the half adder, and I do want you to read this, all right? And so the 7486, that's actually an XOR. That's an XOR gate. So that gets us our sum out. So we can actually implement that with a gate, with an IC, the 7486. So let's go take a quick look at that, 7486. So we'll go to a DigiKey here, and we'll look up a 74LS86. Should be a quad 2-input XOR gate. All right, and here it is right here. And what does it say? XOR exclusive OR 4-channel, and let's pop it open. Get the data sheet here. So you see this is all coming together now. So obsolete, no longer available, 1972, 1988. We would use a new version of this, an LV or LVC or some more advanced technology, but you can still buy these chips. So here is the logic symbol and then the pinout. Let me see if it shows the pinout here. So here's one gate here, so in, out, and then here's the other gate, which is in, out, and then in, out. So you would just use one of these chips, the 7486, just like in the document here, 7486, LS or LVC, something like that. So that gets us our add out, right? And then we want our carry out, which we computed as an and so we need an AND gate. What's that? The 74LS08, 74LS08. All right, and there's the circuit that we just figured out, right? So when we draw this as a schematic, we would say 1/4 of 7486 and 1/4 of 7408, and we would put the pin numbers here if we were drawing this as a schematic and not using a tool to do it, right? And then there you go. So A0 XOR B0, and then A0 and B0. So there it is. Okay, now here's the full adder. I don't really want to go too much into this. You can read about this. So the whole difference is now instead of only 2 inputs, we have 3 inputs. We have the carry in. And so now with all those different 8 combinations, here's what the sum is. Here's what the carry out looks like. So now the question is, here's what the sum looks like. So what circuit is going to give us that? Is it an XOR? Is it this? Is it that? Right? And same thing with the carry, right? So we have to figure that out. Okay, so we could figure this all out. If we wanted to, and you can read here and I do that for you. All right, and here's an interesting thing. If you take 2 half adders, you take 1 half adder and let it add the 2 numbers, you take that result sum and then you take the carry in and use another half adder, That's how you get your sum. And then if you take the carry out there and the carry out there, and then you OR the two carry outs together, that'll give you the final carry out. So you can actually build the full adder with two half adders, all right, which is kind of interesting. I want you to read this to see why that's true, all right? And then forget that, that's not important. And then here is a schematic, a little schematic of one with pull-ups, and then a little switch so you can set the inputs in the carry, all right? So that's it. And then here it is using these DIP packages, right? The 7486 and the 7432, which is the OR, and then here's the AND. So actually doing that with parts, all right? So and we when we get to the bench in a little bit, we'll build one of these. We'll probably build a half adder or a full adder, and that'll be fun. Okay. Okay. So that is it. That is it for the ones complement, twos complement, and just understanding how to deal with binary numbers and what they are and how to add them at the digital level. So that's kind of what's going on. So if you have an i7 processor or whatever, an ARM processor, there's an adder circuit. It's doing just that. It's doing exactly what we did. It's half adding, it's full adding, and that's all there is to it, except it's doing it with 32 or 64, 128, 256 bits, right? Whereas we just did it with like 1 bit. We literally made 1-bit adders, right? So you can see this logic explodes. There's a lot of logic to be able to add large numbers and add them very, very quickly. Very important. Let's take a quick look back here, talking about speed. So one thing is, if you look at this, so this is an adder right here. So this is our full adder. So how many levels of gates are there? That's an interesting question, because remember, if you're going to build something, you want this thing to go fast. If you're building an ARM processor or an Intel, processor, you want it to go fast. So the question is, can you add numbers faster than what we've designed here? And the answer is yes. There's all kinds of ways to add numbers. But if we would look at our little half adder, full adder right here, notice it has 3 levels of gates. Here's level 1 of the gates, right? Here's another level of gates, and then a third level of gates. So we get the sum out a little bit early, but then we got to wait for the carry. See that? So if each one of these was, say, 10 nanoseconds each, right? Say it was slow logic, we've got 30 nanoseconds before the carry comes out. We've got 20 nanoseconds before the sum comes out, right? So if we were clocking, say if this was part of a clock system, and the clock was running, say the clock was running at, let's say the clock's running at 10 nanoseconds, right? So the clock's running at 10 nanoseconds, which means our processor is running at 100 megahertz. So we're running a 100 megahertz processor. So we're 100 megahertz processor, and say this was our adder circuit. If this was our adder circuit and we're running at 100 megahertz, right? So that means, again, that we've only got 10 nanoseconds for one clock. So this circuit right here takes 30 nanoseconds just to get our C out, right? So that means that we're, probably 30 nanoseconds it would take to get this entire result. So how many clocks would it take if we had a 100 megahertz system and we got 10 nanoseconds per clock? It's going to take 3 clocks. So that means it's going to take 3 clocks to add a number, right? So we can't run that at full speed. That's why when you look at a processor and you program an assembly language or whatever, different instructions take different amounts of time, because there's different layers of logic the instructions have to go through to execute all these subcommands that make up those instructions, right? So when you're dealing with a microprocessor or microcontroller, each one of those instructions is actually a bunch of smaller instructions called microcode, and that microcode executes very, very basic operations with the processor core and the buses. It takes data from one place to another. It adds in the ALU, it moves the data, it shifts the data, things like that. So one instruction may have 5, 10, 20 micro instructions that compose that larger assembly language instruction. Of course, you'll never program in microcode, right? You'll always program in assembly code. That's the lowest you can go with a processor or microcontroller. There are some processors you can actually program in microcode, though. But anyway, there's actually more little things going on in there. And so in this case, if we were building a processor and this was our adder circuit, we would have to realize that, hey, it's going to take 30 nanoseconds or 3 clocks to get our result for a simple addition. That's why multiplication is complicated, because multiplying binary numbers, you do it just like you multiply normal decimal numbers. You shift and add, shift and add, shift and add. And there's all kinds of multiplication algorithms that can go faster. But the bottom line is that's why multiplication and division in microcontrollers and microprocessors is typically slow and something you want to avoid. So addition and subtraction are okay. Multiplication these days is pretty fast. Division can be very slow, right? So unless you've got a very fast ARM processor or Intel with a floating point unit that can do these things in one clock cycle. All right. So anyway, so that's talking about that. So good. All right, let's see what's the next thing here. Okay, so mixing logic family. So let's stop here. We did a lot of good work today. So read that two's complement in the on Wikipedia or any other sources you want to try. Try some examples also. And another thing, it wouldn't hurt you. You can always use your computer as a scientific calculator. There's many scientific calculators. And one thing that's really cool is called Microsoft Math. It's free. Google it, Microsoft Math, and you can download it. It's a really nice little scientific calculator. But I like holding a calculator in my hand. And I recommend getting a calculator, a simple little $5, $20, $10 calculator like a Casio or something that has base N math. So you can do binary, decimal, hexadecimal math with it, in addition to its scientific functionality. All right, or you can get a big TI calculator, big TI 80 series calculator that does all kinds of crazy stuff. But get a base N calculator because it'll help you check your math. Because unless you think in binary or hex, which I don't, and can you do math in your head, you're going to have to check your math if you're doing examples. Okay? All right, so that's it. I will see you in the next lecture. Bye. Hello and welcome back. And on this lecture, this is going to be pretty quick. I just wanted to kind of finish out this chapter. We've been loosely following my book on and off in different areas, but these sections in chapter 4 are kind of all important one way or another. So we're going to talk about this real quick. So mixing logic families, and we've discussed this a little bit already. So there are many, many logic families now in 2017, 2018, of course. The ones that I'm listing here, you're seeing some of the LS and ALS and F and HC and HCT, so TTL and CMOS technology families. But there are many, many more now, and we're going to take a look at that in a second. But the premise of how you get these things to work together is always the same. So say if you're building something, you're building a project, and you particularly like a certain kind of IC, and maybe that IC only comes in one logic family. If so, and your other logic families of your other ICs are different, you're going to have to interface these things together. Now, there's a few different things that you have to consider. One would be the power supplies, the voltages that the logic families are using. So first, are they using the same voltages? So 3.3, 2.5, 1.8, 5 volt, whatever. That's number one. So first, if they're using the same voltage, that's great. So now you're working with the same voltage rails. Then the second thing is if you're going to mix TTL and CMOS, now remember these technologies are different. TTL is based on transistors, CMOS are based on field effect transistor or FETs. In one case, these are current driving devices. The other case, these are voltage driving devices, and they work differently. So to mix these families together, you have to look through the data sheets and you have to understand if you want to connect, for example, a TTL to drive a CMOS part or a CMOS to drive a TTL part, you have to understand is it going to be able to do it when you're driving it high and driving it low, those two cases, right? And then how is it going to affect the fan out of the IC, how many ICs it can drive, and so forth. So anyway, I want you to read through this, but in a nutshell, you can take a look at a couple little figures here. So in this figure, we're just showing some CMOS device and it's outputting to a TTL input, right? Now, if we're dealing with a 5-volt system, CMOS typically will output a very high voltage. It'll almost be to the rail. So it'll be like 4.4, 4.5 volts, sometimes even higher if it's a 5-volt system. Now the TTL input, if you remember, the V input high needs to be approximately 2.0 volts, right? 2.0 will be registered as a high. So definitely when we have a CMOS driving a TTL high, that will work, all right? The other problem is when the CMOS is driving it low, right? We need to make sure that low works also in the same way, and the TTL input is going to, remember, it's going to source and it's going to sink current, and those currents are important, and so you have to make sure that the CMOS can sink or source the amount of current required as well, all right? And if it can't, then it's not going to be able to drive it low, and it's not going to be able to drive it high, because the TTL requires current, not just voltage. So when you're driving it high, current is going to flow into the TTL input. When you're driving it low, current is going to flow out of, right? So the device is going to sync it. So the CMOS has to be able to sync current, all right? So that's when you're doing CMOS to TTL. Now, when you're going the other direction, and again, you can read all this, when you're going the other direction, the TTL, now typically you can just hook a TTL directly up to a CMOS, it'll usually work, but the TTL is not guaranteed to have its output very high. So it's guaranteed to have an output of like 2.4 volts for a 5 volt TTL, but the CMOS input, it's the lowest voltage that it'll register as a 1, depending on the family, right, is a little bit higher than the 2 volts. So if we go back to that chart, we can probably find it. Let's see if we can find it real quick. Let me just scroll up here. Close your eyes if this makes you sick. I know it does with some people. And right about, keep going, keep going, keep going. Oh, let's see, we're almost there. It's here someplace. I think it's right here. So here's just one. So if we look and we see here's our 2.5 CMOS, here's our 5 volt CMOS and TTL, right? So we can see these two things. So if we've got a TTL chip and it's outputting a high, right? So it's guaranteed to put out a 2.4 volt high. But on the 5 volt CMOS, it requires a 3.5 volt to register a high. Now, when you have a real TTL chip and you output a high, it's usually much higher than 2.4. It'll be up here. It'll be up here, just barely above 3.5 volts. Usually, sometimes almost 4 volts. So it'll usually be okay outputting that high. But if you start loading it, it won't be. All right, and so it's only guaranteed to be 2.4. All right, so you can kind of look at these two voltage levels, right? For high and for low, and then for high and for low. These have to be matched. So that is what is important, or any two families that you want to match together, right? So that's what the importance is here. So in the case of the let's go back to chapter 4 here where we just were. Okay, so back to the figure we were looking at. So if you have a TTL output and you're driving a CMOS input, what you may have to do is put a pull-up resistor to make sure that you get that high value at the voltage level that you need. So you might put a 1 to 3.3K resistor, or maybe even a little bit higher, up to your 5 volt supply. And that'll guarantee when you output a 1, the CMOS will register 1, and when you output a 0, you'll get a 0 also on the CMOS input. So anyway, so that's the whole point is, if you're going to mix logic families, you have to pay attention how these things work. You got to look them up. You got to look up that figure that we just were looking at that shows the different values and how they relate to each other. And then you've got to consider things like current, source current, sinking current, and so forth. And then you can hook these things together. The better approach is don't mix logic families. Try and stick with one logic family and one voltage so that you don't have these problems. One of the biggest problems with playing with Arduinos and Raspberry Pis, especially with Arduinos, 8-bit Arduinos, they're all 5 volt systems. And a lot of ICs these days are 3.3 volts. That's kind of the norm these days for building things, is 3.3 volts. So if you want to interface it, it's difficult. You've got to have what are called level shifters. You have to have multiple voltage supplies, 5 volts and 3.3. Then the other problem is you can just kind of hook these things up and throw caution to the wind, but you may damage an input or an output, and you got to be careful. All right. Now, what I want to show you now is a resource here. So Texas Instruments is one of the biggest semiconductor manufacturers in the world. Texas Instruments, been around for a long time, and this site is just it's an unbelievable potpourri of knowledge and resources, and very, very well written documentation. So if you just go on Google and you look at things on Wikipedia and so forth, remember those are just from people just writing. There's peer review of a sense because other people look at it, but if you look at white papers and application notes that are written by a company like Texas Instruments, that information is very, very, very good. And most of these people writing these things, have masters or PhDs in electrical engineering, so you can really listen to what they're saying and not worry about it. So anyway, what I wanted to do here was I wanted to do this. Let's search for logic family specifications or comparison guides. So you see all these different things that come right up here. So logic family specifications.